Hey guys, good morning, and welcome back again to your Unacademy NEET English channel. I hope all of you doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats with some fire emojis. If all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats. Good morning, people. Good morning, and welcome back. Good morning and welcome back. Good morning and welcome back. Yes, I had to delay the session a bit because there were some technical glitches. Mic was not working, etc., etc. Leave that part aside. So now here I'm in front of you. Yeah. So people, as you all must be knowing, today it's going to be the marathon of our complete class 11th chemistry, right? Now you must be thinking, how come it's possible to complete entire class 11th chemistry in one go? My dear students, let me tell you, if you select any chapter in chemistry, there are some favorite topics in a chapter, right? Like in a chapter, there are like 5-6 topics from which questions will be framed. So I'll be directly on point. I'll be discussing those topics briefly with the question patterns as well, from which questions will be asked. No irrelevant stuff, nothing like that. Okay, nothing irrelevant. I'll be directly on point in the today's session. And at the same time, the handwritten PDF of this particular session I'll be sharing on my Telegram. If you do not know the name of my Telegram channel, let me quickly write the name of the Telegram channel. It is Wassim Bhat Chemistry Official. It is Wassim Bhat Chemistry Official. This is the name of the Telegram channel on which I shall be sharing the handwritten PDF of this particular session as well. Okay. Perfect. How long the class will be? The class, I don't know how long it's going to be. I seriously don't know. Let's see. We have to complete things. Okay. And by the way, let me tell you one more thing. In our class 11th chemistry, what all chapters do we have? Mole concept, redox, atomic structure, periodic classification, chemical bonding, chemical equilibrium, ionic equilibrium, thermodynamics. Then we have GOC, then we have hydrocarbon. So in total, we have 10 chapters. But I'm not going to complete all the 10 chapters. I'll be completing 8 chapters, my dear students. GOC and hydrocarbon will be taken on Wednesday on this particular channel, separately. Okay? So 8 chapters I'll be discussing in the today's session. 2 chapters, right? That will be done on Wednesday. That is your GOC and hydrocarbon. Okay? Perfect. And GOC and hydrocarbon won't be taken by me. It will be taken by KK sir, who takes organic chemistry on this particular channel. All right? Perfect. So before starting the session, let me know which part of the country you guys are watching me from right now. I want to know which state you are from. I want to know, people, which state you are from. Yes, I'll be starting from basics only, don't worry. Before starting, I want to know which state you are watching me from. Every one of you. Every one of you people. Andhra Pradesh, Kashmir, Karnataka, Tamil Nadu, Kerala, Kashmir, Karnataka, Telangana, Goa, UP. Okay. Andhra Pradesh, Punjab. Nice, amazing. Lucknow, Himachal, West Bengal. Okay. Tamil Nadu, Rajasthan, Mizoram, Chhattisgarh, Bihar, Patna. All right. Pondicherry. Perfect, guys. Perfect. I can see majority of the students are watching us from the South Indian part, right? Majority of the students are watching from South India. And from the northeastern part of the country too. That's great. That's great. That's great. Perfect. Should we start then? The ones who have not smashed the like yet, liking the session is mandatory, my dear students. Liking the session is mandatory, so do smash the like button right now. As you know, it's a long marathon, and I would want you guys to be with me till the end. I would want you guys to be with me till the end, okay? Because this is going to be like extremely, extremely important session. Extremely important session this is going to be, my dear students. P block comes in class 12th chemistry. Today we are discussing class 11th chemistry, right? There will be a marathon for class 12th chemistry as well, don't worry. So should we start? All ready? All ready? If you're at 0 also, don't worry. You can still watch this particular session. Don't worry. I'll be starting from the basics only, from the scratch only. Don't worry. Should we start? Just say yes or no in the chats, everyone, so that I'll get going. All right, people. Perfect, perfect, perfect. So let's get going then. Let's get started with the today's session. And the first chapter, which I shall be discussing with you, what is that chapter going to be? That chapter is going to be your mole concept. The first chapter, my dear students. The mole concept. Okay. Now, first of all, before starting the mole concept chapter, let me tell you from which topics questions will be asked in the mole concept chapter. Let me tell you from which topics questions will be asked in the mole concept chapter. My dear students, in your mole concept, the questions will be asked from the basic mole calculation, number 1. Basic mole calculation is the first topic from which question will be asked from the mole concept chapter, right? The second topic from which the question will be asked, that's going to be your stoichiometry. Stoichiometry. The third topic that comes in stoichiometry only, what is that? That's your limiting reagent. That's your limiting reagent. And the last topic from which questions will be asked in mole concept, that is empirical and molecular formula. Empirical and molecular formula. Well, these are the 4 topics from which questions will be asked in the chapter mole concept. Okay? These are the topics from the chapter mole concept from which the questions will be framed. So let's discuss all these topics one by one, my dear students. Let's discuss all these topics one by one. Okay? So first of all, my dear students, the first topic is calculation of moles. Calculation of moles. How do we calculate number of moles of any substance? How do we calculate number of moles of any substance? Let me tell you, we have got 3 formulas to calculate number of moles of any substance. 3 results we have, 3 formulas we have. And I would want you guys to remember all the 3 formulas, and I'll show you how do we apply them as well. The first one, my dear students, number of moles of the substance. Number of moles of the substance, which I represent with N. It is always equal to given mass of the substance in grams divided by molar mass of the substance. Divided by molar mass of the substance. Given mass of the substance divided by molar mass of the substance. This is the first formula with the help of which we can calculate moles of the substance. And this formula is basically valid for solids, liquids, as well as gases. It is valid for solids, liquids, as well as gases. The second formula, my dear students, by means of which we can calculate number of moles of the substance,
that is equal to given number of particles, or you can say given number of entities divided by the Avogadro's number. And I believe all of you know the value of Avogadro's number. It is 6.022 into 10 raised power 23. This is the second formula with the help of which we can calculate number of moles of a substance. And my dear students, this particular formula is also valid for solids, liquids and gases. The third result which we have to calculate number of moles. That formula is basically valid for gases. This particular formula is valid for gases. And the gases should be present at STP, standard temperature pressure. Gas should be present at this particular condition, STP condition. And how do we calculate this? It is simply going to be given volume of the gas in liters divided by 22.4 liters. Or if the given volume of the gas is in ml, then I'm supposed to divide with 22400 ml. So these are basically the three formulas by means of which we can calculate number of moles of a substance. First formula is valid for solids, liquids as well as gases. This formula is also valid for solids, liquids as well as gases. This particular formula, my dear students, it's valid only for gases and the gas should be present at STP condition. Point number one. Point number two, my dear students. Point number two. As I told you, in order to calculate moles, we have got three ways. We have got three formulas to calculate moles, right? Now, either I will be given with the mass of the substance in grams, or I will be given with the number of particles of the substance. Or I will be given with the volume of the gas in liters. That too at STP. Now remember few things, my dear students. Remember few things. Let me tell you, if mass of the substance is given and I'm supposed to calculate moles. If mass is given, moles are to be calculated. What do we do? Given mass of the substance divided by molar mass of the substance. Similarly, if moles are given, mass is to be calculated. Then moles are to be multiplied with molar mass of the substance. Point number one. Point number two, my dear students. If number of particles of the substance are given, and I am supposed to calculate moles, how do I do that? Given number of particles divided by Avogadro's number. That gives me moles. Now, if moles are given, particles are to be calculated, then moles multiplied by Avogadro's number, that gives me particles. Okay. Similarly, my dear students, if volume of the gas is given, and I am supposed to calculate moles, how do I do it? Given volume of the gas divided by 22.4 liters. It gives me moles. And if moles are given, volume is to be calculated. What do we do? Moles multiplied by 22.4 liters. Tell me once in the chats if this diagram is clear to everyone. Pretty much simple. In order to calculate moles, either mass will be given, particles will be given, or volume will be given. Given mass divided by molar mass, that gives me moles. Moles multiplied by molar mass, that gives me mass. Simple. Similarly, given number of particles divided by Avogadro's number, that gives me moles. Moles multiplied by Avogadro's number, that gives me particles. Similarly, given volume of the gas in liters divided by 22.4 liters, that gives me moles. Moles multiplied by 22.4 liters, that gives me volume. Perfect. Now let me show you how exactly we are going to use them. Simple, basic questions I'm starting with. Look at this question, guys. Calculate the number of moles present in 160 grams of NaOH. So first of all, tell me one thing, my dear students. Am I given with the mass of the substance? Yes, I'm given with the mass of the substance. What am I supposed to calculate? I'm supposed to calculate moles of the substance. How do I calculate moles? Given mass divided by molar mass. So given mass I'm representing with W divided by molar mass of the substance. What is the given mass of the substance? It's simply 160 grams. What will be the molar mass of the substance? Molar mass of NaOH. Sodium, its molar mass is 23 grams. Oxygen, 16 grams. Hydrogen, 1. So 23 plus 1 plus 16, that comes out to be 40 grams. So molar mass of NaOH is 40, the value comes out to be 4. Correct? So technically, I would say 160 grams of NaOH means 4 moles of NaOH. As simple as that. Look at the second question. I'm given with the volume of the gas in liters. I'm given with the volume of the gas in liters. I'm supposed to calculate moles. So number of moles of carbon dioxide will be equal to given volume of the gas in liters, divided by 22.4 liters, right? The value comes out to be 3. So 67.2 liter carbon dioxide means 3 moles of carbon dioxide. Agreed? Look at the third one. I am given with the atoms of carbon. That means I'm given with the particles. And when you are given with the particles, you are supposed to calculate moles. How do you do that? Number of moles of carbon will be equal to given number of particles divided by Avogadro's number, whose value is approximately 6 into 10 raised power 23. The value comes out to be 4. Correct, people? Similarly, here also, if you look carefully, I'm given with the particles of water, molecules of water. Molecules means particles. So when particles are given, moles are to be calculated. What do? I'll say number of moles of water will be equal to given number of particles, which is 48 into 10 raised power 24, divided by Avogadro's number, which is 6 into 10 raised power 23. The value comes out to be 80. Right? Perfect. So you got to know how do we calculate moles if mass is given, if particles are given, if volume is given. Correct? Now, my dear students, tell me one thing. Sometimes in the question, you will be given with mass of the substance. You will have to calculate its volume. Sometimes in the question, you will be given with the mass of the substance. You'll be given with the mass of the substance. And you will be supposed to calculate the volume. So what do? You will be starting from the mass. Just a second, guys. I think there is electricity cut. I have to turn some lights off for a moment till generator is on. Okay. All right. See, guys. Sometimes in the question, you will be given with the mass of the substance. You'll be supposed to calculate volume. So what do? You have to start from mass. You have to go to volume. How do you go from mass to volume? You have to follow some arrows which will take you from mass to volume. What all arrows do you have to follow? See, guys, I have to start from mass. I have to go to volume. So my first step will be given mass divided by molar mass. That will give me moles. Moles multiplied by 22.4 liters. That will give me volume. As simple as that. Right? As simple as that. Similarly, for example, there is a question in which volume is given. I'm supposed to calculate particles. Volume is given. I'm supposed to calculate particles. So I'll be starting from volume. I'll have to reach to particles. So I'll have to follow all the arrows which will take me from volume till particles. Now, what all arrows I'll have to follow? Given volume divided by 22.4 liters. That gives me moles. Moles multiplied by Avogadro's number. That gives me particles. There will be a question in which, for example, particles will be given. Mass will be calculated. Particles will be given and will be supposed to calculate mass. So what do? I'll be starting from particles. I'll have to reach to mass. So given number of particles divided by Avogadro's number. That will give me moles. Moles multiplied by molar mass. That will give me mass. Simple. Correct? Now, people, let's have a look. What kind of the questions can be framed from this? Look at the first question. Calculate the mass of 67.2 liters of carbon dioxide at STP in grams. Just understand one thing. What are we given with and what are we supposed to calculate? What are we given with and what are we supposed to calculate? Just tell me that. My dear students, if you look at this particular question, we are given with volume. We are supposed to calculate mass. Volume is given, mass is to be calculated. Volume is given, mass is to be calculated. Volume is given, mass is to be calculated. What is the volume we are given with? We are given with 67.2 liters of carbon dioxide, right? We are supposed to calculate its mass. So I'll be starting from volume. I'll have to go to mass. How many arrows I'll have to follow? I'll have to follow 2 arrows. My dear students, the first arrow, given volume divided by 22.4 liters. That will give moles. So first step will be number of moles of carbon dioxide will be equal to given volume, that's 67.2 liters divided by 22.4 liters. The value comes out to be 3. What is this 3? These 3 are the moles of carbon dioxide. Now moles multiplied by molar mass. That gives me mass. So mass of carbon dioxide will be equal to moles of carbon dioxide multiplied by molar mass of carbon dioxide, right? How many moles of carbon dioxide we have? 3. Molar mass of carbon dioxide is 44. The value comes out to be 132 grams, right? So what does it mean? What does it mean? It means that 67.2 liter carbon dioxide at STP will have the mass of 132 grams. As simple as that. Is it clear? Everyone in the chats, is it clear? And people, if it is clear, tell me the answer of the second question. Tell me the answer of the second question. Tell me the answer of the second question. Sir, please increase the pace a bit. Don't worry about the pace. I know what exactly I'm doing. Just be with me. We'll complete everything, okay? What do you think about this one, guys? Calculate the number of molecules present in 440 grams of carbon dioxide. I am given with mass. I'm supposed to calculate particles. So my first step is number of moles of carbon dioxide. That will be equal to given mass of carbon dioxide in grams divided by molar mass of carbon dioxide. The value comes out to be 10. So these are the moles. Now the second step, from moles till particles. From moles till particles. So moles are supposed to be multiplied with Avogadro's number. You'll be getting the particles, right? So I'll say number of molecules of carbon dioxide. Number of molecules of carbon dioxide will be equal to 10 multiplied by Avogadro's number. So this is the final answer of the question, right? I believe this is clear. I believe this is clear. It's hot here. I need to put my jacket off, I think. Just a second. Let me know, guys, if this is clear to everyone. Let me know if this is clear to everyone. Quickly. Yeah? All right, people. Amazing. Can you quickly solve this question as well? Can you quickly solve this question as well? Can you quickly solve this question as well? My dear students, what are we given with? We are given with mass. We are supposed to calculate volume. Mass to volume. So firstly, I'll be converting mass into moles. So number of moles of carbon dioxide will be equal. Sorry, number of moles of, this is SO2 here. Just change it, it's SO2. Huh? It is SO2. Number of moles of SO2 will be equal to given mass of SO2 in grams divided by its molar mass, that is 64 grams. The value comes out to be 2. So I got the moles. Now from moles to volume, what do we do? Moles multiplied by 22.4 liters. That gives me volume. So volume of SO2 will be equal to moles multiplied by 22.4 liters. The value comes out to be 44.8 liters. Do you understand this? Is it clear? Is it clear, people? Is it clear? Is it clear? Now, look at the next one. Look at the next one, guys. Look at the next one. If you look at the next question, calculate the atoms in 16 grams of helium. We have to calculate particles. We are given with mass. We have to calculate particles. So first of all, from mass to moles, number of moles of helium will be equal to given mass of helium in grams divided by molar mass of helium. That's 4 grams. The value is 4. Now moles multiplied by Avogadro's number. That gives me particles. Particles means atoms. So I got the atoms of helium. How many atoms of helium do we have? 4 Na. Look at the second question. Again, we are given with mass, but the mass is not given in grams. It is given in AMU, or you can say U, right? 16 U of helium. Tell me one thing, guys. What is the mass of one atom of helium? 4U. 4U is the mass of one atom of helium, correct? If I ask you what is the atomic mass of helium, you will say 4 AMU or 4U. What is the atomic mass of helium? 4 AMU or 4U. So atomic mass means mass of one atom. So technically I would say 4U is the mass of one atom. If 4U is the mass of one atom, it means 1U will be the mass of 1 by 4 atoms. 1U will be the mass of 1 by 4 atoms. So 16U, multiply both sides with 16. 16U will be 1 by 4 into 16 atoms. So which comes out to be directly 4 atoms. Right? So I would say 16U is nothing but 4 atoms of helium. Correctly done? Look at the next one. Molecules in 126U of HNO3. HNO3. If I ask you what is the molecular mass of HNO3, you'll calculate it 1 plus 14 plus 16 into 3. That will come out to be 63U. 63U is the molecular mass of HNO3. That means 63U is the mass of one molecule of HNO3. It is the mass of one molecule of HNO3. If 63U is the mass of one molecule of HNO3, What about 1U? 1U will be the mass of 1 by 63 molecules of HNO3. Right? Therefore, 126U, multiply both sides with 126. 126U will be the mass of how many? Into 126. The value comes out to be 2. So, I would say the mass of 2 molecules of HNO3 is nothing but 126U. Clear? I believe this sort of a question is clear. Now, my dear students, before moving on to the next question, I need to tell you one thing. Remember that. My dear students, remember molar mass of the substance, molar mass of the substance is equal to mass of one particle of the substance in grams multiplied by Avogadro's number. Remember this particular result. Molar mass of the substance is equal to mass of one particle of the substance multiplied by Avogadro's number. Why this is important? I'm giving you a simple question, you'll understand its significance. For example, I have a question like this. Let's say, my dear students, the mass of one atom, let's say the mass of one atom of an element X is equal to 4 into 10 raised power minus 23 grams. Let's say the mass of one atom of X is equal to 4 into 10 raised power minus 23 grams. I'm asked to calculate molar mass of X. Or let me modify the question like this. I'm supposed to check, here they have mentioned that, identify the element. The mass of one atom of an element is this. We are supposed to identify the element. How do we do it? Pretty much simple, guys. Understand. So first of all, if I know the mass of one atom of X, can I calculate the molar mass of X? I can do that. Molar mass of substance is equal to mass of one particle of the substance multiplied by Avogadro's number. This term cancels out. 6 4s are 24 grams. So molar mass of element is 24 grams. Now tell me one thing. If molar mass of the element is 24 grams, that means atomic mass of the element will be 24 AMU. Which element is there whose atomic mass is 24 AMU? Magnesium is the element whose atomic mass is 24 AMU. As simple as that. Correct, people? Correct? Am I clear with this? Yes or no in the chats? Absolutely. If they ask you a question like this, calculate the molar mass of electron. Let's say this is the question. Calculate the molar mass of electron. Will you be able to solve this? You should be in a position to solve this. My dear students, I will say molar mass of electron is nothing but mass of one electron into Avogadro's number. Mass of one particle into Avogadro's number. Now, what is the mass of one electron in grams? It is 9.1 into 10 raised power minus 28 grams. Just multiply this with Avogadro's number and you're done. This value will be 6 9s are 54.6 into 10 raised power minus 5 grams. This is the molar mass of electron. Correct? This is the molar mass of electron. Now, my dear students, if they ask you a question like this, simple question. Let's say the question is, the mass of one atom of an element X is 2 into 10 raised power minus 23 grams. The mass of one atom of X is 2 into 10 raised power minus 23 grams. Now they are asking us to calculate the moles in 72 grams of X. Calculate the moles in 72 grams of X. So technically, if you see, what are we supposed to calculate? We are supposed to calculate number of moles present in 72 grams of X. So we are given with mass. We are supposed to calculate moles. So I'll say number of moles of X will be equal to given mass of X in grams divided by molar mass of X. But I do not know the molar mass of X yet. My dear students, molar mass of X will be mass of one atom of X. Mass of one atom of X multiplied by Avogadro's number. Right? This term cancels out. The value comes out to be 12 grams. So this is the molar mass of X. If you got the molar mass of X, so it's going to be given mass divided by molar mass. The value comes out to be 6. Done and dusted, right? Perfect. Someone is saying 10 raised power minus 31.
That is 9.1 into 10 raised power minus 31 kg. But we have to take in grams. That's why I wrote 10 raised power minus 28 in the last question. People, am I clear with this? Am I clear with this? Yes or no quickly in the chats? Every one of you. Every one of you. I want the chats to be running. I don't want the session to be boring, etc., etc. Quickly, people. Everything done? All right. Now, moving on to something called as stoichiometry. Again, one more important concept from which questions are frequently asked. Stoichiometry. My dear students, understand this properly. I'll give you simple methods to solve the questions based on stoichiometry. Okay? See what you have to do. See what you have to do. My dear students, for example, I'm taking a general reaction, N2 gas plus H2 gas. It gives, for example, NH3 gas. It gives, for example, NH3 gas. This is the reaction, for example. Okay? If I ask you, is the reaction balanced or not? No, the reaction is not balanced yet. So let's balance the reaction. This should be 3 times. This should be 2 times. This should be 1. Now this 1, 3, and 2, this 1, 3, and 2 is something I'll be calling as stoichiometric coefficients. Stoichiometric coefficients. Stoichiometric coefficients. Now I'm going to tell you one statement by means of which you can solve all the questions of stoichiometry. What you have to do. There will be some questions. There will be some questions. There will be some questions. Wherein? There will be some questions. Wherein? They'll ask you to calculate the moles of NH3 formed in the reaction. Moles of H2 reacted in the reaction, etc. etc. A lot of questions will be that. Perfect. Now, my dear students, what you need to do here is just write a simple statement. A statement is like this. You will write number of moles of N2. First of all, is N2 reacting in this reaction? Yes. So I'll say number of moles of N2 reacted in the reaction divided by stoichiometric coefficient of N2 is always equal. H2 is also the reactant. It will be reacting. I'll write number of moles of H2 reacting in this reaction divided by stoichiometric coefficient of H2 will be always equal to number of moles of NH3. Is NH3 reactant or product? It is product. So I'll say it is formed in the reaction divided by stoichiometric coefficient of NH3. Just this statement and you can solve the questions easily. Just this statement, you can solve the questions easily. Number of moles of N2 reacted divided by stoichiometric coefficient will be always equal. Number of moles of H2 reacted divided by its stoichiometric coefficient is equal. Number of moles of NH3 formed divided by its stoichiometric coefficient. Now see how I'm going to solve, how I'm going to use this in the questions. Pretty simple concept. I'm not showing you the unitary method here. I'm just giving you this concept and you can solve the questions easily. How exactly? Have a look. My dear students, look at this question. Look at this question. The question says, calculate the mass of O2 gas. Calculate the mass of O2 gas produced on heating 12.25 grams of KClO3. As far as the question is concerned, you are going to heat up KClO3. Well, you should know when you heat up KClO3, it gets converted into KCl, and with KCl, you get O2 gas. This is something which every one of you should know. When you heat up KClO3, you get KCl and you get O2. Now, is the reaction balanced? No, the reaction is not balanced. Reaction is not balanced. So balance the reaction first. This is 2 times. This is 2 times. This is 3 times. Balanced. The first step always is to convert the given quantity into number of moles. I'm given mass of KClO3. Convert it into moles first of all. So number of moles of KClO3 will be equal to given mass of KClO3 in grams divided by molar mass of KClO3, which is 122.5. When you calculate this, potassium 39, 35.5, 16 into 3, that comes out to be 122.5. So I'm given with 0.1 moles of KClO3. So my point is, convert the given quantity to moles, right? Now people, understand one thing. What are we supposed to calculate? The mass of O2. The mass of O2 produced on heating 12.25 grams of KClO3. That's the thing. Now we use the stoichiometric equation. Equation is number of moles of KClO3 divided by its stoichiometric coefficient will be equal. Nothing to do with this. Just talk about this one. Number of moles of O2 divided by its stoichiometric coefficient. What am I supposed to calculate? I'll calculate number of moles of O2 from here. So number of moles of O2 will be, take 3 here, it becomes 3 by 2 times number of moles of KClO3, right? So number of moles of O2 will be equal to 3 by 2 times number of moles of KClO3. I've calculated that 0.1. The value comes out to be 0.15.
So these are the moles of O2. Since O2 is the product, so O2 is being produced. So these are the moles of O2 produced. But am I supposed to calculate moles of O2 produced? No. I'm supposed to calculate mass of O2 produced. How do I convert moles into mass? Simple. Moles multiplied by molar mass of O2. The value comes out to be 4.8 grams. So this is the mass of O2 produced. Am I clear? Am I clear, people? Am I clear? Quickly in the chats. Quickly in the chats, everyone. Did you understand how do we deal with such kind of the questions? Yeah? Done and dusted? Isn't it simple, guys? Just write the stoichiometric equation and you're done. You're sorted. You're sorted. Perfect. Perfect, guys. One more similar question. I've taken the same question but in the reverse form. This is the same question but in the reverse form. Calculate the mass of KClO3. Calculate the mass of KClO3, which is required to produce 4.8 grams of O2 during its decomposition. So first of all, KClO3 gives KCl and O2. Reaction is 2 times, this is 2 times, this is 3 times. Balanced reaction. Now, calculate the mass of KClO3 required to produce what? 4.8 grams of O2. What is my first step always? Convert the given quantity into moles. Convert the given quantity into moles, right? My dear students, we are given with mass of O2, so convert it into moles. So number of moles of O2 is given mass of O2 in grams divided by molar mass of O2, right? The value comes out to be 0.15. I got the moles of O2. Now do one thing. Use the stoichiometric equation. I'll write number of moles of KClO3 divided by stoichiometric coefficient is equal to number of moles of O2 divided by stoichiometric coefficient, right? I need to calculate number of moles of KClO3 here. This will be equal to 2 comes here, so it is 2 by 3 times number of moles of O2, which can be written as 2 by 3 times number of moles of O2 is 0.15. The value comes out to be 0.1. I got the moles of KClO3. My dear students, if you got the moles of KClO3, are you supposed to calculate moles of KClO3? No. You're supposed to calculate mass of KClO3. So mass of KClO3 will be equal to moles of KClO3 multiplied by molar mass of KClO3. The value comes out to be 12.25 grams. Simple. This is something I was supposed to calculate. Understood? Yes or no in the chats? Is it clear, my dear students? Every one of you? Is it clear? I believe yes. Okay, if this is clear, then there is something which I need to tell you. What is that? Understand. Before solving this question, I remember 2 things. Whenever you have got an organic compound like this, CXHY, whenever you will have an organic compound like this, CXHY, when you do its combustion, it will lead to the formation of carbon dioxide, and with carbon dioxide you get water. Whenever you have got an organic compound containing carbon and hydrogen, when you do its combustion, it will lead to the formation of carbon dioxide and water. Now, there is a special way of balancing this reaction. How exactly? Tell me, how many carbon atoms do you see here? X. Take this X, make it stoichiometric coefficient here. What is the stoichiometric coefficient of hydrogen here? Y. So take this Y and make this Y by 2 here. Stoichiometric coefficient of oxygen will be X plus Y by 4. This is something which I want every one of you to remember. My dear students. And if you can remember this, we can easily solve the question. How exactly? Try to understand. Calculate the volume of carbon dioxide at STP by complete combustion of 570 grams of octane. What is the molecular formula of octane? It is C8H18. You are doing its what? You are doing its combustion. It will lead to the formation of carbon dioxide, and with carbon dioxide we get water. Right? Now, my dear students, tell me one thing. Is the reaction balanced? No. Have I taught you how to balance this reaction? Yes. What is the value of X here? X value is 8, so that 8 goes here. What is the value of Y here? 18. 18 by 2 is 9. This will be X plus Y by 4. 18 plus 18 by 4. When you solve, the value comes out to be 25 by 2. Right? Balanced. After balancing, my dear students, tell me, what am I supposed to do? Convert the given quantity to moles. We are given with mass of octane. So convert the mass of octane into moles. So it will be given mass of octane in grams divided by, when you calculate molar mass of octane, it comes out to be 114. The value will be 5. Okay. The value will be 5. Now tell me one thing. What am I supposed to calculate? Calculate the volume of carbon dioxide at STP by complete combustion of 570 grams of octane. Use the stoichiometric equation and you are done. I can say number of moles of octane reacted divided by its stoichiometric coefficient, that's 1, is equal to number of moles of carbon dioxide produced divided by stoichiometric coefficient 8, right? If I take 8 here, I'll say number of moles of carbon dioxide is equal to 8 times the number of moles of octane. So it is 8 multiplied by number of moles of octane. I've calculated that's 5. So 8 multiplied by 5 is 40, right? So I got, if you look carefully, my dear students, we got to know 40 moles of carbon dioxide produced. And if 40 moles of carbon dioxide produced, so what is the volume of carbon dioxide produced? Moles multiplied by 22.4 liters. The value comes out to be 896 liters. Tell me, will you be able to solve these sort of questions? Yes or no in the chats quickly? Yes or no in the chats, my dear students? Every one of you quickly in the chats. I want to know in the chats quickly. I want to know in the chats quickly. Yes or no, people? I'm looking at the chats only. Quick, quick, quick. Done? Done, people? Simple thing, guys. Moles by stoichiometric coefficient is equal to moles by stoichiometric coefficient is equal to moles by stoichiometric coefficient. Nothing else. You just have to convert the given quantity into moles first. Then write the equation and you are done. Chalo, I'll solve one more question for you. I'll solve one more question for you so that you understand properly. Let's say this is the question. What is my first step? Say reaction is already given. How many grams of NO2? How many grams of NO2 are required to produce 25.2 grams of HNO3? So what is my first step always? Convert the given quantity into moles. So number of moles of HNO3 will be equal to number of moles of HNO3 will be equal to given mass of HNO3 in grams, given mass of HNO3 in grams divided by its molar mass. Given mass of HNO3 in grams divided by its molar mass. When you solve, how much it will be? Almost 0.4, right? Almost 0.4. What happens to electricity? Is it working? Yes. Okay. All right, people. So first of all, convert the given quantity into moles. So number of moles of HNO3 is equal to given mass of HNO3 divided by its molar mass. The value comes up to be approximately 0.4. Now, use the stoichiometric equation. I'll write number of moles of NO2 divided by stoichiometric coefficient of NO2 is equal to number of moles of HNO3 divided by stoichiometric coefficient of HNO3. Simple. What am I supposed to calculate? I'm supposed to calculate moles of NO2. This will be equal to 3 divided by 2 times number of moles of HNO3, that is 0.4. It will be 0.6. I got the moles of NO2. Now, what will be the mass of NO2? Moles multiplied by molar mass of NO2. Molar mass of NO2 will be how much? It will be, I think, 46, right? The value will be 27.6 grams. So this is the mass of NO2 which I was supposed to calculate. Simple. Done and dusted. Now, my dear students, let's move on to one more concept. That is your limiting reagent. Let's move on to one more concept. That's your limiting reagent. My dear students, if you look at the limiting reagent concept, what happens here? Understand properly. For example, you have got the reaction 2A plus 3 times B, it gives 5 times C. Let's say this is the reaction. Okay? Understand what I'm going to do. Let's say this is the reaction. Now I'm writing time t is equal to 0. What does that mean? That means the reaction has not started yet. So, if the reaction has not started, that means moles of C in the container will be 0. Moles of C in the container will be 0 because the reaction has not started. Product has not got formed yet. Let's say I'm given with 10 moles of A and I've got 10 moles of B. So, before the start of the reaction, assume that we had 10 moles of A, we had 10 moles of B, and there will be 0 moles of C, right? Because the reaction has not started yet. Now, understand one thing. As the reaction starts, number of moles of reactants will keep on decreasing.
as the reaction starts, as the reactants keep on reacting and forming the products, number of moles of reactants will keep on decreasing. Number of moles of products will keep on increasing. Number of moles of reactant will keep on decreasing. Number of moles of product will keep on increasing. Can I say out of these two reactants, there will be a reactant which will be getting completely consumed? Out of these two reactants, you will find a reactant which will get 100% consumed. You call that particular reactant as the limiting reagent. So limiting reagent is that reactant which gets completely consumed, Now the point is, how do we identify the limiting reagent? How do we identify the limiting reagent? What do you have to do? What do you have to do for that? Given moles divided by respect to stoichiometric coefficient. See, this is 10 divided by its stoichiometric coefficient is 2. This is 10 divided by its stoichiometric coefficient is 3. This value comes out to be 5. This value comes out to be 3.33. Which value comes out to be lesser? This is the lesser value. The one that gets the lesser value, that's always your limiting reagent. So B is my limiting reagent here. If B is the limiting reagent, A would be the excessive reagent. If B is the limiting reagent, A would be the excessive reagent. Now tell me one thing, my dear students. First of all, at time t is equal to 0, no product formation, only reactants present in the container. As the reaction starts, moles of reactants will keep on decreasing. There will be one reactant which will be getting 100% completely consumed, right? That reactant I'll be calling as the limiting reagent. How do I identify the limiting reagent? Given moles divided by stoichiometric coefficient. Given moles divided by stoichiometric coefficient. The one that gets the lesser value, that's always my limiting reagent. So here in this particular case, B is my limiting reagent. If B is my limiting reagent, it would have got completely consumed in the reaction. So after some time, you'll find nothing. No moles of B in the container. But when B would have got consumed, there will be still A present in the container. Some moles of A will be still left in the container because A is the excessive reagent. And at the same time, some moles of C would have got formed also. Some moles of C would have got formed also. Do you understand? B is the limiting reagent, completely consumed. A is the excessive reagent. That means out of 10 moles of A, some moles would be still left in the container. Similarly, some moles of C would have got formed as well. Now they'll ask us the questions in which they'll ask us how many moles of C have got formed, how many moles of A are still left in the container. How do we tackle those questions? How do we tackle those questions? Understand how do we tackle those questions? One simple question, guys. You are given the reaction, okay? 3 moles of NaOH. So at time t is equal to 0, we are given 3 moles of NaOH, 4 moles of H2SO4. Since I wrote time t is equal to 0, neither this got formed nor this got formed because the reaction has not started yet. Reaction has not started yet. Now which one is the limiting reagent? How do we check that? Given moles divided by respective stoichiometric coefficients. Given moles divided by respective stoichiometric coefficients. So it's 3 divided by 2. 3 divided by 2 is 1.5. This is 4 divided by 1. That is 4. Which one is getting the lesser value? This is the lesser value. So NaOH is my limiting reagent. The one that gets the lesser value, that's always your limiting reagent. Done and dusted. Right? Now, for example, moving on to the next question. For example, this is the question. I'm given the reaction 6 times LiH plus 8 times BF3. It gives 6 times LiBF4. 6 times LiBF4 plus B2H6. For example, this is your reaction. Now, at time t is equal to 0, we are starting with 2 moles each of reactants. So this would be 0 in the beginning. This would be 0. Now, what is the question saying? What is the question saying? Calculate the moles of B2H6 formed. How many moles of B2H6 have got formed? How do I do that? Tell me one thing, guys. Tell me just one thing. Which one is the limiting reagent? 2 divided by 6. 2 divided by 8. Which one is getting the lesser value? BF3. So this is my limiting reagent. My dear students, limiting reagent decides everything in the reaction. Limiting reagent decides how many moles of products would get formed. Limiting reagent is going to decide how many moles of product would have got formed. So do one thing, write the stoichiometric equation, right? In terms of BF3 and B2H6. So what do? I'll write number of moles of BF3 divided by stoichiometric coefficient, that's 8, is equal to number of moles of B2H6, which we have to calculate, divided by its stoichiometric, that's 1. So I would say number of moles of B2H6 is equal number of moles of BF3 divided by 8.
How many moles of BF3 I had? 2 divided by 8. The value comes out to be 1 by 4. So 1 by 4 moles of B2H6 would have got formed. Simple. I wrote the stoichiometric equation and I just related limiting reagent with this. That's it. Nothing more, nothing less. Understood? I'll show you one more question. With that, things will be more clear. For example, this is the question. The reaction is given. Now, at time t is equal to 0, we are starting with 10 moles each of reactants. We are starting with 10 moles each of reactants. This would be 0 in the beginning. This would be 0. Now, the question is saying, calculate the moles of barium phosphate formed. Calculate the moles of barium phosphate formed. So, identify the limiting reagent first. Given moles divided by stoichiometric coefficient. 10 by 3, that is 3.33. 10 by 2, that's 5. Which one is getting lesser value? BaCl2. So, this is limiting reagent. So, write the stoichiometric equation in terms of these two. So, I'll write number of moles of BaCl2 divided by its stoichiometric coefficient is equal to number of moles of barium phosphate divided by its stoichiometric coefficient. That's 1. I need to calculate number of moles of barium phosphate, which will be equal. Number of moles of barium phosphate is equal. Number of moles of BaCl2 divided by 3. Number of moles of BaCl2 are given to me in the question. That's 10. 10 by 3 is how much? 3.33. So these are the moles of barium phosphate which would have got formed at the end of the reaction. Now tell me in the chats, is the concept of limiting reagent also clear? Tell me guys, quick. Quickly in the chats. Quickly in the chats. Someone is saying LiH is the limiting reagent. Where is LiH limiting reagent? Is LiH limiting reagent? I want to eat your brain. 2 divided by 6. And here it's 2 divided by 8. Which one is lesser? 2 by 6 or 2 by 8? Is 2 by 6 lesser or 2 by 8 is lesser? 2 by 8 is lesser. Right? So BF3 is your limiting reagent. All right. Perfectly, guys. Moving on to one last topic of the mole concept. These are the 4 short topics from which questions will be asked from the chapter mole concept. Let me tell you that very honestly. Whenever question asked is coming from mole concept, it will be coming from these topics only. Okay? Just keep that thing in mind. Just keep that thing in mind. I'm telling you that. Okay. See guys, this is one more important topic and this is the easiest one too. I know you love it because you just have to divide things and get the answer, right? So understand. First of all, what is empirical formula and what is molecular formula? Let me make you understand all this particular concept in one slide. That's it. In one slide, guys. If I talk about glucose, do you know the formula of glucose? C6H12O6. This is the formula of your glucose. C6H12O6. My dear students, how many elements do you see? 3 elements. Can you tell me what is the atomic ratio here? It is 6:12:6. This is the atomic ratio. 6:12:6. Okay, this is the atomic ratio. Can I further simplify this ratio? Absolutely, I can further simplify this ratio. It can be written as 1:2:1. So how many ratios do you see here? I can see 2 ratios. This particular ratio I'll be calling as the actual ratio. This is what I call as actual ratio. This is what I call as the simplest ratio. This is what I call as simplest ratio. Now, my dear students, as per the actual ratio, the formula is C6H12O6. As per the actual ratio, the formula is C6H12O6. And that particular formula, which gives the actual ratio, we call that formula as the molecular formula. That particular formula which gives the actual ratio, we call that formula as the molecular formula. Now, as per the simplest ratio, what should be the formula? C1H2O1. So that particular formula which gives the simplest ratio, we call that as the empirical formula. So there are 2 representations. One is molecular formula, one is empirical formula. Molecular formula gives me the actual ratio of the atoms. Empirical formula gives me the simplest whole number ratio of the atoms. As simple as that. Now people try to understand. Remember, with the help of molecular formula, we can calculate molecular mass. And with the help of empirical formula, you can calculate empirical mass. With the help of molecular formula, you can calculate molecular mass. With the help of empirical formula, you can calculate empirical mass. How exactly? Have a look. I'll say molecular mass is equal to 12 into 6 plus 1 into 12 plus 16 into 6. The value comes out to be 180 U. This is the molecular mass of glucose. This is the molecular mass of glucose. Now, what about the empirical mass? Use the empirical formula. It is 12 into 1 plus 1 into 2 plus 16 into 1. The value comes out to be 30 U. This is the empirical mass. I got the molecular mass of glucose. I got the empirical mass of glucose. I got the molecular mass of glucose. I got the empirical mass of glucose. Now, after getting the molecular mass and empirical mass, there is a term which I'm defining, that's X. X is nothing but, it is the ratio of molecular mass and the empirical mass. It is the ratio of molecular mass and empirical mass. And once you get X, then there is one more formula which you need to know. Molecular formula is equal to empirical formula multiplied by X. Remember these two results as well. Now I'll show you how do we apply all this in the questions. Again, first of all, we have got two ratios here, actual ratio and simplest ratio. As per actual ratio, this is the formula. As per simplest ratio, this is the formula, right? This formula is giving the actual ratio. We call it as molecular formula. This formula is giving the simplest ratio. We call it as the empirical formula. With the help of empirical formula, we calculate empirical mass. With the help of molecular formula, we calculate molecular mass. And once we get molecular mass and empirical mass, you need to get the value of X. X is what? X is a number. What number? Ratio of molecular mass and empirical mass. Once you get X, then I would say molecular formula is equal to empirical formula multiplied by X. Right? Now guys, try to understand one more thing. Try to understand one more thing. Remember, there is one more result. Do remember that result as well. You'll use that in the questions. Molar mass, or you can say molecular mass, is nothing but it's 2 times vapor density. Sometimes in the question, they'll give you the vapor density. Sometimes in the question, they'll give you the vapor density. From vapor density, you need to calculate molecular mass. How? Vapor density multiplied by 2, that gives you molecular mass. Remember this result as well. This will be used in the question as well. Now you must be thinking, how questions will be framed out of all this? It's a very simple concept. Just remember a few steps and you're done. Just remember a few steps, guys. Remember a few steps. For example, this is the question. The question is calculate the empirical formula of the compound that contains potassium, chromium, oxygen. So you have got a compound, and in the compound, what all elements are present? There is potassium present, there is chromium present, there is oxygen present. In the compound, there are 3 elements present: potassium, chromium, oxygen. Let me tell you, in the question, you will be either given with mass percentage of the elements, or you will be given with the masses of the elements directly, or you will be given with the mass ratio of the element. Out of these 3 things, anything will be given in the question. Either you will be given with mass percentage of these elements, or directly masses of these elements, or the mass ratio of these elements. Now, in this question, what are we given with? If you look carefully, we are given with the mass percentage of these elements. What is the mass percentage of potassium that's given to me? That is 26.6%. What is the mass percentage of chromium that's given to me? How much is that? That is 35.4%. What is the mass percentage of oxygen that's given to me? 38.1%. So I'm given with mass percentage of these elements in this question, right? Anything out of these 3 can be given. Okay? And right now in this question, I'm given mass percentage. Now tell me one thing. What is the atomic mass of potassium? 39. Chromium 52. Oxygen 16. My first step always is to calculate the atomic ratio. How do I calculate atomic ratio? How do I calculate atomic ratio? Whatever things are given, divide these things by their respective atomic masses. Divide these things by their respective atomic masses. So it will be 26.6 divided by 39. This will be 35.4 divided by 52. This will be 38.1 divided by 16. Correct? When you solve this, this value comes out to be 0.68. This value will also come out to be 0.68. This value will come out to be 2.38. Right? Now people tell me one thing. Which one is the least number among these 3? The least number is 0.68. I'll be dividing all of them with the least number so that I get the least atomic ratio. So least atomic ratio will be 0.68 divided by 0.68. Similarly, 0.68 divided by 0.68. Similarly, 2.38 divided by 0.68. This value will be 1. This value will be 1. This value will be 3.5. Do you see the ratio? It is 1:1:3.5. The ratio, if I talk about potassium, chromium, oxygen, the ratio is coming out to be 1:1:3.5. Now, if I ask you, Is it the simplest whole number ratio? Is it the whole number ratio? It is not the whole number ratio. So convert it into whole number ratio. So what do you need to do? Multiply throughout with 2. If you multiply throughout with 2, this becomes 2 is to 2 is to 7. So I would say the empirical formula of the compound will be K2Cr2O7. Simple. Right? This is the general method of solving this particular question. If I'm clear, let me know once in the chats so that I can solve one more question. Quickly in the chats, people. Every one of you, quickly in the chats. Quickly in the chats. Every one of you, quickly in the chats. Yeah? Amazing. One more question I'm giving people so that it makes every single thing clear to you. You have got a compound that contains nitrogen and oxygen. The compound contains nitrogen and oxygen. As per the question, my dear students, mass ratio of nitrogen and oxygen is given. How much is that? 7 is to 16. 7 is to 16. Mass ratio of nitrogen and oxygen is given. 7 is to 16. What is my first step always? To calculate the atomic ratio. How do I get the atomic ratio? Whatever is given, divide them with respect to atomic masses. So 7 divided by 14. This is 16 divided by 16. This value will come out to be 0.5. This value will be 1. Which one is the least number among the two? 0.5. So divide both of them with 0.5. I'll be getting the least atomic ratio. So it is 0.5 divided by 0.5. That's 1. It is 1 divided by 0.5. That is 2. So the least atomic ratio among nitrogen and oxygen, I got to know as 1 is to 2. So that means empirical formula of the compound is N1O2. Empirical formula of the compound is N1O2. But am I supposed to calculate empirical formula? Am I supposed to calculate empirical formula? No. I am not supposed to calculate empirical formula. What am I supposed to calculate? I am supposed to calculate molecular formula. Few minutes back I told you molecular formula is nothing but empirical formula multiplied by X. Have we calculated molecular formula? Sorry, have we calculated empirical formula? Yes. Have we calculated X? No. I need to calculate X. What is X? X is molecular mass divided by empirical mass. Is molecular mass given? No. Vapor density is given. I told you a few minutes back. Molecular mass is equal to twice vapor density. So 46 into 2 will be 92 divided by. Calculate empirical mass. Empirical mass you can calculate from empirical formula. 14 into 1 plus 16 into 2. The value is 46. The value comes out to be 2. So X is 2. What was the empirical formula? N1O2. What is the value of X? X value is 2. So the formula is N2O4. This is your molecular formula, people. This is your molecular formula. Am I clear? Am I clear? Am I clear? Everyone in the chats? Am I clear? Everyone in the chats? Yes? Sir, I just joined. Shall I continue? Yes, you can continue from here. No worries. I want everyone to let me know in the chats if all of this is clear or not. Quick, 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 everyone. Quickly, guys. If you look at this question, again the similar type. When you look at this particular question, again the similar type, people, yeah? Again the similar type of question. Just look at the question. Just look at the question and tell me whether you will be able to do it or not. Whether you'll be able to do it or not. Say yes or no. You should be in a position to solve this. Yes. Amazing, guys. So let's move on now to your atomic structure. So first of all, let me tell you what all concepts will be asked in the atomic structure. See, the atomic structure is a very vast chapter. You don't need to do all the things right now in atomic structure. Only do those things which will be asked in the exam. That means the relevant stuff.
There is a lot of irrelevant stuff as well, which is not asked, like discovery of electron, discovery of proton, discovery of neutron, Millikan's oil drop experiment, etc., etc., etc. Nothing to do with that, yeah? We are going to talk to the point. We are going to talk to the point. So, from which topics questions will be asked in atomic structure? So, let's have a look. My dear students, the first topic from which the question will be asked, that is your Bohr's model. And in Bohr's model, from where? From where? Radius, velocity, time period, frequency, right? Similarly, total energy. This is the first topic from which questions will be asked in the atomic structure. Number one. Number two is going to be your hydrogen spectrum. Hydrogen spectrum. That Lyman, Balmer, Paschen, etc. Calculate the minimum wavelength, maximum wavelength, right? Rydberg's formula, every single thing here. Every single thing here. My dear students, the third thing. What is that? That's your Heisenberg. Heisenberg's uncertainty principle. That is the next important topic from which question will be asked. Yeah. The next topic, my dear students, the next topic from which question will be asked in the atomic structure, what is that? That is your questions based on quantum numbers. Questions based on quantum numbers. The next topic that will be asked, that is questions based on nodes. Calculation of nodes. And the last topic here is psi versus r and psi square versus r. These are the topics from which your questions will be framed when it comes to your atomic structure. And we are going to discuss all of them one by one. We are going to discuss all of them one by one. So are you all ready? Are you all ready, people? Are you all ready? Kirthana, laws of chemical combination, you just have to remember the definitions. There is nothing to teach there. Just remember its definition. That's more than sufficient. All ready, people? Sir, do it fast. I'm already doing fast, guys. We complete mole concept in 1 hour. Do you understand? This mole concept, I take 12 hours to complete this entire chapter. And here we took in only 1 hour. I'll give you breaks in between as well. Don't worry. Breaks will be also given. I need break more than you. Why is that? Because I have throat issues. You have no idea. I'm taking almost 6 tablets every single day for throat. Doctor has prescribed. He has given me steroids for throat. It's in such a bad condition. So I need breaks more than you. So don't worry, breaks will be right in the middle. Chalo, let's get going then. Let's get started. Let's get started with your atomic structure. My dear students, in the atomic structure, the first topic you will be asked. What is that? The first topic will be calculation of the radius of nth Bohr's orbit. Radius of nth Bohr's orbit, Rn. Radius of nth Bohr's orbit. How do I calculate the radius of nth Bohr's orbit? How do I calculate the radius of nth Bohr's orbit? Try to understand what I'll be doing. For example, you are taking an atom. Which is a single electron species, for example. For example, you are taking a single electron species. So that species which contains only 1 electron. Let's say this is the nucleus of the atom. Okay. And this is the electron which is revolving in this particular shell. Let the shell number be n. Right? Let the atomic number of this atom be Z. Let the atomic number of this atom be Z. So first of all, the distance from here to here, I'll be calling as radius. Radius of nth Bohr's orbit. How do I calculate radius of nth Bohr's orbit? There is a formula. Radius of nth Bohr's orbit is nothing but R naught
n square divided by z. A radius of nth Bohr's orbit is equal to r naught n square divided by z. What is z? Atomic number. What is n? Shell number in which electron is revolving. In which electron is revolving. What is this r naught? R naught is a constant whose value is 0.529 angstroms. That's a constant. Now, my dear students, imagine that. Imagine one thing. Let's say the atomic number of this atom is Z1, right? Let's say the radius of this orbit is R1. Radius of this Bohr's orbit is R1. Let's say the shell number is N1. Shell number is N1. For example, there is one more single electron species whose nucleus is this, right? This is the shell number in which electron is revolving. Let the shell number be N2. Let the atomic number of this species be Z2, and let the radius be R2. Let the radius be R2. If I need to compare the radii of these two Bohr's orbits, if I need to compare the radii of both these two Bohr's orbits, how do we do that? I'll say R1 divided by R2 is equal to N1 square divided by N2 square multiplied by Z2 divided by Z1. This is the formula with the help of which you can compare the radii of two Bohr's orbits. Which will be asked? Sir, can we take laptop to exam hall with us? Yes, you can do laptop. You can take laptop. You can take this mobile phone, Chat GPT, right? Gemini, everything. All the reference books. Okay? Okay, do all that. But do one thing, do not take the hall ticket with you. Rest all the things you can take. Yeah? Do not take that admit card, hall ticket, etc. with you. Rest you can take everything. Everything. You can take me also. I can, help you out in chemistry. Yeah? Yeah, correct. You can give me a call at that time. While sitting in the examination, give me a call, yeah? Sir, they are not allowing me inside the examination center. What do I do? Chalo, should we move on? Should we move on? Achha, by the way, tomorrow I am posting a small video on this channel. Complete salt analysis in 10 minutes. Complete salt analysis in 10 minutes. Tomorrow I'll be posting that very, very, very important video. Do watch that. Okay? Chalo, let's move on. Let's move on, people. So this was the radius of nth Bohr's orbit, right? This was the radius of nth Bohr's orbit. Similarly, how do we calculate the velocity of the electron in the nth Bohr's orbit? How do I calculate the velocity of the electron in the nth Bohr's orbit? Again, there's a formula for that. Velocity of the electron in the nth Bohr's orbit, which I call as Vn, is equal to V naught Z divided by N. What is V naught? It's a constant whose value is 2.18 into 10 raised power 6 meter per second. Now, similarly, if I need to compare the velocities of two electrons moving in two different Bohr's orbits, I'll be using the equation V1 divided by V2 is equal to Z1 divided by Z2 multiplied by N2 divided by N1. This is the formula with the help of which you can compare the velocities of two electrons moving in two different orbits. Okay? Similarly, guys, I think this is understood, yeah? I think this is understood. I'm removing this, this understood. Similarly, my dear students, the third thing, that is your time period. I'm not going to derive anything. I'll just give you the result. That's more than sufficient. And I'll show you how to utilize that result. Okay? So I'm marking the heading here as time period. How do we calculate time period of the electron? In the nth Bohr's orbit? time period of electron in the nth Bohr's orbit. The formula to calculate time period of electron in the nth Bohr's orbit, that is Tn is equal to T naught n cube upon z square. T naught n cube upon z square. And my dear students, look at the value of T naught. How much is T naught? 1.5. 1.5 into 10 raised power minus 16. 1.5 into 10 raised power minus 16. So T naught value here is 1.5 into 10 raised power minus 16 seconds. Okay? And if you need to compare the time periods of two electrons moving in two different orbits, you can say T1 by T2 is equal to N1 cube divided by N2 cube multiplied by Z2 square divided by Z1 square. This is the formula with the help of which we can compare the time period of two different electrons moving in two different Bohr's orbits. Am I clear with this? Quick, everyone. Everyone, people. Yeah? Similarly, there is one more thing here. What is that? Total energy of the electron in the nth Bohr's orbit. Total energy of the electron in the nth Bohr's orbit. Remember, the formula is total energy of the electron in the nth Bohr's orbit, that's equal to minus 13.6 Z square divided by N square electron volts. Okay. This is the total energy possessed by the electron in the nth Bohr's orbit. All right. Total energy possessed by the electron in the nth Bohr's orbit. This is the formula which you need to remember. Similarly, kinetic energy of the electron in the nth Bohr's orbit. That's plus times this. Plus 13.6 Z square divided by N square electron volt. And similarly, if they ask you about the potential energy is minus 27.2 Z square upon N square electron volt. Right? Similarly, if they ask you about the frequency of the electron in the nth Bohr's orbit. Frequency of the electron in the nth Bohr's orbit is nothing but that's inverse of time period. So if time period was directly proportional to n cube, inversely proportional to z square, so frequency will be directly proportional to z square, inversely proportional to n cube. Remember this particular point as well. Okay. Now see what kind of questions can be framed here. These are all the derivations and stuff. We have got nothing to do with the derivations. We just have to remember the formulas, right? And we are done. Tell me the answer of this question quick. See, how do we deal with such kind of questions? Calculate the radius ratio of second orbit of He positive and third orbit of Be tri positive. So basically, I am given with He positive on one side. And on another side, I am given with Be tri positive. Tell me their atomic numbers first of all. Hydrogen, helium, atomic number is 2. Hydrogen, helium, lithium, beryllium, atomic number is 4. Right? Here, which orbit they are talking about? They are talking about the second orbit. Here, they are talking about the third orbit. Right? Let the radius here is R1. Let the radius here is R2. You know the formula already. R1 divided by R2 is equal to N1. What is the formula? R0 N square by Z. So N1 square, N2 square multiplied by Z2 divided by Z1. So what is N1 square? 2 ka square, that's 4, divided by N2 square, 3 ka square, that's 9. Z2 is 2. Z2 is how much? Z2 is 4. Z2 is 4 divided by Z1 is 2. So this value comes out to be 16 divided by 9 to is 18. So it is simply 2829. So the radius ratio here is 8:9. Right? I just use the formula. Nothing more, nothing less. R1 by R2 is equal to N1 square divided by N2 square into Z2 divided by Z1. Few minutes back, the formula which I gave you, that's it. So the answer is 8:9. This is the radius ratio. Yeah, this is the radius ratio. I believe this is clear. Tell me what should be the answer of this question. Every one of you in the chats. Tell me in the chats, quick. if you look at this particular question, we are given with hydrogen atom and we are given with Li dye positive. Perfect. Now, atomic number of hydrogen is 1. Atomic number of lithium, hydrogen, helium, lithium, that's 3. Perfectly done. Since they are talking about the first orbit of hydrogen, and the velocity of electron in the first orbit is V, given to me in the question. Now, what is the orbit number which they are mentioning in Li dye positive? They are talking about the third orbit, and let the velocity of electron here is V2. I need to calculate V2. Few minutes back, I gave you the result. V2 divided by V1. Or I can say V1 by V2. I can say V1 divided by V2. Few minutes back, I gave you the formula. V is equal to V naught Z divided by N. So it's V1 by V2 is equal to Z1 divided by Z2 multiplied by N2 divided by N1. This is the formula I'll be using. Simple, right? So it's going to be V1 divided by V2 is equal to V1 divided by V2 is equal to, what was Z1? That was 1. What is the value of Z2? That is 3. What is the value of N2? That is 3. What is the value of N1? That's 1. This gets cancelled. The value is 1 by 1. The value is 1 by 1. So V1 by V2 is equal to 1 by 1. 1 by 1. V1 is already given as V. So do the cross multiple stuff. You'll get V2 value equal to V. This is something you were supposed to calculate. So V2 is equal to V. Perfect. Perfect, people. Now there is something called as, this is important, hydrogen spectrum. There is something called as hydrogen spectrum. My dear students, I believe all of you would be knowing one thing. When the electron makes a transition, from lower energy state to higher energy state, when the electron makes a transition from lower energy state to higher energy state, it absorbs energy, right? It absorbs energy in the form of radiation. And that radiation has got some wavelength as well, correct? And when the electron makes a transition from higher energy state to lower energy state, when the electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiation. It emits energy in the form of radiation. That radiation will be definitely having some wavelength as well. One thing, when the electron makes a transition from lower to higher, it absorbs energy. When electron makes a transition from higher to lower, it emits energy in the form of radiation. Correct? Now try to understand, people, what exactly I'm going to do. Try to understand very clearly. Okay? Just have a look. I'm talking about the hydrogen atom. Let's say this is the ground state of hydrogen. That means N is equal to 1. Let's say this is N is equal to 2 for hydrogen. N is equal to 2. Similarly, let's say this is N is equal to 3 for hydrogen. Similarly, this is, for example, N is equal to 4 for hydrogen. And similarly, guys, for example, this is N is equal to 5 for hydrogen. Similarly, for example, this is N is equal to 6 for hydrogen. And somewhere at the top, here is N is equal to infinite for hydrogen. So this was N is equal to 1. This is N is equal to 2. This is N is equal to 3. N is equal to 4. N is equal to 5. N is equal to 6. This N is equal to infinite. Which atom I'm talking about? Hydrogen atom. Right? Now, my dear students, N is equal to 1 is called as ground state. Right? Ground state. N is equal to 2 is called as first excited state. It's called as first excited state. Or you can call it a second energy state. You can call it a second energy state. You can call it either as second energy state or first excited state. Similarly, this will be second excited state or third energy state. Third energy state, right? Similarly, this will be third excited state, fourth excited state, fifth excited state. Perfect. Now, people, you should know one thing. When the electron makes a transition from higher energy state to shell number 1, when the electron makes a transition from higher energy state to shell number 1, when the electron makes a transition from higher energy state to shell number 1, we get a series of radiations. When the electron makes a transition from higher energy state to shell number 1, we get a series of radiations. Lot of radiations are emitted. Those radiations have got specific wavelength as well. And the series of radiations which we get, series of radiations which we get when the electron makes a transition from higher energy state to shell number 1. This series is what you call as Lyman series. So in Lyman series, the ground state is n is equal to 1. The ground state is n is equal to 1. Similarly, when the electron makes a transition from higher energy state to shell number 2, higher energy state to shell number 2, higher energy state to shell number 2, what do we get? We get a series of radiations. And these series of radiations is what we call as Balmer series. Similarly, when the electron makes a transition from higher energy state to shell number 3, when the electron makes a transition from higher energy state to shell number 3, again, what do we get? A series of radiation. What do we call this as? Combustion series. Lyman-Balmer combustion. Similarly, higher energy state to shell number 4. Higher energy state to shell number 4. Bracket series. Okay. Similarly, higher to shell number 5. Higher energy state to shell number 5. Series of radiations. You call this as Fund series. So you've got Lyman series, you've got Balmer, you've got Combustion, you've got bracket, you've got Fund. Ground state of Lyman is 1. Ground state of Balmer is 2. Ground state of Combustion is 3. Ground state here is 4. Ground state here is 5. The first question that will be asked to you, what is that? Lyman series falls in which region? Lyman series falls in which region? It falls in ultraviolet region. It falls in ultraviolet region. Balmer series falls in visible region, visible spectrum. Combustion falls in infrared. Bracket falls in infrared. Fund falls in infrared. This is the first question which will be asked. Which series falls in which region? Number 1. Number 2, guys. Number 2. The second thing that will be asked here. What is that? What is that? Have a look. They'll ask you, when the electron makes a transition from higher energy state to lower energy state, when the electron makes a transition from higher energy state to lower energy state, how many total number of spectral lines will be observed? How many total spectral lines will be produced? Remember, there's a formula. Total spectral lines is equal to N2 minus N1 into N2 minus N1 plus 1 divided by 2. The total number of spectral lines which are produced, the total number of spectral lines which are observed when the electron makes a transition from higher energy state to lower energy state. That is N2 minus N1 into N2 minus N1 plus 1 divided by 2. What is N2? What is N1? N1 is basically your lower energy state and N2 is basically your higher energy state. It is higher energy state. Now you need to understand few important things here, guys. You need to understand few important things here. Understand properly. This particular formula, it is valid for large number of atoms. Do remember this as well. This formula is valid for large number of atoms. Now, one more formula I'm giving, then I'll let you know how do we use this formula. Number of spectral lines falling in a particular series. Number of spectral lines falling into a particular series. That's equal to N2 minus ground state of the series. N2 minus ground state of the series. Now you must be thinking, what am I talking about? Where do we use all this? Where do we use all this? Have a look. For example, they are giving you the question. The electron is making a transition from 6 to 1. The electron is making a transition from 6 to 1. Tell us how many total spectral lines will be observed, right? Tell us out of the total spectral lines, how many series will fall into Lyman category. Tell us out of total spectral lines, how many lines will fall into Balmer category, how many lines will fall into Combustion category, etc., etc. This can be the question asked. Now, how do we deal with such kind of a question? My dear students, lower energy state is N1, higher energy state is N2, total spectral lines is N2 minus N1 into N2 minus N1 plus 1 divided by 2. The value comes or be, this is cancelled, 6, 5, 30, 30 by 2 is 15. So total 15 spectral lines are produced. Total 15 spectral lines are observed. Now, since total 15 spectral lines are observed, how many will fall into Lyman category? Out of 15, how many will fall into Lyman category? N2, higher energy state is 6, minus. Ground state of Lyman is 1. So out of 15, 5 will fall into Lyman. How many will fall into Balmer? N2, higher energy state, that is 6, minus ground state of Balmer is 2, 4. How many will fall into Combustion? Higher energy state minus ground state of Combustion is 3, right? Bracket will be 6 minus 4, that is 2. Fund will be 6 minus 5, that is 1, right? So if you add all this, 5 plus 4 plus 3 plus 2 plus 1, it comes out to be 15 only. So this sort of a question can be asked. Is it clear, guys? Is anyone, doing something wrong in the chats? Sir, it is Arnold George. Where is this Arnold George? Wait, I'll block him. Is he actually saying some wrong stuff to people? Where is he? Where is he? Where is he? Hi, Arnold, where are you? Do you know who Arnold is, first of all? You have kept the name Arnold? I cannot see any Arnold in the chats. Just a second, guys, just a second. Where are his chats? Okay, if he comes again, let me know, okay? I'll block him right here. I don't have to call anybody to block. I have got everything, channel access and everything here with me. You don't worry about that. Okay? So if he does the same, do let me know in the chats. Sir, what about the equation n into n minus 1 by 2? That equation is only valid when the ground state is 1. When the ground state is 1. Okay, one more question of this pattern. One more question of this pattern. One more question of this pattern. Just a second, just a second. Okay. Look at the question, guys. Look at the question. Electron in the hydrogen atom jumps from some higher level up to third energy level. Some higher level, let the higher level be N2, to the third energy level. To the third energy level. If 6 spectral lines are possible, so total spectral lines are 6. Find the initial position of electron. Find the initial position of electron. Just use the formula. Total spectral lines is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by what? Divided by 2. So total spectral lines are 6. 6 into 2 is 12. Right? 6 into 2 is 12 is equal to N2 minus N1. N2 minus N1 into N2 minus N1 plus 1. Correct? So 12 is equal to N2 minus 3. This will be N2 minus 2. Perfect. Right, guys? So what should be the value of N2 here? Can you tell me in the chats? You have to use your common sense a bit. You have to use common sense here, guys. Common sense, quick. What do you think will be the value of N2? I'm asking you. See, N2 has to be 6. So that 6 minus 3 is 3. 6 minus 2 is 4. Then only 4 into 3 comes out to be 12. So N2 value from here is equal to 6. So the initial position is basically the 6th energy state. Got it? Tell me the answer of this question. A lot of students will mark it incorrectly. Read it carefully and then solve it. Read it carefully and then solve it. In hydrogen-like atom, electron makes a transition from 4th excited state. 4th excited state means 5th energy state. 4th excited state means 5th energy state. Up to 2nd state. This is not second excited state. This is 2nd energy state. This is 2nd energy state. This was 4th excited state. That means N2 is equal to 5. That means 5. This is second state, second energy state. Second energy state. So the electron is making a transition from 5 to 2. So first of all, tell me total spectral lines. N2 minus N1. Similarly, N2 minus N1, and this will be N2 minus N1 plus 1. Divide by what? Divide by 2. So I would say total spectral lines will be 5 minus 2 is 3 multiplied by 5 minus 2 is 3 plus 5 minus 2 is 3 plus 1, 4 divided by 2. So total spectral lines are 6. Total spectral lines are 6. Okay. Now, out of these 6, how many will belong to Balmer and how many will belong to Paschen? If I talk about out of these 6, how many will belong to Balmer? N2 is how much? 5 minus ground state of Balmer is 2. So 5 minus 2 is 3, right? So number of lines in Balmer is 3. Similarly, number of lines in Paschen is N2 minus ground state of Paschen. Lyman, Balmer, Paschen. So 3. 5 minus 3 is 2. So there will be 2 spectral lines in Paschen series as well. Got it? So all are correct except one. All are correct except one. I believe this is also clear to everyone. And if this is clear, then there is one thing which I need to show right here. What is that? Let's have a look. There is a formula called as Rydberg's formula. There is a formula called as Rydberg's formula. From this particular formula, questions are frequently asked. Now, what is this Rydberg's formula? Rydberg's formula is nothing but it is 1 divided by lambda is equal to R Z square 1 upon N1 square minus 1 upon N2 square. This is your Rydberg's formula. Where do we use this? For example, there's a question. When the electron makes a transition from 5 to 1, when the electron makes a transition from 5 to 1, energy will be emitted in the form of radiation. Now they'll ask you, what is the wavelength of that radiation emitted? What is the wavelength of the radiation emitted when the electron makes a transition from higher energy state to lower energy state? That can be the question. Right? What is the wavelength of the radiation emitted when the electron makes a transition from higher energy state to lower energy state? That can be the question asked. For that purpose, you have to use this formula. Now understand, guys, what exactly I'm going to say. For example, when you talk about this particular hydrogen spectrum, let me tell you, in Lyman series, this is called as H alpha line. This is called as H beta line of Lyman series. Similarly, this is called as H gamma line of Lyman series. Or you can call this as first line of Lyman series. You can call it as second line of Lyman series. You can call it as third line of Lyman series. Similarly, this is the first line of Balmer series, second line of Balmer, third line of Balmer, or you can call it H alpha of Balmer, H beta of Balmer, H gamma of Balmer. This is first line of Paschen, second line, third line, first, second, third, etc., etc. Similarly, H alpha, H beta, H gamma. Now, what is the point here? What is the point here? My dear students, if I try to analyze the Lyman series, the first question that will be asked to me, what is that? They'll ask me to calculate the series limit. In Lyman. Now you must be thinking, what is series limit? Series limit is nothing but minimum wavelength emitted in Lyman series. Lambda minimum is what I call a series limit. Minimum wavelength emitted is called as series limit. You tell me one thing. Delta E is inversely proportional to lambda. For lambda to be minimum, energy gap has to be maximum. For lambda to be minimum, energy gap has to be maximum. You know it. For lambda to be minimum, energy gap has to be maximum. Now I have to calculate lambda minimum in Lyman. For lambda to be minimum in Lyman, energy gap has to be maximum. I'm talking about Lyman series. For wavelength emitted to be minimum, energy gap has to be maximum. In Lyman, when can be the energy gap maximum? Energy gap is maximum in Lyman when the electron makes a transition from infinity to 1. You understand? I have to calculate series limit in Lyman series. That means I have to calculate shortest wavelength. Shortest wavelength is possible when the energy gap is maximum. Maximum energy gap in Lyman is when the electron makes a transition from infinity to 1. So this is the lowest energy state. Lower energy state, N1. Higher energy state, N2. Calculate the wavelength emitted. Use the Rydberg's formula. 1 divided by lambda minimum is equal to R Z square multiplied by 1 upon n1 square minus 1 upon n2 square. Correct? Remember, my dear students, 1 by R value you can remember as 911.5 angstroms. 1 by R value you can remember as 911.5 angstroms. Now, I can say 1 divided by lambda minimum is equal to R. Z value for hydrogen is 1. 1 upon n1 square. 1 upon n1 square. So it's 1 only. Minus 1 upon infinity square. Infinity square is infinity only. So I'll get the equation like this. 1 divided by lambda minimum is equal to R. So you can take the reciprocal. I can say lambda minimum is equal to 1 by R. And 1 by R is nothing but 911.5 angstroms. Okay. So this is the shortest wavelength emitted in Lyman series. Similarly, they can ask you, calculate the longest wavelength. Calculate the longest wavelength in Lyman series. Longest wavelength in Lyman series. Lambda max. So tell me one thing. When can be lambda value maximum? Lambda value can be maximum if delta E, energy gap, is minimum. When is the energy gap minimum in Lyman? Energy gap is minimum in Lyman when the electron makes a transition from 2 to 1. When the electron makes a transition from 2 to 1. So here, I'll assume the electron is going from 2 to 1. Lower energy state is N1. Higher energy state is N2. The formula is 1 divided by lambda is equal to R. Z value is 1. 1 upon N1 square minus 1 upon N2 square. So it is 1 by lambda max. 1 divided by lambda max is equal to R. This will be 1 by 4. 4 minus 1 is 3. 3 divided by 4. Or you can say, if you take the reciprocal, you can say lambda maximum is equal to 4 divided by 3 into 1 by R. So 4 by 3 you can write as such. 1 by R is nothing but 911.5 angstroms. Solve it and you'll get the answer. This is the maximum wavelength emitted. Right? After this chapter, I'll give you a break. Don't worry. I believe this is clear. Similarly, guys, you tell me one thing. I'm asking a question. Calculate the series limit in Balmer. Series limit in Balmer. What does that mean? Shortest wavelength in Balmer. Shortest wavelength in Balmer. That means energy gap has to be maximum in Balmer. In Balmer, when can be the energy gap maximum? When the electron makes a transition from infinity to 2. Yes? Do you understand? Do you understand, people? Say yes or no in the chats. I'm asking you. It's a Rutherford alpha particle. That is not asked in chemistry atomic structure. That is asked in your modern physics. Not here. Guys, do you understand? Did you understand what I said? Honestly? I think yes. Okay. Okay. If I am clear, can you tell me, will you be in a position to solve these questions? H alpha. Alpha means first line. First line means in the Balmer. First line of Balmer. H alpha means first line of Balmer. First line of Balmer. In first line of Balmer, the electron makes a transition from 3 to 2. 3 to 2. So you can easily calculate lambda with the help of Rydberg's formula. Right? With the help of Rydberg's formula. Look here. Series limit of Lyman, we have already calculated. H beta of partition. H beta means second line. Second line of partition. Lyman-Balmer partition. In partition, first line will be from 4 to 3. Second line will be from 5 to 3. So here the transition is from 5 to 3. Now, you got N1, you got N2. You can use the Rydberg's formula and you can get the lambda here. Yes? Am I clear? Am I clear, people? Am I clear? Say it quickly. Yes? Perfect. All right, one more question. Look at this question, guys. Look at this question, quick. Hydrogen atom in ground state. Hydrogen atom in ground state. So hydrogen atom is in ground state. Is excited by the monochromatic radiation of wavelength lambda. So it's going to higher energy state, for example, N2. On coming back to ground state, 15 different spectral lines are observed. Total spectral lines observed are 15. What do we have to calculate? Lambda. We have to calculate lambda. So first of all, understand people. Total spectral lines is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. Total spectral lines observed are 15, correct? Is equal to N2 I'm writing as such, N1 is 1. N2 I'm writing as such, N1 value is 1 plus 1 divided by 2, correct? So 15 twos are 30 is equal to N2 minus N1. So this got cancelled, the value is N2, correct? Now, when is this equation valid? Sorry, this N2 minus 1. This N2 minus 1 here. Okay, when is this equation valid? I would say N2 value should be 6. If N2 is 6, then only 6 minus 1 comes out to be 5, then only 6 5s comes out to be 30. So N2 has to be 6. N2 has to be 6. So I got to know that electron is making a transition from 6 to 1. I got to know that the electron is making a transition from 6 to 1. So this is your lower energy state, this is your higher energy state. Now they are asking us when the electron makes a transition from 6 to 1, calculate the wavelength emitted. So I'll use the Rydberg's formula. 1 by lambda is equal to R. Z value for hydrogen is 1. 1 upon N1 square minus 1 upon N2 square. 6 ka square is 36, right? So it's going to be 1 by lambda is equal to R. This will be 36 minus 1, that is 35 divided by 36. If you take the reciprocal, it's going to be 36 divided by 35 into 1 by R. 1 by R is 911.5 angstroms. Just a matter of calculation. Get the lambda. That's it. Got it? I believe this is clear. Look at this question, guys. Look at this question. This question I'm giving you as the homework. You can do this question on your own. I believe so. You can do this question on your own. Yeah? This question I'm keeping as the homework. I hope I'm clear with all the stuff till now. I hope I'm clear with all the stuff till now, my dear students. Okay? My dear students, now comes one more thing, that is Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. You know already this. It is impossible to determine the exact position and the momentum of the microscopic particle, right, simultaneously with 100% accuracy. Correct? Now, what do we have to do here in Heisenberg? My dear students, in Heisenberg, either you'll be asked a question based on statement. What is the statement of Heisenberg? According to Heisenberg's principle, it is impossible to determine the exact position and the exact momentum of a microscopic particle like electron simultaneously with 100% accuracy. Perfect. Second thing is this equation. Delta x dot delta p is greater or equal to h upon 4 pi. We should know how to use this equation. That's the point. Delta x dot delta p is greater or equal to h upon 4 pi. What is delta x here? Delta x is what we call as error or uncertainty in position. Similarly, delta p is what we call as error or uncertainty in momentum. Similarly, delta v is the error or uncertainty in velocity. Perfect. Now, you just have to remember these results first of all. Delta x dot delta p is greater or equal to h upon 4 pi. Right? Now, guys, since you know, momentum is nothing but mass into velocity. So, if there is error in momentum, that means that error will be due to in the error in velocity. So, delta p is nothing but m delta v. So, instead of delta p, you can write m delta v. Delta v you can keep here, m you can take in the denominator. So, you can remove it like this as well. So, delta x dot delta p is greater or equal to h upon 4 pi. Delta x dot delta v is greater or equal to h upon 4 pi m. Now, what kind of question can be formed? This kind of the question can be formed. This kind of the question can be framed here. The question is, if the error in the velocity and the position, if the error in the velocity and position are same, what will be the error in the de Broglie's wavelength? What will be the error in the de Broglie's wavelength? What will be the error in the de Broglie's wavelength? What will be the error in the de Broglie's wavelength? How do you solve this question? Since you know your de Broglie's wavelength lambda is equal to h upon mv. Lambda is equal to h upon mv. So delta lambda will be equal to h upon m delta v first of all. Delta lambda will be equal to h upon m delta v. So technically I have to calculate delta v. Now, you know, delta x dot delta v is greater or equal to h upon 4 pi m. I'm using the equal sign. Now, delta x, delta v are equal. So, I can say delta v ka square is equal to h upon 4 pi m. So, I can say delta v is equal to under root of h upon 4 pi m. So, you got delta v. If you got delta v, my dear students, what do you have to calculate? Delta lambda. What do you have to calculate? Delta lambda. So, I'll say delta lambda is equal to h upon m, and delta v you got as h upon 4 pi m. H upon 4 pi m. Right? Just the matter of calculation. Just the matter of calculation. Just the matter of calculation. See, h I'm keeping as such. If I take m inside the root, it becomes m square. 1m gets cancelled. So it's under root of hm divided by 4 pi. Now, if I do one more thing, if I take root entirely, this h becomes h square. So 1h gets cancelled. So it's h, and this is 4 pi divided by, and in the denominator, it's going to be m. So this is the final answer of the question. When you do a bit of calculation, this is going to be the final answer of the question. Yes? Did you understand, people? How do we deal with such kind of the question? Quickly in the chats. Quickly in the chats. For example, if I write the question like this, if the error in position and error in momentum is equal, calculate error in velocity. If the error in position and momentum are equal, if the error in position and momentum are equal, calculate the error in velocity. Now, from this, you'll understand the earlier question as well. So, first of all, error in position and momentum are equal. You know, delta x dot delta p is greater or equal to h upon 4 pi. Correct? Yes? Right, guys? So, can I say, if delta x, delta p are equal, so it's going to be delta p ka square is equal to h upon 4 pi. Clear till here? So, delta p will be equal to under root of h upon 4 pi. Now, you know, delta p is nothing but m delta v. So, m delta v is equal to under root of h upon 4 pi. So, I can say delta v is equal to 1 upon m. Delta v is equal to 1 upon m under root of h upon 4 pi. If I take 2 outside, it's going to be under root of h upon pi. This is the error in velocity. Got it? I hope this is again clear, guys. Yes? Sir, do calculation of the earlier question again. Is the calculation difficult? See, till here I believe it's clear. Now I put the value of delta v here. Okay, what did I do? I took the root common in the denominator. If I take the root common in the denominator, it becomes m square. M square here. M square and m gets cancelled. So it becomes hm by 4 pi. Now I take the root entirely common. If I take root entirely common, this h becomes h square. So h square and h gets cancelled. So I'll be only left with h divided by. This was 4 pi in the denominator, comes up. So 4 pi comes up. And this m was already in the denominator. It's a basic calculation, guys. There is nothing wrong in that. Okay, you can do this after some time. I believe I'm clear with this. I believe I'm clear with this. I believe I'm clear with this. Now, from quantum numbers, there is a one type of question that's asked. Which of the following quantum numbers is not permissible? Which of the following quantum numbers is not possible? Which of the following set of quantum numbers is permissible? Like that questions are asked. Let me first of all tell you, we have got 4 quantum numbers, you know that. One is called as principal quantum number. One is called as principal quantum number, which we represent with n. One is called as azimuthal quantum number. Azimuthal quantum number, which we represent with L. One is called as magnetic quantum number. Magnetic quantum number, which we represent with N. M. One is called as spin quantum number. Spin quantum number, which we represent with S. 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 These are the 4 quantum numbers. My dear students, the first thing that can be asked, which of the following quantum number is not the outcome of Schrodinger's wave equation? This is not the outcome of Schrodinger's wave equation. This is not the outcome of Schrodinger's wave equation. Remember that directly. This is not the outcome of Schrodinger's wave equation. Now, my dear students, understand few things. Understand few things. This principal quantum number, it gives me the idea about the shell number in which electron is present. Shell number. You know one thing. You know one thing. Your shells are made of subshells. Subshells contain orbitals. You know that? Shells contain subshells. Subshells contain orbitals. That's something we study in 7th, 8th, 9th class, right? Now, first of all, this principal quantum number, it gives me the idea about the shell number in which the electron is present. Azimuthal quantum number, whose value is from 0 to n minus 1 as per the formula. It gives me the idea about the subshell in which electron will be. And this magnetic quantum number, whose value is from minus L to plus L, minus L to plus L, it gives me the information about the orbital in which the electron will be. And spin, it gives me the idea about whether the electron is going with clockwise spin or anti-clockwise spin. So S can have two values, plus 1 by 2 or minus 1 by 2. Plus 1 by 2 means clockwise spin, minus 1 by 2 means anti-clockwise spin. Now try to understand what exactly I'm going to say. Try to understand, guys. Simple thing I'm going to say. The question will be asked, you'll be given with some values. Let's say this is N. Let's say this is L. Let's say this is M. Let's say this is S. Okay. Let's say one of the options says that N is equal to 5, L is equal to 4, M is equal to 3, S is equal to plus 1 by 2. The second is, for example, saying this is 5. Okay. This is 5. This is minus 5. This is minus 1 by 2. Let's say the third option says this is 4. This is 3. Right. This is, for example, minus 4. This is plus 1 by 2. Let's say the last option is saying this is 3. This is 2. This is minus 2, this is 0. You have to check which set of quantum numbers are possible, which set of quantum numbers are not possible. This is the type of the question that will be asked. Can you check it out? I already told you one thing. See, in the first option, N is equal to 5. If N is 5, L will be from 0 to N minus 1. 0 to 5 minus 1. That means 0 to 4. 0 to 4. So L can be 0, 1, 2, 3, 4. L can be 0 to 4. 0, 1, 2, 3, 4. So L is 4 here, correct. M value is from minus L to plus L. What is L here? 4. So M will be minus 4 to plus 4. So minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. So M comes in that, correct. S can have two values, plus 1 by 2, minus 1 by 2. So this first set of quantum numbers is possible. This is correct. A is possible. Look at the next one. N value is 5. N value is 5. L value is 5. L is from 0 to n minus 1. So 0 to 5 minus 1, 0 to 4. It can be 0, 1, 2, 3, 4. But here they mentioned 5. So not possible. Cancel here only. Not possible. Right? Similarly, the next one. N is 4. N is 4. L is 3. So 0 to 4 minus 1. 0 to 3. Correct? M is minus 4. M is from minus L to plus L. So minus 3 to plus 3. Minus 3 to plus 3. But here they mentioned minus 4. Not possible. S can only have two values, plus 1 by 2, minus 1 by 2. Here they have given 0, so not possible. Got it? Got it, people? Am I clear? Everyone in the chats, am I clear? Quickly, people, quickly in the chats. Am I clear with all this? Yes or no in the chats? And this principal quantum number, it gives me the information about the size and energy of the shell. Okay? This gives me the information about size and energy of the cell. This magnetic quantum number, it gives me the information about the orientation. It gives me the information about orientation. Remember that. There is one more thing that can be asked here. What is that? They can ask you about the orbital angular momentum. There is a formula to calculate orbital angular momentum, guys. Under root of L into L plus 1 h upon 2 pi. This is the formula. This is the formula. Now remember one thing first of all. In case of S subshell, the value of L is 0. In case of P subshell, the value of L is 1. In case of D subshell, the value of L is 2. In case of F subshell, the value of L is 3. Remember these values first of all. Okay. Now, for example, you are taking certain orbitals, 1s, 2s, 2p, for example, 3p, 3d, right? 4f. You have to calculate their orbital angular momentums. Orbital angular momentums of all of these. For S subshell, the value of L is 0. If L is 0, this entire term becomes 0. So orbital angular momentum here is 0. Again, this is S. For S, the value of L is 0. For S, the value of L is 0. If L is 0, this entire term becomes 0. So orbital angular momentum is 0. For P, the value of L is 1. So orbital angular momentum will be equal to under root of L into L plus 1. So 1 into 1 plus 1 multiplied by h upon 2 pi. So it will be finally h upon root of 2 pi. Okay. The next one. Talk about P. Talk about P. For P, the value of L is 1. If L is 1, put the value of L as 1 here. So orbital angular momentum in this particular case will be again h upon root 2 pi only. This is 3D. Put the value of N. N value will be 2. L. L value here will be 2. If L is 2, orbital angular momentum will be equal to under root of 2 into 2 plus 1 multiplied by h upon 2 pi. So 2 plus 1 is 3. 3 2s are 6. So it's going to be root 6 into h upon 2 pi. Similarly, 4f, SPDF, L value is 3. If L is 3, orbital angular momentum will be equal to under root of L into L plus 1 multiplied by h upon 2 pi. So 3 plus 1, 4. 4, 3, 12. So it's a root of 12 h upon 2 pi. These questions are directly asked, guys. Right? These questions are directly asked in the exam. Am I clear till here? Everyone? Am I clear till here, people? Everyone in the chats? Everyone in the chats? Yes? Now. There is one more thing, guys, which I would want to share with you. What is that? Understand. Sometimes they'll ask you the question about nodes. Calculate the nodes. Calculate the nodes. Few formulas you have to remember first of all. This is again important. Calculation of nodes. My dear students, how do I calculate the total number of nodes first of all? Total nodes are calculated as n minus 1. This is the formula to calculate total nodes. This is the formula to calculate total nodes. Similarly, nodes are of two types. One is called as angular node. Angular node. Angular node is given by the value of L. The second node is called as spherical or radial node, which is equal to n minus L minus 1. This is the formula box which you have to remember, and you are done. And you are done. And you are done. Yes? Now, people, for example, I'm taking 3s here. I'm taking 3s here. For example, I'm taking 3p here. For example, I'm taking 3d here. I want to calculate total number of nodes, radial nodes, spherical nodes, etc., etc. Okay? Okay? Understand. What is the value of n here, first of all? N value is 3. For S subshell, the value of L is 0. So total number of nodes will be n minus 1. 3 minus 1, that is 2. Angular nodes will be the value of L, that is 0. Spherical nodes is n minus L minus 1, that is 2. Understood? Anything can be asked. Okay. 3p. What is the value of n? N value is 3. In case of p, the value of L is 1. Total number of nodes, n minus 1. 3 minus 1 is 2. Right? Angular nodes, value of L, that is 1. Spherical nodes, n minus L minus 1, the value comes out to be 1. 3D, n value is 3. L value for D is 2. Total number of nodes, n minus 1. Angular nodes, the value of L. Spherical nodes, n minus L minus 1, 0. Got it?
Got it, people? This can be asked too. This can be asked too. Yeah? This can be asked too. Tell me once in the chats if this is clear, people. Every one of you in the chats. In the chats, in the chats. Everyone means everyone. Everyone means everyone. Is this particular point also clear? Yeah? Sir, equivalent mass. Equivalent mass, I'll be discussing in redox. Just wait. Is this concept clear? Question, short question will be asked from this. Short question. Asha, one more thing. They will ask you about the psi versus R graph. Or they can ask you about psi square versus R. And they will ask it for 1s and 2s. Because in your syllabus, only 1s and 2s is mentioned. P, etc., is not mentioned. 1s and 2s is mentioned in the syllabus. Just remember these graphs directly. I'm giving them to you. Have a look. If I talk about 1s, for 1s, for example, you have to plot a graph between psi versus R. Okay? All the psi versus R graphs, and psi square versus R graphs for s orbital, for s subshell, they start from the top. The graph is like this. Here also the graph is like this. Okay? This is 1s. Psi versus R, psi square versus R. Since it is not touching the R axis. Why? Because if it touches the R axis, at that point, psi square becomes 0. Psi square 0 means node. Probability of finding electron 0. Psi square is node. Psi square 0 is node. But we know in case of 1s, there will be no node. There is 0 node. If you check n minus 1, 1 minus 1, 0, there is 0 node. So it's not going to cut this R axis. Right? Similarly, for 2s, they'll also ask. And for 2s, what will they ask? They'll ask you about psi versus R and psi square versus R for 2s. Now tell me one thing. 2s, total number of nodes will be n minus 1. 2 minus 1 is 1. So the graph is going to cut the R axis at one point. The graph starts from the top. It's going to come like this. Right? Here is the node. Now, psi square versus R. Start the graph from here to here. Same. Now, remove this part. Take its reflection along x-axis like this. This is the graph. And this point represents the node. So this is psi versus R, psi square versus R. For 2s, this is psi versus R, psi square versus R. For 1s. Remember these two graphs as well. Okay? Got it? Got it, people? Got it? Got it? Everyone in the chats once. Okay, one more thing, guys. Someone was telling me, give us the idea about the subshells and orbitals. Let me give you the idea about subshells and orbitals. With that, we'll take a break. A lunch break, proper lunch break. Don't worry, guys. I'm here. I'm going to give you the break also. Should I cancel the class? You want me to do that? Guys, I'm telling you, whatever concepts I'm teaching you, your paper is going to come from these concepts. You have not studied the entire year. Okay? At least do something in these last 15 days so that you can shoot up your ranks. Okay? Even I am tired. I have been continuously talking, shouting. My throat is also not well. I'm getting nothing out of this session. Okay? Still I'm teaching. If I'm doing that, you can do that too, right? At least it's going to be you who has to give the exam, not me. Correct? So be patient, right? Utilize these 15 days in the proper direction. At least so that you won't have that regret. Okay, what if I studied in the last 15 days? What if I did this in the last 15 days? Okay? Please and please. Be patient. And I'm telling you, your majority of the questions from the chapters which I'll be teaching you today will be from this particular session only. I won't say directly the questions will be asked. Direct, indirect questions will be asked from these topics only. I promise to you. Okay? Be patient. Okay. Now see guys, understand one more thing. If for example, n value is equal to 1, if n is equal to 1, n represents shell number. So the electron is present in the first shell. The electron is present in the first shell. Electron is present in the first shell, right? First shell is called as K shell. You know it already, right? First shell is called as K shell. Now electron is no doubt present in first shell. But in which subshell? In which subshell electron is present? Subshell idea, azimuthal quantum number gives me. Azimuthal quantum number L is from 0 to n minus 1. 0 to 1 minus 1, that is 0. So L is equal to 0. Remember, every value of L represents a subshell. Every value of L represents a subshell. I got one value of L. I got one value of L. And that one value of L came out to be 0. So that means in this first shell, there will be only one subshell. One subshell. That's called as S subshell. That's called as S subshell. So electron is present in K shell. In the K shell, it is present in S subshell of the K shell. Now, in which orbital? Orbital information is given by M. M is from minus L to plus L. So M is 0 only. And every value of M represents an orbital. That means in this S subshell, there is only one orbital, which is called as S orbital. So electron is present in S orbital of S subshell of K shell. Do you understand? Now, for example, if n is equal to 2, n is equal to 2, that means electron is present in second shell. Second is called as L. Electron is present in second shell. What are the L values? What are the L values? 0 to n minus 1. 0 to 2 minus 1. So 0 to 2 minus 1 means 0 and 1. So L can be 0, L can be 1. L is equal to 0 means S subshell. L is equal to 1 means P subshell. That means in your second shell, there are two subshells, S subshell and P subshell. Now, in case of S subshell, what will be the M value? M is from minus L to plus L, so M is 0. Here, M is from minus L to plus L, so minus L to plus L, minus 1, 0, plus 1. Every value of M represents an orbital. So this is called as S orbital. S subshell contains S orbital. And here, your P subshell contains 3 orbitals. These are 3 P values, that means 3 P orbitals. One is called as Px, one is called as Py, one is called as Pz. So in your second shell, how many total orbitals are there? In your second shell, there are 3 plus 1, total 4 orbitals, out of which 1 is S and 3 are P. Understood? Let me give you one more example. For example, n is equal to 3. N is equal to 3. That means KLM shell. This is the third shell. Third shell. L value. L is from 0 to n minus 1. 0 to 3 minus 1. So 0 to 2. It is 0. It can be 1. It can be 2. Now L is equal to 0. Every value of L represents a subshell. L is equal to 0 is called as S subshell. L is equal to 1 is called as P subshell. L is equal to 2 is called as D subshell, right? D subshell. Correct? Now talk about the M values. Here the M value will be from minus L to plus L. So M is equal to 0. Here M is equal to from minus L to plus L, minus 1 to plus 1. So minus 1, 0, plus 1. Here M. L is equal to 2. Minus 2 plus 2. So minus 2, minus 1, 0, plus 1, plus 2. Every value of M represents an orbital. This is your S orbital. These are your 3 P orbitals. These are your 3 P orbitals. One is called as Px. One is called as Py. One is called as Pz. These are your 5 D orbitals. These are your 5 D orbitals. One is called as dxy. One is called as dyz. One is called as dzx. One is called as dx square minus y square. One is called as dz square. These are your 5 D orbitals. Now, if I ask you, in the shell number 3, how many total orbitals are there? 5 plus 3, 8 plus 1, 9. So in shell number 3, 9 orbitals. In shell number 2, 4 orbitals. So can I say total number of orbitals? Total number of orbitals in a shell is equal to n square. Total number of orbitals in a shell is equal to n square. And every orbital accommodates maximum of 2 electrons. Every orbital accommodates maximum of 2 electrons. So total number of electrons which can be accommodated in a shell, that's equal to 2n square. Okay, 2n square. Got it? Now people, now. How do I calculate the spin magnetic moment? One was your orbital angular momentum. One is called a spin magnetic moment.
spin magnetic moment. Spin magnetic moment is calculated as under root of n into n plus 2 Bohr magnetrons. And n represents the number of unpaired electrons. The number of unpaired electrons. Now guys, for example, have a look now. For example, Fe die positive. If you talk about iron, what is the outermost configuration of iron? It is 3d6 4s2. But it is iron die positive, so take 2 electrons out. So it is 4s0. Now, how do you represent this 3d6? 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, and 6. So how many unpaired electrons do you see? 4. So n value is 4. If n is equal to 4, what is the magnetic moment? Under root of n into n plus 2. 4 plus 2 is 6. 6 4 is 24. Root of 24, which will be 4.9 something. 4.9 something Bohr magnetron. Right? Similarly, for example, you have got Mn die positive. Mn die positive. Calculated spin magnetic moment. Manganese. Manganese is 3d5 4s2. But it's manganese die positive. So take 2 electrons out. When you take 2 electrons out, it becomes 3d5 configuration. 1, 2, 3, 4, 5. 3d5. 1, 2, 3, 4, 5. 3d5 configuration. N value here is 5. N value here is 5. If n is 5, your magnetic moment is equal to under root of n into n plus 2. So 5 plus 2 is 7. 7 5s are 35. So root of 35. Root of 35 will be 5.9 something. 5.9 Bohr magnetrons. Similarly, you can check all the ones. Actually, one thing guys. Remember the configuration of chromium. It is, chromium has got exceptional configuration. It is 3d5 4s1. Right? Similarly, remember the configuration of copper. Copper is 3d10 4s1. And why is this configuration? Why? Because here you get half-filled configuration. And half-filled configurations are more stable. Half-filled configurations are more stable. Here you get completely filled configuration. And completely filled configurations are also more stable. That's why these are their actual electronic configurations. Otherwise, their expected electronic configuration is different. But these are their actual electronic configurations. Because here chromium gets half-filled configuration. Right? And here copper gets fully filled configuration, which is more stable. Extra stability. Perfect. So with this, we are done with your atomic structure as well. Okay. See, look at this question. This is something which you know now. The correct ground state electronic configuration of chromium, 3d5 4s1. Where is that? 3d5 4s1. Okay. Tell me the answer of this one. Which one of the following has maximum number of unpaired electrons? Magnesium die positive. Magnesium has got 2 electrons in the outermost shell. So magnesium die positive, 0 unpaired. Scandium, titanium. It is 3d2 4s2. 3d2 4s2. But this is titanium tri-positive. Take 3 electrons out. 2 from here, 1 from here. It becomes 3d1 configuration. 3d1. So unpaired electron is 1. Vanadium. Scandium, titanium, vanadium. It is 3d3 4s2. But it's vanadium tri-positive. Take 3 electrons out. 2 from here, 1 from here. It becomes 3d2 configuration. If it is 3d2, that means unpaired electrons are 2. Fe die positive. Few minutes back only we saw. Fe die positive is 3d6, right? So there are 4 unpaired electrons. So more unpaired electrons are present in Fe die positive. Yes? I believe this is clear. This question you are going to mark wrong. This question you are going to mark wrong. Tell me, what is the answer? What is the answer? Node is nothing. It is the region around the nucleus where the probability of finding the electron is 0. Chi-square value is 0. A p orbital can accommodate normally what a student thinks when he hears about p, he thinks this is your p. It contains 3 orbitals. So every orbital will have 2 electrons. So he will go with 6 electrons, right? But my dear students, it's p subshell. P subshell has got 3 orbitals. They are asking about p orbital. They are asking about one of the p orbital. One of the p orbital can accommodate an orbital can accommodate maximum of 2 electrons. That too with opposite spin. Okay? Be careful with these sort of small questions where students do mistake. Okay, this was your NEET 2019 question. NEET 2019 question. You have to arrange them on the basis of their energy, right? There is a rule called as Bohr-Bary's rule. there's a rule called as Bohr-Bury's rule. You call it as N plus L rule as well. Remember, more the value of N plus L, more the value of N plus L, more the energy. Now, if N plus L value is same for two subshells, if N plus L value is same, then remember, more the N value, more the energy. This is something which you have to remember, and you are sorted. This is your Bohr-Bury's rule. Have a look now. Have a look. Try to understand. Try to understand. N value is 5. Okay, let me write all of them. This is 5F. This is 6P. Then you are given with 5P. Then you are given with 4D. What is N value? 5. L value for F is 3. So N plus L, 5 plus 3, 8. 5 plus 3, 8. N value, 6. For P, L value, 1. 6 plus 1, 7. N value, 5. L value, 1. 5 plus 1, 6. N value, 4. L value for D, 2. So 4 plus 2, 6. Okay? More the N plus L, more the energy. So 5F has got more N plus L. 5F will have maximum energy. Right? Then it will be 6P. Then it will be 6P. Now among these two, N value is same. Now decide on the base of N. See, N plus L here is same. N plus L here is same. Now decide on the base of N. More the N value, more the energy. 5P will be having more energy. So it's option A. Yes? Guys, do you understand? Do you understand? Do you understand? Tell me the answer of this one. The total number of atomic orbitals in fourth energy state. N is equal to 4. Total orbitals. Few minutes back I told you, total number of orbitals is N square. So 4 ka square is 16. So there are 16 orbitals. Okay. What are degenerate orbitals? What are degenerate orbitals? You would have heard this once in your life. Degenerate orbitals. Degenerate orbitals, which have got same energy. Right? Correct? They have got same energy. Okay, guys? So, chalo. With this, we are done. Okay? There is one very small topic here that I left. What was that? That was shapes of orbitals. Do you remember that? How S orbital looks like, how P orbital looks like, how D orbital looks like. Let me show it to you quickly. It's a simple one. S orbitals are spherical. Let's say this is the nucleus. S orbitals are spherical like this. What are these dots which I'm showing here? This is your electron density basically. You call it as electron cloud. S orbital is spherical. Number 1. S orbital is spherical. S orbital is spherical. Okay. Number 2. P orbitals. P orbitals are dumbbell shaped. P orbitals are dumbbell shaped. First of all, there are 3 P orbitals. Px, Py and Pz. Px, Py and Pz. Okay, Px, Py and Pz. How Px looks like, how Py looks like, and how Pz looks like. Understand, guys. For example, imagine that this is your, for example, y-axis. For example, this is your z-axis. So that means x-axis will be perpendicular to this, like this. This is your x-axis, which is perpendicular. Now Px, it is dumbbell shaped. It is dumbbell shaped. And the lobes of it will be along x-axis, like this. Lobes of it will be along x-axis, like this. Lobes of it will be along x-axis, like this. Right? My dear students, do you see? Do you see a plane cutting this orbital in the middle? A plane cutting this orbital in the middle. And on this plane, there is no electron density. A plane cutting the orbital in the middle. And on the plane, there is no electron density. That plane, which cuts the orbital in such a way that no electron density lies on the plane, that plane is called as nodal plane. So how many nodal planes do you see? One nodal plane. And this nodal plane is your xy plane. It is your xy plane, right? Similarly, Py. In Py, what will happen? In Py, I'm not going to make it. Now you know it already. This was your Px. Now in Py, what's going to happen? My dear students, in Py, the lobes will be along y-axis. There'll be also one nodal plane, and that nodal plane is going to be xz plane. Right? Similarly, in PZ, there'll be the lobes will be along z-axis. Nodal plane will be 1, and that nodal plane will be xy plane. Perfect? Remember these points as well. Remember these points as well. This was Px, Py, Pz. Now comes your d orbitals. Now comes your d orbitals. Okay? Now comes your d orbitals. How d orbitals look like? My dear students, you have got dxy. There is dyz. There is dzx. There is dx square minus y square. And there is dz square. These are the 5 d orbitals which we have. These are the 5 d orbitals which we have. How this dxy looks like? D orbitals are double dumbbell shaped. Let's say this x-axis, this y-axis. The lobes will be between the x and y-axis. This is your dxy. This is your dxy. dyz. dyz. Let's say this is your y-axis, this is your z-axis. dyz. Lobes will be along between the yz axis like this. Okay? dzx. Let's say this is z, this is x. This is your dzx. dx square minus y square. Let's say this x-axis, this y-axis. In x square minus y square, the lobes will be along x and y-axis. This is dx square minus y square. What about dz square? Dz square will be like this. Dz square will be like this. Understand? Dz square. Let's say this x-axis. This for example y-axis. And imagine this is for example your z-axis. Okay? dz square I have to show. Now you must be thinking it's a p. You must be thinking it looks like a p. It looks like a p orbital. But it's not complete yet. It's not complete yet. These are the lobes along z-axis. And there is a bangle kind of the structure here along this xy plane. On this xy plane. On this xy plane. Okay? Remember, there is no nodal plane in dz square. This is dz square. Remember, there is no nodal plane, but there are 2 conical nodal surfaces. Remember directly. 2 conical nodal surfaces. 2 conical nodal surfaces in dz square. Okay? If I ask you how many nodal planes do you see here? How many nodal planes do you see here? See, this is the plane cutting the orbital in such a way that no electron density falls on the plane. Similarly, this is one more plane cutting the orbital in such a way that no electron density falls on it. So I can draw 2 planes on which there will be no electron density. So there will be 2 nodal planes. Right? If this is xy, that means one of the nodal plane will be yz and one nodal plane will be xz. This was xy, right? One nodal plane will be yz, one will be xz. Right? Class chal rahi hai bahar. Class chal rahi hai meri. Okay. dyz. dyz. First of all, this is again a nodal plane. One nodal plane. This is one more nodal plane, right? So first of all, there are again 2 nodal planes. This was dyz. So it's going to be dxy and dzx. These are the 2 nodal planes which we have. This was your dyz. So one is going to be xy, one is going to be xz. Yeah? Guys, do you understand? Here also, this is one nodal plane. This is one more nodal plane. So again, I would say there are 2 nodal planes. And one nodal plane will be, if this is zx, one will be yz and one will be xy. These are the 2 nodal planes which we have here. Okay? And here also, the same 2 nodal planes. These are the nodal planes. These are the nodal planes. One will be xz, one will be yz. xz and yz. Perfect. Here there will be no nodal plane, but there will be 2 conical nodal surfaces. And those conical nodal surfaces can be shown like this. This is one of the conical nodal surface. This is one more conical nodal surface. You don't have to go to the depth. Just remember what I'm saying. That's it. 2 conical nodal surfaces in dz square. So with this, our atomic structure is also over. Now, my dear students, next chapter will start after a break. But I would want every one of you to be back on time. And if everyone is not back, I would be
canceling the session right there. Okay. It is 1-2. I'm giving you a proper 30-minute break, proper 30-minute lunch break. Okay. I would want everyone to be back by 1:40, guys. Okay. 1:40 p.m. Okay. Be back on time. Be back on time. Be back on time. Done? 40 minutes is enough. But I want every one of you to be back. Everyone means everyone. And I'll see you after the break. Next chapter, I'll see here only. I don't know what's the next chapter. Let's see. Anyone we can take. You tell me in the chats afterwards which chapter to take. I'll start with that chapter. See you after the break, guys. Is everyone back? Is everyone back? I was expecting you would be spamming in the chat, late OP, late OP, late OP, yeah? Okay, everyone is back? So what's up? Are you done with your lunch? Are you done with your lunch, people? All right, perfect. So what's up? What's up? Now almost like 12 to 13 days are left. How do you feel? Excited? Nervous? Mixed emotions? What is it? What's it? Depressed? Huh? Achha, by the way, day after tomorrow, on Monday, I'm going to keep a session at 9 p.m. That will be complete chemistry in 100 questions. So we'll be solving some more questions on Monday 9 p.m. Just to let you know. All right, people. All right. Perfect. Yes, 9 p.m. at night, of course. So should we start? I hope whatever things I've discussed till now, every single thing is like super clear to everyone. Yeah? Okay, now, my dear students, we are going to start the next chapter. That is going to be a redox reaction. A redox reaction. I told you my throat is not in a good condition. Okay. Organic chemistry session will be taken by KK sir on Wednesday. I'll let you know, don't worry. You all are on my Telegram, right? You have joined my Telegram? Then no need to worry, okay? I'll be discussing entire schedule there. Don't worry. There will be a marathon of 12th chemistry as well. Everything is sorted, don't worry. I'll keep you updated on my Telegram. Okay, people. So let's move on and let's get going with the chapter redox reactions. So first of all, from which topics the questions are going to come in the chapter redox? What are the topics? What are the topics? Yes, before 25th only, I'll keep that session also, don't worry. So first of all, what are the topics from which questions are going to come in the chapter redox reactions? Let me tell you the name of the topics. The first topic is oxidation state. Oxidation state. A theoretical question will come from this, number one. Number two, identification of oxidizing agents, reducing agents. This is the second topic from which questions are going to come. The third topic in redox from which question will be coming, that is going to be equivalent mass calculation. And my dear students, there is one more topic from which questions will be coming, that will be balancing of redox reactions. From these four topics, you will be getting question from the chapter a redox reaction in the NEET 2026. So let's discuss all these topics in detail one by one here, right? And I'll try to be super quick, and please do match my speed with you. Okay? Perfect, guys. Let's move on and let's talk about the first topic, that is calculation of oxidation state. Calculation of oxidation state. Calculation of oxidation state.
My dear students, how do we do the calculation of oxidation state? It's pretty much simple. It is pretty much simple. Someone is asking about the concentration terms. Concentration terms will be done in the solution chapter. That is class 12th marathon, not today. Okay, this is class 11th marathon. So first of all, calculation of oxidation state. How do we calculate the oxidation states? Try to understand few things. My dear students, here I am writing few compounds. MnO4 negative, Cr2O7 dinegative, for example, S4O6 dinegative, Fe2O3, Fe3O4. Similarly, we have got C3O2, Br3O8, NH4NO2, NH4NO2, and Fe0.930. Right? These are the compounds which are mentioned over here, and I've underlined few elements here. I need to calculate the oxidation states of the underlined elements. I need to calculate oxidation states of the underlined elements. How do I exactly do it? My dear students, first thing which I want every one of you to remember from now onwards. See, you know oxygen? Remember the most common oxidation state of oxygen is -2. Most common oxidation state. You know hydrogen? Its most common oxidation state is +1. Remember these two things first of all. The most common oxidation state of oxygen is -2. The most common oxidation state of hydrogen is +1. Now people, in the first question, I need to calculate the oxidation state of manganese. Let the oxidation state of manganese is X plus oxygen. The most common oxidation state of oxygen is -2. How many oxygen atoms? 4 is equal to, what is the net charge? Net charge is -1. When you solve this, you'll get the X value as +7. So manganese here is in +7 oxidation state. Pretty much simple. The second one, let the oxidation state of chromium is X. But over here we have got 2 chromium atoms, so it will be 2X. Oxygen, -2. 7 oxygen atoms. Net charge, -2. When you solve this, the value of X will come out to be +6. So chromium here is in +6 oxidation state. Right? For example, sulfur. Let the oxidation state of sulfur be X. So this is going to be 4X. Oxygen is going to show -2 oxidation state. And there are 6 oxygen atoms. Net charge is S4O6 dinegative. Net charge is -2. When you solve this, the value of X will come out to be +2.5. So this is the oxidation state of sulfur here. Similarly, this iron. Let its oxidation state be X. It's going to be 2X. Oxygen will show -2. Right? There are 3 oxygen atoms. Net charge is 0. When you solve, X value will come out to be +3. Fe3O4. Let its oxidation state is X. So this will be 3X. Oxygen -2. 4 oxygen atoms. Net charge 0. So solve it. It will be +8/3. Similarly, this is going to be 3X. Oxygen will show -2. There are 2 oxygen atoms. Net charge 0. Solve it. X value will come out to be +4/3. Bromine. Let its oxidation state is X. This will be 3X. Oxygen will show -2. There are 8 oxygen atoms. Net charge 0. The value of X comes out to be +16/3. Now this NH4NO2 which you have here, this NH4NH2, it exists as NH4 positive dot NO2 negative. It exists as NH4 positive dot NO2 negative. I have to calculate oxidations of this nitrogen as well as this nitrogen. Well, in order to calculate oxidations of this nitrogen, I'll consider this part as the separate entity. I'll consider this part as the separate entity. Now, let's calculate the oxidations of nitrogen here. This is X. Hydrogen, it shows +1. There are 4 hydrogen atoms. Net charge here is +1. When you solve it, X value will be -3. Now, what about this particular nitrogen? Let its oxidation state be X. Oxygen will show -2. There are 2 oxygen atoms. Net charge is -1. When you get it, X value will come out to be +3. Got it? Now you have got Fe0.930. Let me make it on another slide. We have got Fe0.930. Let the oxidation state of iron be X. And how many iron atoms do you see? 0.93. Plus, oxygen is going to show -2 oxygen state. Net charge is 0. When you solve this, it's going to be 0.93. X -2 is equal to 0. Or I would say X will be equal to 2 divided by 0.93. Or I can say 200 divided by 93. So its oxidation state here is +200 divided by 93. Perfect. Got it? Is it clear? Simple.
Is it clear, people? Very simple. Yes? Let me know once in the chats. Is it simple? Is it simple? Every one of you. Perfect. Now, my dear students, remember one thing. Remember one thing. Maximum oxidation state of an element. Maximum oxidation state of an element cannot be greater than +7. Maximum oxidation state of an element, it cannot be greater than +7. Except osmium in osmium tetroxide, where it is +8. This particular statement is very important. Remember this directly. My dear students, the maximum oxidation state of an element, it can never be greater than +7. The maximum oxidation state of an element, it can never be greater than +7. There is one exception here. In your syllabus, there is one exception. There are more also, right? That is osmium. When osmium forms OSO4, the oxidation state of osmium at that time is +8, right? This was the question asked once in AIMS examination as well. What is the oxidation state of osmium in OSO4? Okay? Remember this particular point as well. Remember this particular point as well. Now, why this statement is important? Why this statement is important? There's a logic. What is the logic? Have a look. For example, I'm writing CrO5. I want you to calculate the oxidation state of chromium. You'll say it's X. Oxygen will show -2. There are 5 oxygen atoms. Net charge is 0. When you solve, you'll get the X value as +10. But is +10 possible? Is +10 possible? No. The maximum oxidation state of an element cannot be greater than +7, except osmium in OSO4. Okay? So this is wrong. This is not right. Similarly, for example, I'm writing CrO6. I want you to calculate oxidation state of chromium. My dear students, you will say it is X. Oxygen shows -2. There are 6 oxygen atoms. Net charge is 0. When you calculate X, it comes out to be +12. But +12 again is not possible. Maximum oxidation state of an element cannot be greater than +7, except this, right? So this is wrong. This is wrong. Now, how do we correct them? How do we correct them? We correct them with the help of structures. So there are some small structures which I want every one of you to remember. There are few structures of some compounds. There are some structures of some important compounds which I want every one of you to remember. Which structures exactly am I talking about? My dear students, the first one is CrO5. You must remember its structure. It has got a butterfly-like structure. Butterfly-like structure. Remember its color as well. It is deep blue in color. It is deep blue in color. How it looks like exactly? This is chromium, double bond oxygen. This is single bond. This is single bond. There's a linkage here. Single bond, single bond. There's a bond here. Linkage here between 2 oxygen atoms. This is the structure of your CrO5. Now, from the structure, how do I get the oxidation state? From the structure, how do I get the oxidation state? Try to understand. First of all, this is a single bond. Between what? Chromium and oxygen. My dear students, all of you must be knowing about one thing. In the periodic table, which one is the most electronegative element? Fluorine, followed by oxygen, followed by nitrogen. In the periodic table, fluorine is the most electronegative element, followed by oxygen, followed by nitrogen. And you must be knowing, when you move from left to right in the periodic table, electronegativity increases. And when you move from top to bottom in the periodic table, electronegativity decreases. Remember these 2 points. Left to right, electronegativity increases. Top to bottom, electronegativity decreases. Now, look at this particular bond. The bond is between chromium and oxygen. Which one is more electronegative? Oxygen. So this electron pair, this bond pair will be shifted towards oxygen, due to which oxygen gets -1, chromium gets +1. Due to this single bond, again, oxygen is more electronegative. Electron pair will be shifted towards oxygen. So -1, +1. Due to this single bond, -1, +1. Due to this single bond, -1, +1. Due to this double bond, -2, +2. So tell me, what is the total charge on chromium which you see? +2, +3, +4, +5, +6. So the actual oxidation state of chromium in CrO5, it is +6. It is not +10. Understood? The second structure, my dear students, that is your CrO6. This was asked in your NEET 2022 as well. What is the oxidation state of chromium in CrO6? What is the oxidation state of chromium in CrO6? Now understand. Look at the structure. The structure is like the Cr. This is oxygen. This is oxygen. There is a single bond. Again,
Two oxygen atoms, single bond. Again, two oxygen atoms, single bond. One thing I forgot to tell you. What is that? My dear students, whenever you see a single bond between two oxygen atoms, whenever you see a single bonded linkage between two oxygen atoms, this linkage is called as peroxide linkage. This linkage is called as peroxide linkage. This linkage is called as peroxide linkage. Whenever you see a single bonded linkage between two oxygen atoms, the linkage is called as peroxide linkage. Now, my dear students, tell me one thing. Chromium, oxygen. Oxygen is more electronegative. So oxygen will have -1. This will have +1. Again, +1. Again, +1. +1, +1, +1. What is the total charge on chromium here? It will be +6. So +6 is the oxidation state of chromium in CrO6. Okay. If I ask you, how many peroxide linkage do you see here? How many peroxide linkage do you see here? This is one peroxide, second peroxide, third peroxide. So there are 3 peroxide linkages here in CrO6. Similarly, there is a compound called as Carose acid. There is a compound called as Carose acid. Carose acid formalizes H2SO5. H2SO5. You need to remember its structure as well. This is S, double bond O, oxygen attached with hydrogen. This is oxygen, oxygen, and here we have got hydrogen. So my dear students, now calculate the oxidation state. Among sulfur and oxygen, which one is more electronegative? Oxygen. So both the electron pairs will be shifted towards oxygen. Oxygen gets -2, sulfur gets +2. Again, due to this double bond, sulfur again gets +2. Due to this single bond, sulfur gets +1. Due to this single bond, sulfur gets +1. So what is the total oxidation state of sulfur here? +2, +4, +5, +6. So +6. Do you see any peroxide linkage? Yes, there is one peroxide linkage here in H2SO5. Yes. Perfectly done. Amazing. So this was your Carose acid, the third structure. The fourth one, my dear students, have you heard about oleum? Have you heard about oleum? H2S2O7. H2S2O7. This is SOS, double bond O, oxygen attached with hydrogen, double bond O, oxygen attached with hydrogen. When you calculate the oxidation state of sulfur, here you'll find out to be +6. Here also you'll find out as +6, right? By following the same procedure. Perfect. Now, how many sulfur atoms do you see here? 2. So, if I want to calculate average oxidation state on sulfur, see guys, the first sulfur has got +6 oxidation state, plus second sulfur has got +6 oxidation state, divided by, there are 2 sulfur atoms. So, the average comes out to be +6, right? There is a special linkage here, SOS linkage, SOS linkage. There is a special linkage here, SOS linkage, right? Perfect. Perfect, people. Is it clear? Amazing. So this was your oleum. Now talking about Marshall's acid. Marshall's acid, it has got the formula of H2S2O8. So how it looks like exactly? This is SOOS. Guys, there is no trick to make these structures, okay? You have to practice them once. You have to practice them once, twice, then you will be able to make these structures. Now here, when you calculate the oxidation state, sulfur will be in +6. This sulfur will be also in +6. So average oxidation state of sulfur. The first sulfur has got +6, second has got +6, 2 sulfur atoms, so average is +6. So this was your Marshall's acid. This was your Marshall's acid, right? Similarly, my dear students, the next structure. Till now we are done with 5, right? The next structure, that is the 6th one. 6th one is Na2S4O6. Na2S4O6, or you can write it simply as tetrathionate ion, S4O6 dinegative. S4O6 dinegative, right? How it looks like? This is S, double bond O, oxygen with a negative charge. This is double bond O, this is double bond O, and here oxygen with a negative charge. And on this side, there'll be Na positive attracted to it. On this side, there'll be Na positive attracted to it. Now. This sulfur, when you calculate its oxidation state, this will be +5. this sulfur will be in 0 oxidation state, this sulfur will be in 0 oxidation state, this sulfur will be in +5 oxidation state. So if I ask you average oxidation state of sulfur here, the first sulfur +5, second 0, third 0, fourth +5 divided by total 4. So average will come out to be +2.5. This is the average oxidation state of sulfur in your S4O6 di negative. Right? Perfect, people. Am I clear? Am I clear? Am I clear? Let me know once in the chats, people, quick. I think there is electricity cut. Wait. Let the generator start. We have to wait for a few seconds. Okay, guys, I believe this is clear. I believe all of this is clear. Yeah? I believe all of this is clear. So this was the structure of your S4O6 di-negative. Okay? Now, my dear students, there is one more structure which we have. You must have heard about C3O2. Carbon suboxide. How it looks like exactly? Its structure is C double bond C, double bond C, double bonded oxygen, double bonded oxygen. Now, if I ask you to calculate the oxidation state of all the carbon atoms, how do I exactly do it? How do I exactly do it? How do I exactly do it? Check it out. This is carbon double bond oxygen. So oxygen will attract both the electron pairs towards itself. So -2. Carbon will be showing +2. This carbon will also show +2. This carbon will in 0 oxidation state. Because on one side carbon, another side also carbon. So average oxidation state of carbon, the first carbon is having +2, second 0, third +2, total 3 carbon atoms. The average comes out to be +4/3. Similarly, my dear students, you have got Br3O8. Br3O8. If you talk about this bromine, if you want to look at its structure is something like this. This is Br single bond Br single bond Br, double bonded oxygen, double bonded oxygen, double bonded oxygen. Again, everywhere there is a double bond here in Br3O8. You need to remember the structure, people. And if I ask you about the oxidation state here, it will be in +6. This will be in +4. Even this will be in +4. So now you can easily calculate average oxidation state of bromine here. It will be, the first one is having +6, second +4, third one, sorry, this is +6. Third was in +6 divided by total 3 bromine atoms. 6, 6, 12, 4, 16. So it's +16/3. It's average oxidation state. Yeah? I believe this is super clear. And my dear students, if this is clear, remember there is one thing called as bleaching powder. CaOCl2. There is one compound called as bleaching powder. Let me write it here only. Bleaching powder. Bleaching powder. What is the formula for bleaching powder? It is CaOCl2. How many chlorine atoms do you see here? 2. Remember, one chlorine is in -1 oxidation state and other chlorine is in +1 oxidation state in bleaching powder, right? Therefore, if I ask you, what is the average oxidation state of chlorine in bleaching powder? One is having +1, second -1. So average comes out to be 0. Average comes out to be 0. Yes, average comes out to be 0. I believe this is clear. I believe this is super clear to everyone. So these were some very, very important structures. There are more structures coming when I'll be discussing equivalent mass with you. Okay? Now, my dear students, try to understand one thing. How do you exactly define term oxidation? You must be knowing oxidation. What is oxidation? In simple words, oxidation is nothing but increase in the oxidation state. Whenever you see oxidation state of an element increasing, whenever you see oxidation state of an element increasing, understand, whenever you see oxidation state of an element increasing during any reaction, understand that element will be undergoing oxidation. And the one that undergoes oxidation also involves loss of electrons. Oxidation also involves loss of electrons. What does it mean? You will understand in 2 minutes. Just wait. Similarly, my dear students, there is a term called as reduction. There is a term called as reduction. Reduction is defined as decrease in the oxidation state. Decrease in the oxidation state of an element is called as reduction, and reduction involves gain of electrons. A reduction involves gain of electrons. Now, my dear students, try to understand what exactly I'm going to do. For example, Let's say you've got the reaction like this. Zinc plus copper dye positive. It gives zinc plus zinc dye positive plus copper. This is the reaction, for example. This is the reaction, for example. Now tell me one thing. What is the oxidation state of zinc here? Do you see any charge on zinc? No. Do you see charge on copper? Yes, +2. Charge on zinc? Yes, +2. Charge on copper? 0. Now tell me, is the oxidation state of zinc increasing or decreasing? 0 to +2. Oxidation state of zinc is increasing. I told you, increase in the oxidation state is what you call as oxidation. I would say zinc is undergoing oxidation. And the one that undergoes oxidation, that loses electrons. So zinc will be undergoing loss of electrons. And remember, the one that undergoes oxidation, that's called as reducing agent. The one that undergoes oxidation is called as reducing agent. Similarly, +2 to 0. +2 to 0, decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. The one that undergoes reduction will be gaining electrons. And remember, the one that gains electrons, the one that undergoes reduction, that's called as oxidizing agent. Perfect. The one that undergoes oxidation is your reducing agent. The one that undergoes reduction is what you call as the oxidizing agent. Okay? Perfectly done. Now, my dear students, for example, I'm giving you a reaction like this. Let's say you've got the reaction MnO4 negative plus Fe dye positive. Let's say it gives Mn dye positive plus Fe tri positive. This is the reaction. And I'm asking you, which one is the oxidizing agent? Which one is the reducing agent? How do you do it? How do you do it? How do you do it? Tell me, what is the oxidation state of manganese here? When you calculate it, X minus 2 into 4 is equal to -1. So this is +7. Oxidation state of iron is here +2. Manganese is in +2. Iron in +3. Understand? +7 to +2. Decrease. Decrease means reduction. So I would say this entire compound is undergoing reduction. And the one that undergoes reduction is your oxidizing agent. +2 to +3. Increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. So Fe dye positive is undergoing oxidation. The one that undergoes oxidation is your reducing agent. The one that undergoes oxidation is your reducing agent. Am I clear? Hello? Hello? Anji? Sir, bishus, tu karibe thoda shamas phone bis class mas vinkinas. Okay. Okay, guys. I hope now you can easily check which one is your oxidizing agent and which one is your reducing agent. Now, guys, one thing very, very, very important which I'm going to tell you. What is that? Understand. When you talk about the p block elements, they show range of oxidation states. P block elements, they show range of oxidation states. And remember, what range of oxidation states P block element shows? Oxidation state of P block element is always from group number -18 to group number -10. Group number -18 to group number -10. This is the range of the oxidation states that P block element shows. For example, if I, talk about chlorine, you know chlorine belongs to 17th group, right? Chlorine belongs to 17th group. If chlorine belongs to 17th group, what will be its range of oxidation state? 17 minus 18 is -1. 17 minus 10 is +7. So I would say this is the lowest possible oxidation state of chlorine. This is the highest possible oxidation state of chlorine, right? For example, I talk about sulfur. Sulfur belongs to group number 16, oxygen family, right? So what is the range of the oxidation states? Range of oxidation states. 16 minus 18 is -2. 16 minus 10 is +6. So I would say the lowest possible oxidation state of sulfur is -2. Highest possible oxidation state of sulfur is +6. Yeah? And remember, my dear students, your P block elements, they are from group number 13 to 18. Group 13 to group 18 elements are what you call as P block elements. Perfect. Now, there is one more thing which I want to specify here. My dear students, I'm selecting two D block elements. One is chromium, one is manganese. Frequently, these two elements will be used in these chapters. Both of them are D block elements. Both of them are D block elements. You need to remember their maximum oxidation state. Remember, chromium shows maximum oxidation state of +6. Manganese shows maximum oxidation state of +7. Chromium shows maximum oxidation state of +6.
Manganese shows maximum oxidation state of +7. Remember these two things as well. Now, why these things are very, very, very important? Because there's a logic, there's a reason. And what is the reason? Try to understand what is the reason. Try to understand what is the reason. I'm writing, for example, HCl. I wrote a compound HCl. Now, I am asking you whether this HCl is oxidizing agent or reducing agent. I'm asking you whether this HCl is an oxidizing agent or reducing agent or both, right? For example, I'm giving you a compound H3PO4 and I'm asking you whether it works as the oxidizing agent, reducing agent or both. How do we do it? How do we do it? How do we do it? Just a second. Just a second, guys. Okay. For example, I'm giving you a compound and I'm asking you whether it is your oxidizing agent, it works as a reducing agent, or it works like both. So how do we do it? Understand properly. The first thing which I always do is I always calculate the oxidation state of the central atom. I always calculate the oxidation state of central atom. Now, my dear students, if the central atom is present in lowest oxidation state already, if the central atom is already present in lowest oxidation state, if the central atom is already present in lowest oxidation state, that means it cannot further decrease it. If the central atom is already present in lowest oxidation state, that means it cannot further decrease it, but it can increase. When it increases its oxidation state, it will undergo oxidation. If it undergoes oxidation, that means at that point of time, it's going to behave as a reducing agent. Simple. Yes. Now, if the central atom, my dear students, if the central atom is already in highest possible oxidation state, if the central atom is already in highest oxidation state, it cannot further increase it because it's already in highest. It cannot further increase it, but it can decrease. When it decreases, it undergoes reduction. When it undergoes reduction, it is going to behave as the oxidizing agent. Yes? Agreed? Similarly, people, if the central atom is neither in highest nor lowest oxidation state, if central atom is in intermediate oxidation state, if the central atom is neither in highest nor in lowest, it is in between, its oxidation state is in between. That means it can increase also, it can decrease also. So it can behave both oxidizing as well as reducing agent. Now you must be thinking, why is he teaching this stuff? Why do I need this? You need this, guys. Where? Have a look. For example, I'm writing H3PO4. I'm asking you whether it's an oxidizing agent, it is a reducing agent, or both. Tell me. How do I check it? First of all, I will be calculating the oxidation state of phosphorus. It will be in +5 when you calculate it. +1 into 3. This is X minus 2 into 4. So 5. Phosphorus. Phosphorus is group 15 element. And group 15 elements, their range is from -3 to +5 when you check it. So this is the lowest possible oxidation state of phosphorus. This is the highest. So phosphorus right here is already in highest. Phosphorus right here is already in highest oxidation state. So it cannot further increase it, but it can decrease it. It can decrease. And when it decreases, it undergoes reduction. It behaves like the oxidizing agent. So for H3PO4 behaves like the oxidizing agent. Perfect. For example, I'm writing HCl. I'm asking you, what is its nature? Chlorine in -1 oxidation state here, right? What is the range of oxidation state of chlorine? It is -1 to +7. Few minutes back only I told you, -1 to +7. Perfect. This is the lowest oxidation state. This is the highest oxidation state. So can I say Cl here is already in lowest? Cl is already in lowest oxidation state. So it cannot further decrease, but it can increase. When it increases, it undergoes oxidation. When it undergoes oxidation, it's going to behave like the reducing agent. So it is the reducing agent here. Understood? For example, I have got K2Cr2O7. When you calculate oxidation state of chromium here, it is +6. It is +6. When you calculate the oxidation state of chromium here, it is +6. So chromium is already in maximum oxidation state. It cannot further increase, but it can decrease. When it decreases, undergoes reduction. So oxidizing agent. Understood? For example, I'm writing H2O2. H2O2, hydrogen peroxide. Remember in hydrogen peroxide,
Oxidation state of oxygen is -1. In hydrogen peroxide, oxidation state of oxygen is -1. Now, what is the range of oxidation state which oxygen shows? Oxygen is group 16 element. So 16 minus 18 is -2. 16 minus 10 is +6. So lowest is -2. Highest is +6. But here is -1. So oxygen here is neither in lowest nor in highest. So it is in the middle somewhere. It is an intermediate oxidation state. So it can increase also, it can decrease also. That means it can behave both oxidizing as well as reducing agents. So tell me once in the chats, is this particular topic clear to everyone or not? Yes or no quickly. Yeah? I want everyone to let me know quickly in the chats. Is this particular topic clear? Yes or no, people? Everyone means everyone. Please don't ask me to repeat. Instead, you can do one thing. You can drag the video a little back. It will be a replay for you. Whosoever was telling me to repeat. Yeah? Perfect, 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 people. I told you already, your P block elements, they show variable oxidation state. Group number -18 till group number -10. Perfectly done. Perfectly done. Guys, there will be one more question that will be asked. There will be one more question here asked. Which of the following will undergo disproportionation? The question will be like this. The question will be which of the following undergoes disproportionation? Disproportionation. What is meant by the term disproportionation? Let's get to know that first. What is meant by disproportionation? Understand, guys. Remember one thing. For example, you have got the reaction like this. A2 gives A positive plus A negative. Let's say you have got the reaction like this. A2 gives A positive plus A negative. Now, if I ask you, what is the oxidation state of A here? You'll say it's 0. It does not have any charge. No charge. What is the oxidation state of this A here? It is +1. A -1. 0 to +1. Increase. 0 to -1. Decrease. 0 to +1. Increase. 0 to -1. Decrease. So can I say oxidation state of same element is increasing as well as decreasing simultaneously? Yes. Oxidation state of same element is increasing as well as decreasing simultaneously. Whenever you see such kind of the scenario where oxidation state of same element increases as well as decreases simultaneously, we say that species undergoes disproportionation. So A2 here undergoes disproportionation. Now you'll be asked a question. Which of the following undergoes disproportionation? Your options will be, for example, ClO negative, ClO2 negative, ClO3 negative, ClO4 negative. Can I say in disproportionation, oxidation state of same element should increase as well as decrease? Perfect. Now imagine if the central atom is already in maximum oxidation state. Imagine if the central atom is already in maximum oxidation state. It cannot increase it further. It cannot undergo disproportionation. Or if the central atom is already in lowest oxidation state, it cannot further decrease it. It cannot further decrease it, right? Because it's already in lowest. So it cannot undergo disproportionation. So can I say for disproportionation to happen, central atom should be present in intermediate oxidation state? Right? Sir, how to find lowest possible and highest? 2 minutes back, I've told you that. Just drag the video back, you'll understand. So I would say in order to show disproportionation, your central atom should be in intermediate oxidation state so that it can increase as well as decrease. So that it can increase as well as decrease. Now, just do one thing. Just do one thing. What is the oxidation state of chlorine here? X minus 2 is equal to -1, so it's +1. X minus 4 is equal to -1, so it's +3. This will be similarly +5. This will be similarly +7. So tell me, what is the range of oxidation state which chlorine shows? Chlorine is group 17. Group number minus 18. So 17 minus 18 is minus 1. 17 minus 10 is plus 7. So this is the lowest possible oxidation state of chlorine. This is the highest possible oxidation state of chlorine. Right? Now, if you look carefully, what I have to check? Which of the following shows disproportion? Here chlorine is in plus 1. Here chlorine is in plus 1. Plus 1 is neither minimum nor maximum. Plus 1 is intermediate. That means here chlorine can increase as well as decrease. So it will undergo disproportionation. This will also undergo. This will also undergo. This cannot undergo disproportionation. Why? Because this is already in highest. It cannot further increase it. Am I clear with this? Everyone, people, am I clear with this? Yeah? Am I clear with this? Everyone in the chats? Sir, question is wrong. No, question is correct, but it is more than one option correct, which is never asked in NEET examination. In NEET examination, they'll ask you, which of the following does not undergo disproportion? Then your answer is going to be this one. Alright, guys. Okay, I'm moving on to next topic, my dear students. That is your equivalent mass calculation. This is very, very, very important. Equivalent mass calculation. How do you exactly calculate equivalent mass of the substance? How do you calculate equivalent mass of the substance? Sir, please block spammers. Give me the name of the spammer. I'm going to block right away. Just tell me the name of the spammer. Okay. How do you calculate equivalent mass of the substance? My dear students, remember one direct formula. Equivalent mass is nothing but it is molar mass of the substance divided by n factor of the substance. Equivalent mass is nothing but it is molar mass of the substance divided by n factor of the substance. Okay, n factor of the substance. Now, the first point. What is n factor for elements? What is n factor for elements? For elements, n factor is nothing but valency. For elements, n factor is nothing but valency. For example, talk about nitrogen. What is the valency of nitrogen? 3. Talk about oxygen. What is the valency of oxygen? 2. Carbon. What is the valency of carbon? 4. Sodium. What is the valency of sodium? 1. Magnesium. What is the valency of magnesium? 2. Whatever is the valency of the element, that's what you call its n factor. That's what you call its n factor. And once you get n factor, you can easily calculate equivalent mass. So tell me, the equivalent mass of nitrogen will be molar mass of nitrogen divided by n factor 3. Similarly, equivalent mass of oxygen, molar mass of oxygen divided by n factor 2. Equivalent mass of carbon, molar mass of carbon divided by n factor 4. Similarly, you can calculate the rest of the things. I'm pretty much sure. Yes? So, for elements, valency is nothing but n factor. Second, in case of salts, what is n factor? In case of salts, n factor is nothing but LCM of charge on cation, LCM of charge on cation, comma, the charge on anion. In case of salts, what is the n factor? N factor is LCM of charge on cation, charge on anion. Now, people, what does that mean? For example, you have got NaCl, it's a salt. You have got, for example, BaCl2, right? You have got AlCl3. You have got Al2SO4 whole thrice. These are all salts. Perfect. Now, I want to calculate their equivalent masses. So, what do I need? I need their n factors. How do I calculate their n factors? N factor of salt is nothing but LCM of charge on cation and anion. Now. What is my cation? What is my anion? What is the charges on them? Have a look. How many Na here? 1. Chlorine 1. Barium 1. Chlorine 2. Aluminium 1. Chlorine 3. Aluminum 2. Sulfate 3. What do I do here? I'll do the crisscross stuff. This one will go as the charge here. This one will go as the charge here. This 2 will go as the charge here. This 1 will go as the charge here. This 3 will go as the charge here. This 1 will go as the charge here. This 3 will go here. This 2 will go here. Now tell me, what is the LCM of 1 and 1? That is 1. What is the LCM of 2 and 1? That is 2. What is the LCM of 3 and 1? That is 3. What is the LCM of 3 and 2? That's 6. LCM of what? LCM of charge on cation and anion. LCM of charge on cation and anion gives you the n factor of the salt. So these are the n factors of these salts. And if you got the n factors, you can easily calculate equivalent masses. How? Molar mass divided by n factor. Molar mass divided by n factor. Molar mass divided by n factor. Done? Done, people? Perfect. So first one I discussed, what was that? That was n factor of elements. Then I discussed n factor of salts. The third one, my dear students. The third one. Third one is basically n factor of acids. Third one is n factor of acids. How do you calculate n factor of acids? N factor of acids is nothing but basicity of the acid. Basicity of the acid. And how do I define basicity? Number of H positives an acid donates. Number of H positives an acid donates, or number of OH negatives an acid accepts. An acid accepts. Number of lone pairs an acid accepts. These are the three ways by means of which you can define n factor of the acids. N factor is nothing but basicity. How do I define basicity? How do we define basicity? Number of H positives an acid donates, number of OH negatives an acid accepts, number of lone pairs an acid accepts. Okay? Now, try to understand, people, what I'm going to say. Try to understand what I'm going to say. For example, I'm taking HCl, I'm taking H2SO4, I'm taking HNO3, I'm taking H3PO4. These are the acids, some common acids, right? These are some common acids. These are some common acids. Now tell me one thing. When this HCl goes into water, how many H positives it will furnish? It will give 1 H positive. This will give 2 H positives. This will give 1 H positive. This will give 3 H positives. And the number of H positives an acid donates. The number of H positives an acid donates. That defines its basicity. And whatever is the basicity of the acid, that's what you call it as n factor. So n factor of HCl here is 1. N factor of H2SO4 is 2. N factor of HNO3 is 1. N factor of H3PO4 is 3. If you got n factors of these acids, can you calculate its equivalent masses? Molar mass divided by n factor, right? Molar mass divided by n factor. Perfect. Now, my dear students, I am going to write an important statement. Remember, an acid donates only that hydrogen. An acid donates only that hydrogen in the form of H positives. An acid donates only that hydrogen in the form of H positives, which is attached to more electronegative element like chlorine, oxygen, nitrogen, etc. An acid donates only that hydrogen in the form of H positives, which is attached to more electronegative element like fluorine, oxygen, nitrogen, etc. What does it mean? Why this statement is important? Have a look. Understand. My dear students, for example, here I'm writing H3PO2. Here I'm writing H3PO3. Here I'm writing H3PO4. And here I'm writing H3PO5. Perfect. What do you think? This should give 3 H positives. This should give 3 H positives. This should give 3 H positives. This should also give 3 H positives. So n factor of all of them should be 3. N factor of all of them should be 3. But that's not the case. Why is that? Understand. If you look at the structure of H3PO2, H3PO2 looks like this. This is your H3PO2. Similarly, if you look at H3PO3, it looks like this. This is your H3PO3. Similarly, if you talk about your H3PO4, this is how H3PO4 looks like. H3PO5, this is how H3PO5 looks like. Now tell me one thing. In case of H3PO2, how many hydrogens do you see? 3. But out of 3 hydrogens,
How many hydrogens are attached to more electronegative element? Like oxygen, only one. Here, these two. Here, these three. Here, these three. And you know, an acid donates only that hydrogen. An acid donates only that hydrogen in the form of H positive, which is attached to more electronegative element like fluorine, oxygen, nitrogen. So this acid is going to donate only one H positive. This acid is going to donate only two H positives. This acid will donate three H positives. This acid will donate three H positives. And you know, number of H positives and acid donates. Number of H positives and acid donates, that defines its basicity. And whatever is the basicity of the acid, that's something you call as the N factor of the acid. So what is the N factor of this acid? 1. What is the N factor of this acid? 2. What is the N factor of this acid? 3. What is the N factor of this acid? 3. And if you got the N factors, you can calculate their equivalent masses, right? Molar mass of the acid divided by N factor. Molar mass divided by N factor. Molar mass divided by N factor, right? My dear students, there is one more thing which I want to specify here. What is that? Have you heard about boric acid? BOH whole thrice. It is boric acid. It is boric acid, okay? Boric acid. Or you can represent it as H3BO3. You can represent it as H3BO3 or simply boric acid like this, BOH whole thrice. When you introduce boric acid in water, it gets converted into BOH4 negative. It gets converted into BOH4 negative, okay? First of all, I want to tell you something about this boric acid. This boric acid, it's a weak Lewis acid, remember. It's a weak Lewis acid. Now, tell me one thing. How many OH do you see here? Sorry, this is BOH4 negative, not positive. This is BOH4 negative here. Okay, tell me, how many OH do you see here? 3. Here, 4. How many OH here? 3. How many OH here? 4. That means when boric acid was introduced in water, can I say it has accepted one OH negative? Yeah? Yeah? Do you understand, guys? Boric acid had 3 OH negatives. Now in water, it got converted into BOH4 negative. It accepted one OH negative. Right? The number of OH negatives an acid accepts. The number of OH negatives an acid accepts, that defines its basicity. And whatever is the basicity of the acid, that's what we call as N factor. So this boric acid, its N factor is 1. Because it has accepted one OH negative from water. Okay. Now guys, for example, if a question is asked like this, you have got H2SO4, and for example, this is NaOH. For example, it's forming NaHSO4, and with NaHSO4, you have got water. This is one reaction, let's say. Similarly, I'm writing one more reaction. Let's say this is H2SO4. Let's say this is twice NaOH. For example, it's giving us Na2SO4. And with Na2SO4, you are writing 2 times water. These are the 2 reactions which I mentioned here. Now, I'm asking you, calculate the equivalent mass of H2SO4 here. Calculate the equivalent mass of H2SO4 here. I need to calculate equivalent mass of H2SO4 in these reactions. How do we calculate equivalent mass? Molar mass divided by N factor. So technically, I need to calculate equivalent mass. I need to calculate N factor here as well as N factor here. I need to calculate N factor of H2SO4 here as well as N factor of H2SO4 here. Yeah? How do I do it? Understand. My dear students, remember, when one H positive combines with one OH negative, it forms one water molecule. When one H positive combines with one OH negative, it forms one water molecule. Similarly, when 2 H positives combine with 2 OH negatives, it forms 2 water molecules. Okay? So you tell me one thing. How many water molecules are formed here? 1. If 1 water molecule is formed, that means this acid has given 1 H positive, this base has given 1 OH negative, and they have combined and formed 1 water molecule. So tell me one thing. How many H positives this acid is donating? It is donating 1 H positive, and the number of H positives and acid donates. The number of H positives and acid donates. That defines its basicity. And whatever is the basicity of the acid, that's what they call as N factor of acid. So N factor of H2SO4 here is 1. Similarly, 2 water molecules are formed here. If 2 water molecules are formed, that means this acid has given 2 H positives.
This base has given two OH negatives. Now, these two H positives, two OH negatives have combined and formed two water molecules, right? So look at this acid. Can I say this acid is donating two H positives here? Number of H positives acid donates. That defines its base state. And whatever is its base state, that's what I call its N factor. So its N factor is 2. So in the first reaction, N factor of H2SO4 is 1. In the second reaction, N factor of the same substance, H2SO4, that's 2. So, on changing the type of the reaction, does N factor change? Yes. And if N factor changes, does equivalent mass change? Yes, because equivalent mass is equal to molar mass by N factor. Perfect. So, tell me one thing. Is equivalent mass a fixed quantity or variable quantity? You tell me. Is equivalent mass a fixed quantity or variable quantity? Quickly in the chats. Remember, my dear students, equivalent mass is a variable quantity. Unlike molar mass is always fixed. I believe I'm clear with this. This was your N factor of acids. Now. N factor of bases. N factor of bases. This is also simple. N factor of bases. My dear students, N factor of bases is nothing but it is acidity of the base. Acidity of the base. And acidity I'm going to define by 3 ways. Number 1, number of OH negatives a base donates. Number of OH negatives a base donates. Number of H positives a base accepts. Or number of lone pairs a base donates. These are the 3 ways by means of which I can define what? I can define acidity of the base. Number of OH negatives a base donates. Number of H positives a base accepts. Number of lone pairs a base donates. Next chapter will be started in like 30 minutes. Now we will have a look. Try to understand what exactly I'm going to do. Take some bases. NaOH. You have got KOH. You have got barium hydroxide. You have got AlOH whole thrice. These are some common bases. Tell me one thing. When you introduce this in water, how many OH negatives it will give? 1. This will give 1 OH negative. This will give 2 OH negatives. This will give 3 OH negatives. And the number of OH negatives a base donates. The number of OH negatives a base donates. That defines its acidity. And whatever is acidity, that's what you call as N factor. So N factor of NaOH here is 1. This is also 1. Here it's 2. Here is 3. If you got the N factors, you can calculate equivalent masses. How? Molar mass divided by N factor. Got it, people? Got it? For example, if I give a question like this, I'm writing NH3 plus H2O. Let's say it forms NH4 positive plus OH negative. I'm asking you to calculate the equivalent mass of NH3 in this reaction. See, NH3, it's a base, ammonia, it's a base. Though it does not have OH negative. It is a base. What it does? When it goes into water, it gets converted into NH4 positive. How many hydrogens do you see here? 3. How many hydrogens do you see here? 4. That means when NH3 was introduced in water, how many H positives has it accepted? Tell me that. When NH3 was introduced in water, how many H positives has it accepted? It has accepted 1 H positive. Right? NH3, it had 3 hydrogens. Now in water, it gets converted into NH4 positive. So 4 hydrogens. So that means from 3 to 4, it has accepted 1 H positive. And the number of H positives a base accepts. That defines its acidity, and whatever is the acidity, that's something I call as N factor. So what is the N factor of NH3 here in this reaction? It's 1. If N factor is 1, you can easily calculate its equivalent mass. Understood? Now tell me one thing. If a question is asked like this, zinc hydroxide plus HCl gives ZnOHCl plus H2O. This is one reaction. Second reaction, zinc hydroxide plus 2 times HCl gives ZnCl2 plus 2 times water. I am asked to calculate n factor of zinc hydroxide in both these reactions. Can I do it? Simple. How many water molecules are formed here? 1. That means this base would have given 1 OH negative. Okay, so its n factor is 1. How many water molecules are formed here? 2. That means this base over here would have given 2 OH negatives. So its n factor here is 2. Perfect. Now you can calculate equivalent masses, molar mass by 1, molar mass by 2 in both the reactions. Got it? Got it, people? Got it? Now comes something important. What is that? That is n factor of oxidizing and reducing agents. What is n factor of oxidizing and reducing agents? N factor of oxidizing and reducing agents is nothing but it is the number of moles of electrons lost, gained, or exchanged. Number of moles of electrons lost, gained, or exchanged by 1 mole of substance. Number of moles of electrons lost, gained, or exchanged by 1 mole of substance. The point is, how do we calculate it? My dear students, this is important. Okay? Try to understand this carefully. For example, I'm writing a reaction like this. A2 plus B2. It gives 2 times A positive plus 2 times B negative. Okay? See, oxidation state here is 0, here it is 0, here it is plus 1, here it is minus 1. Now 0 to plus 1, increase in the oxidation state. Increase in the oxidation state is called as oxidation. The one that undergoes oxidation is your reducing agent, right? So automatically this is your oxidizing agent. Technically, I want to calculate the n factors of these oxidizing and reducing agents. How do I do it? Have a look. I'll write n factor of A2. N factor of A2. What I do? I'll first of all keep a mod here. I need to calculate n factor of A2. I would say this is the initial oxidation state of A. This is the final oxidation state. So I'll write final oxidation state of A minus initial. Final minus initial. Final minus initial. It gives me change in the oxidation state of A. But this is the change in the oxidation state for 1 atom of A. What is the subscript of A here? 2. So I'm multiplying this with 2. When you solve it, n factor comes out to be 2. Guys, do you understand? I want to calculate n factor of B2. Take it carefully. N factor of B2 I want to calculate. See, 0 to minus 1. 0 to minus 1. This is the initial oxidation state of B. This is final. So I'll write final minus initial, come mod, multiplied by. Whose n factor I'm calculating? B. I'm calculating the n factor of B2. What is its subscript? 2. So multiplying with that 2. So its n factor is also 2. Yeah? For example, I want to calculate n factor of A positive. N factor of A positive. If I want to calculate n factor of A positive, then I'll go in the reverse direction. I'll call this as initial, this as final. Final minus initial. Final minus initial come mod, multiplied by. Whose n factor I need? A positive. What is its subscript? It's 1. So multiplying this with 1, its n factor is 1. I want to calculate n factor of B negative as well. What it would be? B negative. I'll go in the reverse direction again. This is initial, this is final now. So it's final minus initial come mod, multiplied by. I want to calculate n factor of B negative. Its subscript is 1. So multiplying it with 1. The value comes out to be 1. Yes? Is it clear? Say yes or no in the chats. Quick, people. All right. Now let's try to understand this a bit more in detail. Let's try to understand all this a bit more in detail. Understand, guys. See, guys, have you heard about KMnO4? KMnO4 is a very strong oxidizing agent. And this KMnO4, it shows different reactions in different mediums.
KMnO4, it shows different reactions in different mediums. What reactions? Remember, KMnO4 in acidic medium gets converted into Mn dipositive. KMnO4 in acidic medium gets converted into what? Mn dipositive. In neutral medium, you can say neutral or slightly alkaline, it gets converted into MnO2. And in strongly basic or strongly alkaline medium, it gets converted into MnO4 dinegative. Now, I'm asking you, calculate the N factor of KMnO4 in all the mediums. Calculate the N factor of KMnO4 in all the mediums. How do I do it? Understand. What is the oxidation state of manganese here? +7. See, +7 to +2. +7 to +2. Initial, final. Final minus initial ka mod, that is 5. 5 is the change for one manganese. I have only one. So its N factor is here 5. So N factor of KMnO4 in acidic medium is 5. Now talk about this neutral medium. What is the oxidation state of manganese here? X. This is -2 into 2 is equal to 0. So this comes out to be +4. So it's +7 to +4. +7 to +4. This is initial. This is final. Final minus initial. Come mod. The value is 3. 3 is the change for one manganese. I have only one. So 3 into 1 is 3. So its N factor here is 3. Similarly, see, +7 to +6. +7 to +6. What is the change? +7 to +6. Final minus initial. Come mod. Value is 1. 1 is the change for 1. So 1 into 1 is 1 only. So remember, N factor of KMnO4 in acidic medium is 5. N factor of KMnO4 in neutral medium is 3. N factor of KMnO4 in strongly basic medium, that's 1. Okay? You can remember it like this, BAN, B-A-N, and remember the number 153. Remember the number 153. Okay? Basic, N factor 1. Acidic, N factor 5. Neutral, N factor 3. BAN, 153. Okay? Got it? Got it, got it, got it. Tell me the N factor of K2Cr2O7 in this reaction. What do you think? What do you think? What am I supposed to do? I'm supposed to calculate the oxidation state of chromium here. I'm supposed to calculate oxidation state of chromium here. See, oxidation state of chromium, when you calculate, this is +1 into 2. This will be 2x. -2 into 7 is equal to 0. So it is +6. Here chromium is in +3. So +6 to +3. What is the change? Final minus initial ka mod. The value is 3. 3 is the change for one chromium atom. I have 2. So 3 2s are 6. So N factor of K2Cr2O7 here is 6. Okay? Guys, am I clear with this? Am I clear with this? Am I clear with this? Everyone in the chats? Yeah? Okay. Perfectly done. Perfectly done. Okay, for example, I'm giving a question like this. Tell me the N factor of C2O4 dinegative in this reaction. Tell me the N factor of C2O4 dinegative in this reaction. First of all, calculate the oxidation state of carbon here. Is it going to be X or 2X? It will be 2X, right? This will be -2 into 4 is equal to -2. This will be +3. Here it comes out to be +4. So +3 to +4, +3 to +4, change is 1. 1 is the change for one carbon. I have 2. So 1 into 2 is 2. So its N factor here is 2. Is it clear? Say it once in the chats. Say it once in the chats, my dear students. Say it once in the chats, my dear students. Okay? I believe all of this is like very clear to you. There is one more thing which I would want to discuss with you. What if there is a compound like this, ABC? What if there is a compound? What if there is a compound like this, ABC, in which oxidation state of more than one element was changing? For example, here, if you look here in this compound, oxidation state of only chromium was changing. That's why I calculated change in the oxidation state in chromium. Oxidation state of carbon only was changing. That's why I calculated change in the oxidation state of carbon. Now, what if, my dear students, there is a compound in which oxidation state of more than one element was changing? What do we do at that point of time? Understand. There can be certain possibilities. In this compound, oxidation state of A as well as B, for example, both can increase simultaneously in some reaction. Both can decrease simultaneously in some reaction. One can increase, one can decrease in some reaction, right? Oxidation state of all the three can increase simultaneously in some reaction. Oxidation state of all the three can decrease simultaneously in the reaction. Two can increase, one can decrease in a reaction. These are some possible cases which can happen. Now, if oxidation state of more than one element simultaneously increases or decreases, if oxidation state of more than one element either simultaneously increases or simultaneously decreases, how do we calculate its n factor? Its n factor is going to be n1 plus n2. It is also going to be n1 plus n2. If one increases, one decreases, it's going to be mod of n1 minus n2. All the three increases, so n1 plus n2 plus n3. Similarly, all the three decreases, again, n1 plus n2 plus n3. So basically, if the arrows are in the same direction, then add them. If the arrows are in the same direction, add them. See, these two arrows are in the same direction, so it's going to be n1 plus n2. Last one is in opposite direction, so it's minus n3. Come mod. This is how you calculate their n factors. Do you understand? I can give you an example as well. For example, I'm writing a reaction like this. FeC2O4, it gives Fe tri-positive plus carbon dioxide. I want to calculate the n factor of this species. My dear students, how do we do it? Try to understand very carefully what do I do. This iron here is in plus 2 oxidation state and this carbon here is in plus 3 oxidation state. When you calculate it, this is plus 3 and this is plus 4. Now check one thing, plus 2 to plus 3, increase. Plus 3 to plus 4, again increase. Again increase. Do you see? Plus 2 to plus 3, increase. Plus 3 to plus 4, again increase. So I would say oxidation state of more than one element is simultaneously increasing. Oxidation state of more than one element is simultaneously increases. So how do I calculate its n factor? Its n factor is going to be n1 plus n2. Now what is n1? What is n2? What is n1? What is n2? Understand. Plus 2 to plus 3. Plus 2 to plus 3. What is the change? Final minus initial. The value is 1. 1 is the change for one iron. I have only one. So n1 is 1. Plus 3 to plus 4. What is the change? Final minus initial. The value is 1. 1 is the change for one carbon. I have 2. So n2 value is 2. So I got n1, I got n2. So 2 plus 1 comes out to be 3. Its n factor here will be 3. If you got its n factor, you can calculate its equivalent mass. More than mass divided by n factor. Simple. Now last case of the n factor calculation, that is n factor in disproportionation reactions. N factor in disproportionation reactions. For example, you have got the reaction like this. A2 gives A positive plus A negative. Oxidation state here is 0, here is plus 1, here is minus 1. 0 to plus 1, increase. 0 to minus 1, decrease. Can I say oxidation state of the same element is increasing as well as decreasing simultaneously? Absolutely, right? Oxidation state of same element. Oxidation state of same element is increasing as well as decreasing simultaneously. So I would say this species is undergoing disproportionation. And whenever a species undergoes disproportionation, how do I calculate its n factor? It's n1, n2 divided by n1 plus n2. Now the point is, how do we get n1 and how do we get n2? This is the formula, okay? This is the formula. You have to use it. Now get the n1, get the n2. 0 to plus 1. 0 to plus 1. Change is 1. 1 is the change for one atom. I have 2. So n1 value is 2. 0 to minus 1. 0 to minus 1. Change is 1. 1 is the change for an. I have 2. So n2 is also 2. So it's going to be 2 multiplied by 2 divided by 2 plus 2. The value comes out to be 1. Okay? For example, I'm giving you a question. The question is like this. Br2, it gives Br negative plus BrO3 negative. I'm asking you to calculate the n factor of Br2. Can we do it? N factor of Br2. N factor of Br2. See, the oxidation state of bromine here is 0. Here it is minus 1. When you calculate here, it's plus 5. Now 0 to minus 1. Decrease. 0 to plus 5. Increase. oxidation state of same element is increasing as well as decreasing simultaneously. Oxidation state of same element is increasing as well as decreasing simultaneously. So how do I calculate its n factor? It is again going to be n1, n2 divided by n1 plus n2. Now get the value of n1 and n2. 0 to minus 1. 0 to minus 1. Change. Change is 1. 1 is a change for 1. I have 2. n1 value is 2. 0 to plus 5. 0 to plus 5. Change. Final minus initial. The value is 5. 5 is the change for 1. I have 2. So 5 to 10. So it's going to be 2 multiplied by 10 divided by 2 plus 10. The value comes out to be 5 by 3. So this is the n factor of Br2 in this particular reaction. My dear students, one last topic here. One last topic here, that is your balancing. That is your balancing of redox reactions. Balancing of redox reactions. One simple method I'm going to show you. First of all, let's understand balancing of redox reactions in acidic medium. Balancing of redox reaction in acidic medium. There are few steps which I want you to remember. Number one, first step, get the n factor of reactants. Crisscross the n factors. Balance all the atoms except hydrogen and oxygen. Balance oxygen with the help of water. Balance hydrogen with the help of H positives. Get the n factor of reactants. Okay. Crisscross the n factors. Balance all the atoms except hydrogen, oxygen. Balance oxygen with the help of water. Balance hydrogen with the help of H positives. Have a look how exactly we do it. This is balancing in acidic medium, okay? For example, I've got the reaction like this. I've got the reaction like this. MnO4 negative plus Fe di positive. It gives Fe tri positive plus Mn di positive. This is your reaction. This is your reaction. Now, I need to calculate n factor of reactants first. I need to calculate n factors of reactants first. My dear students, what is the oxidation state of manganese here? When you calculate plus 7, here it is plus 2, here it is plus 3, here it is plus 2. Now, plus 7 to plus 2, plus 7 to plus 2, change. Final minus initial, the value is 5. 5 is the change for 1 manganese. I have only 1, so 5 into 1 is 5. Plus 2 to plus 3, plus 2 to plus 3, change. Final minus initial, the value is 1. 1 is a change for 1. I have only 1, so 1 into 1 is 1. So I got the n factors of reactants. I got the n factors of reactants. After getting the n factors of reactants, just crisscross these n factors. That means this 1, it will go as the stoichiometric coefficient here. This 5, it will go as the stoichiometric coefficient here. After getting the n factors, I crisscrossed these n factors. I crisscrossed these n factors. Now, balance all the atoms except hydrogen, oxygen. How many manganese do you see? 1. So, 1 manganese. How many iron do you see? 5. So, 5 iron. I balanced all the atoms except hydrogen and oxygen. Now I have to balance oxygen with the help of water. So tell me, do you see any oxygen here? Yes. How many? 4. Is there any oxygen on this side? No. Which side is oxygen deficient? Right side. How many oxygen deficiencies? 4. So add 4 water molecules to that side, which is hydrogen deficient. Sorry, which is oxygen deficient. Add 4 water molecules to that side, which is oxygen deficient. Now it is the time to balance hydrogen. Do you see any hydrogen here? No. Do you see hydrogen here? Yes. How many? 8. There is some electricity cut. Just I have to turn the lights off for 2-3 minutes. The electricity comes back. Okay. Now is the time to balance hydrogen. How many hydrogen atoms on this side? 8. On this side? No. Which side is hydrogen deficient? Left side. How many hydrogen deficiencies? 8. So add 8 H positives on that side, which is hydrogen deficient. Now the reaction is balanced. Isn't it simple, guys? Honestly, tell me, isn't it simple? Let me take one more example so that things will be more clear to you. For example, you have got a reaction like this. Cr2O7 di negative plus Sn di positive. It gives Cr tri positive plus Sn plus 4. Let's say I have to balance this reaction again in acidic medium. Okay? Now, try to understand what they do exactly. Get the n factors of reactants. How? For that, I have to calculate oxidation states. Oxidation state of chromium here will be plus 6. Here, tin will be in plus 2.
Here chromium is in +3. Here tin is in +4. Now, +6 to +3. +6 to +3. Change. Final minus initial. The value is 3. 3 is the change for 1 chromium. I have 2. So 3 2s are 6. +2 to +4. +2 to +4. Change. 2. 2 is the change for 1. I have only 1. So 2 into 1 is 2. So after getting the n factors, what am I supposed to do? I'm supposed to crisscross these n factors. So this 2 will go here. This 6 will go here. Now. Balance all the atoms except hydrogen oxygen. So 2 2s are 4 chromium, 4 chromium, 6 tin, 6 tin. Now, balance oxygen with the help of water. How many oxygen atoms on this side? 7 2s are 14. How many oxygen atoms on this side? None. So add 14 water molecules on that side, which is oxygen deficient. Right? Now, hydrogen. 14 2s are 28. 28 hydrogen atoms on this side. No hydrogen on this side. So add 28 H positives on that side, which is hydrogen deficient. So the reaction is balanced. Am I clear, guys? You can again do one thing. Since all the stoichiometric coefficients are in even numbers. Since all the stoichiometric coefficients here are in even numbers. So you can divide throughout with 2. You can divide throughout with 2 also. No issues. Okay? All right. Let's take one example in basic medium as well. Let's take one example in basic medium as well. Mainly, if the question is asked, that will be asked in acidic medium. Still, I'm going to show you basic medium as well. What are the steps here in basic medium? Again, the first 3 steps are same. N factor of reactants. Then crisscross the N factors. Then balance all the atoms except hydrogen. Then balance negative charge with the help of OH negatives. Then balance oxygen with the help of H2. Now see, what do we do here? For example, I'm taking the reaction. Which reaction should I take? Balance medium, basic medium, right? Cl2 plus IO3 negative gives Cl negative plus IO4 negative. I have to balance this reaction in basic medium. What is my first step? First step is to get the N factor. See, oxidation state 0. Iodine here will be in +5 oxidation state when you calculate it. Chlorine in -1. Iodine, when you calculate, it will be +7. So 0 to -1. 0 to -1. Change is 1. 1 is the change for 1 atom. I have 2. So its N factor here is 2. +5 to +7. +5 to +7. Change. Change is 2. 2 is the change for 1 iodine. I have only 1. So 2 into 1 is 2. I got the N factors. After getting the N factors, crisscross them. This 2 comes here. This 2 comes here. Now, erase everything. Whatever things you wrote till now, erase them. Now, my dear students, balance all the atoms except hydrogen oxygen. So 4 chlorine, 4 chlorine. 2 iodine, 2 iodine. Okay? Got it till here? Now comes the point. Now comes the point. Balance negative charge with the help of OH negative ions. Balance negative charge with the help of OH negative ions. Do you see any charge here? No. Do you see charge here? Yes. -1. The net charge on this molecule is -1. So one molecule has got the charge -1. If one molecule has got the charge -1, 2 molecules will have -2. So on left side, the total negative charge is -2. On left side, the total negative charge is -2. Now what about right side? On 1 chlorine charge is -1. On 4 chlorine atoms, charge is -4. 1 IO4 carries charge -1. 2 will carry -2. So -4 -2 is -6. On left side, the total negative charge is -2. On right side, it's -6. So which side is negative charge deficient? Left side. How many negative charge deficiencies on left side? 4. So on this side, add 4 OH negatives. You have to add OH negatives to that side which is negative charge deficient. So I added 4 OH negatives on this side. Now balance oxygen with the help of water. So how many oxygen do you see here? 3 2s are 6 and plus 4. So on left side, there are 10 oxygen atoms. On right side, 2 4s are 8. Which side is oxygen deficient? Right side. How many oxygen deficiencies? 2. So add 2 water molecules on that side. Which side is oxygen deficient? So now it's a balanced chemical equation. You are not supposed to balance hydrogen. It's already balanced. With this, my redox reaction chapter is done and dusted.
Tell me once in the chats if all the things are like super clear till here. Yeah? Tell me once in the chats, my dear students, if all the things are like super clear till here. Perfect. I think let's take a small break, a tea break for my throat. Yeah. But I would want everyone to be back on time. A small tea break. Now we are going to start chemical bonding. Let's start at 3:30, okay? Okay, let's start at 3:30. Yeah? Okay? I'll see you all at 3:30 and I would want everyone to be back. Otherwise, there's no fun. And you know what? We started the class with 1400 live watching in the morning. Right now, only 570 students are here. With time, when I end the session, there will be not more than 200 students at that time. Not more than 200 students. And that's your real competition. All the others will come and join. They'll leave. They've got nothing to do with anything. The students who remain till the end, that's actually the real competition, guys. Okay? Chalo, I'll be seeing you in some time after the break. All right? See you. late OP, yeah? Yeah, I knew it. What's up? How are you all? Is everyone alive? Alive and ticking? Yeah? Is everyone alive? What's up? How are you all? Huh. Chalo, that's great. We won't die before NEET, huh? Chalo, shall we start? You know, this is the most important chapter of your complete chemistry. 4 questions are asked from this chapter. Yeah? How was the tea? The tea was fantastic. So 4 questions, my dear students, are asked from this particular chapter. Okay. So let me first of all tell you from which topics questions are asked in chemical bonding. Okay? From which topics questions are asked in chemical bonding. My dear students, the first topic, that is one of the basic topics, that is how do we draw the Lewis structures? Lewis structure, number 1. Second topic, that will be formal charge. Formal charge. Third topic will be Fajan's rules. Fajan's rules. Dipole moment. Dipole moment. Hybridization. Who is continuously calling me? Just a second, guys. Hello? 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 Guys, just give me a second. Just give me a second. Just give me a second. Hello? Auntie calling Sam. All well? Okay. तो बेसिकली मैं अभी लाइव क्लास में हूँ. मैं क्लास ख़त्म करके आपको कॉल करता हूँ, ठीक है? इट्स ओके. मैं क्लास ख़त्म करके बाद कॉल करता हूँ. ओके ओके सर. Okay, so after dipole moment, we'll be discussing about hybridization. Hybridization, that's again important. And after hybridization, you should know about shape and geometry. I mean, shape of the molecules through VSCPR. Through VSCPR theory. And at the end, it's going to be MOT, molecular orbital theory. So these are the topics from which questions are asked in the chapter chemical bonding, my dear students. So we'll be discussing all these topics one by one. So is everyone ready? Are you again fresh? Yeah? Tell me quickly in the chats, because this is a super important chapter. This is not something like which you will neglect or something. Everyone is like super ready? Okay, this is what I want in the chats. The Josh is supposed to be high. Sir, keep pace slow. Okay, why not? All right, people. Chalo then. Let's move on and let's discuss the first topic, that is how do we draw the Lewis structures. How do we draw the Lewis structures? Understand properly what I'm going to say. How do we draw the Lewis structures? My dear students, the molecule which I've taken here, that is carbon monoxide, CO, correct? The first thing always is to calculate the total valence electrons in the molecule. Total valence electrons in the molecule. Tell me, my dear students, how many valence electrons are there with carbon? Carbon has got 4 valence electrons. Plus, oxygen has got 6 valence electrons, right? So in total, my dear students, there are 10 valence electrons. 10 valence electrons means 5 valence electron pairs. One pair contains 2 electrons. One pair contains 2 electrons. So 10 valence electrons means 5 valence electron pairs. Correct? Now what do? We have to draw the structure of carbon monoxide. Let's say this is your carbon, this is your oxygen. Perfect. First thing, put a single bond in between. Single bond between means I have used 1 electron pair. I have in total 5 electron pairs. Out of 5 electron pairs, I have used 1 electron pair, right? So how many electron pairs I'm left with? 4. Now tell me, which one is more electronegative among the two? Oxygen is more electronegative among the two, correct? Now start filling the octet of more electronegative element. What I'll be doing? 1, 2, 3, 4, 5, 6, and 7, 8. Octet of oxygen is complete. How many electron pairs I had? 5. Out of 5, how many I have used? 1, 2, 3, and 4. 4 electron pairs I have used. I am left with 1. Give that 1 electron pair to carbon. Perfect. Give that 1 electron pair to carbon. I have used all the 5 valence electron pairs. Now, my dear students, is the octet of oxygen complete? Octet of oxygen is complete. 2, 4, 6, 8. But is the octet of carbon complete? Check it carefully. 2 and 2, that's 4. Only 4, right? So what do we need to do? Do one thing. Remove 1 electron pair from oxygen and instead of that, put a bond. Remove 1 more electron pair from oxygen. Instead of that, put a bond. Now check. How many valence electron pairs I had? 5. Out of 5, how many I have used? 1, 2, 3, 4, 5. 5 valence electron pairs I have used. Now check. Is the octet of oxygen complete? 1, 2, 3, 4, 5, 6, 7, 8. Done. Carbon. 1, 2, 3, 4, 5, 6, 7, 8. Done. Octet of both atoms is complete. Perfect. So this is the structure of your carbon monoxide. Now they'll ask you, what is the formal charge on carbon? What is the formal charge on carbon? How do we calculate formal charge on atoms? Tell me, when carbon is present in non-bonded state, isolated, when carbon is isolated, how many valence electron carbon has? In isolated state, carbon has 4 valence electrons. We know that. Number of valence electrons which carbon has in non-bonded state, that is 4. Minus how many valence electrons it has right now. How do you check it? Have a look. 1, 2. Out of these 2, select only 1. Out of these 2, select only 1. Out of these 2, select only 1. So 1, 2, 3, 4, 5. So 4 minus 5 is minus 1. So there is formal charge minus 1 present on carbon. Simple. Now formal charge on oxygen. Formal charge on oxygen. When oxygen is in non-bonded state, how many valence electrons oxygen has? 6 minus. How many it has right now? 1, 2, 3, 4, 5. So 6 minus 5 is plus 1. So formal charge on oxygen is plus 1. Understood? Let me take a few more examples so that it becomes like very, very, very clear to you. My dear students, for example, I am taking the molecule CO3 dinegative. CO3 dinegative. First of all, which one is the central atom? Carbon. Now, first thing, I need to calculate the total valence electrons. Carbon has 4 valence electrons. One oxygen atom has 6 valence electrons. Here we have 3 oxygen atoms.
There's a negative charge. If there is negative charge, add that. If there is negative charge, add that. So I'm adding 2 here. If there is positive charge, subtract that. Okay. Now, this is 4, 6, 3, 18. 18 plus 2. So 18 plus 2 is 20. 20 plus 4 is 24. So in total, we have got 24 valence electrons. That means how many valence electron pairs? 14 valence electrons means 12 valence electron pairs. Correct? Now, my dear students, we have got CO3 dinegative. Let's say this is carbon, this is oxygen, this is oxygen, this is oxygen, CO3. Put a single bond everywhere. Put a single bond everywhere. Now start filling the octet of more electronegative element. Start filling the octet of more electronegative element. That is oxygen. So start filling the octet of oxygen. Any oxygen you select. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. How many electron pairs I had? 12. Out of 12, how many I have used? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used all the 12 valence electron pairs. I've used all the 12 valence electron pairs. Octet of all the oxygen atoms is complete. But, is the octet of carbon complete? Check it out. 2, 4, 6. It's not complete. So select any oxygen of your choice, and remove a lone pair. Remove a lone pair. Instead of that, put a double bond. Now check. Is the octet of this oxygen complete? 1, 2, 3, 4, 5, 6, 7, 8. Done. Carbon. 1, 2, 3, 4, 5, 6, 7, 8. Done. These are already completed. Perfect. Now, my dear students, let me give some numbering. Let's call this as oxygen number 1. Let's call this oxygen number 2. Let's call this oxygen number 3. Now the first point. What is the formal charge on oxygen number 1? What is the formal charge on oxygen number 1? My dear students, when oxygen is present in non-bonded state, it has got 6 valence electrons. Minus. Right now, how many it has? 1, 2, 3, 4, 5, 6, and 1 here, 7. So 6 minus 7 is minus 1. So formal charge on this oxygen is minus 1. What is the formal charge on second oxygen? Oxygen, when in non-bonded state, 6 valence electrons. Minus right now, 1, 2, 3, 4, 5, and 6. So 6 minus 6 is 0. So there is no charge on this oxygen. If I talk about this particular oxygen, formal charge on oxygen number 3 is equal to, in non-bonded state, 6 valence electrons. Minus right now, 1, 2, 3, 4, 5, 6, and 1, 7. So 6 minus 7 is minus 1. Perfect. What is the formal charge on carbon? Formal charge on carbon. When carbon is present in non-bonded state, 4 valence electrons, minus. How many it has right now? 1, 2, 3, and 4. So 4 minus 4 is 0. So these are the formal charge on all the atoms. Understood how do we calculate formal charges? Say yes or no once in the chats, then I'll move on to the next topic. Say yes or no quickly in the chats, then I'll move on to the next topic. Quick, everyone. Is it clear? Yeah? Amazing, guys. I am moving on to our next topic. Which one is that? Let's do one thing. Let's discuss first the dipole moment. Let's discuss the term dipole moment. What is dipole moment first of all? What is dipole moment? Try to understand what exactly I'm going to do. My dear students, imagine that you have got 2 equal and opposite charges. 2 equal and opposite charges separated by certain distance. 2 equal and opposite charges separated by certain distance. Let me tell you, whenever you have got 2 equal and opposite charges separated by certain distance, this system of charges, this system of opposite charges separated by certain distance, I call this system of charges as dipole. I call this system of charges as dipole. And for the dipole, my dear students, what do we calculate? We calculate its moment. For the dipole, what do we calculate? We calculate its moment. And that dipole moment is represented by mu. Okay? That dipole moment is represented by mu. And this dipole moment is nothing but it is magnitude of charge on any1 multiplied by distance between the two. Multiplied by the distance between the two. Dipole moment is nothing but charge multiplied by this distance. And this dipole moment, my dear students, it's a vector quantity. It is a vector quantity. If it is a vector quantity, that means it will be having direction as well. That means with magnitude, it will be having some direction as well. And what is the direction? What is the direction? Let me tell you, my dear students, let me tell you, its direction is taken from less electronegative element to more electronegative element. Or I can say its direction is taken from positive to negative. Positive to negative in chemistry. Its direction is taken from positive to negative in chemistry, or less electronegative element to more electronegative element. Okay. Now, my dear students, this dipole moment, since it's a vector quantity, let me tell you the units of the SI unit of dipole moment is what? SI unit of dipole moment is what you call as d by. This is the SI unit of dipole moment. Perfect. Now let's try to understand what exactly I'm going to do here. Let's try to understand, people. Understand, guys. For example, I'm taking a molecule like this, HCl. It's a simple molecule. Now tell me which one is more electronegative. Chlorine. So it will attract the electron pair towards itself, due to which it gets delta negative, it gets delta positive. Correct? Now do you see I have got equal and opposite charges separated by certain distance? Yes. So can I call this as a dipole? Yes. Will it have any moment? Yes. Moment direction is from positive to negative. This molecule has got some dipole moment. This molecule has got some dipole moment. And that molecule, which will be having some net dipole moment, that molecule whose net dipole moment is non-zero, that molecule which will be having some net dipole moment, that molecule is called as the polar molecule. That molecule is called as the polar molecule. Similarly, guys, there is one more important thing. Remember, lone pair also contributes. Lone pair also contributes towards the moment. Lone pair also contributes towards the moment. And remember, the direction of moment due to lone pair, the direction of moment towards the lone pair is towards the lone pair. What does that mean? Have a look. For example, this is your NH3 molecule. You must be knowing, in case of NH3, there is one lone pair on nitrogen. There is one lone pair on nitrogen. Your Yavar sir is video calling me. Why is your Yavar sir video calling me? Yeah? You wanna see him? Do you see this, guys?
What's up, people? How's it going? Are you ready for tomorrow, guys?
They are not ready for tomorrow.
No. You guys are supposed to be ready. Okay? I'll be waiting for you guys.
He'll be waiting for you. Where?
And I will suggest you right now one thing. Close the session. Have studied enough. Okay?
Do you listen to him? Do you listen to my kid? Do you listen
Okay,
to?
guys.
Do you listen?
Take care. Bye-bye.
Do you listen? Do you listen to my child? Yeah.
What's up, bro? How's it going?
क्या दलील है?
Killing it, huh?
क्या चला मानो? उसका
पता नहीं क्या घर को.
ठीक.
मतलब
आने मैं लगी फिर टाइम ठीक ठाक.
होता.
मतलब सब 5 घंटे लगे मुझे भी.
सोच पड़ा.
अल्लाह की कसम.
लेकिन फुल एनर्जी है.
अच्छा चलो बेब करे कंटिन्यू है ना.
ओके.
चलो. All right. Moving on. So I was talking about lone pair. Lone pair also contributes towards moment, and the direction due to lone pair is towards the lone pair. That means this is a lone pair. The moment direction due to this lone pair is towards the lone pair. The moment direction due to this lone pair is towards the lone pair. If you look at this bond, it's between nitrogen and hydrogen, right? The moment due to this bond is from less electronegative to more electronegative. The moment due to this bond is from less electronegative to more electronegative. Less electronegative to more electronegative. Got it? Perfect. Perfect, people. Is this clear? Did you understand? Before showing you its application part, I need to tell you one thing. Okay? You just remember it for now. Whatever I'm telling you, whatever I'm going to tell you now, remember it for now. You'll understand it in some time. My dear students, as I told you,
If you have got any molecule whose net dipole moment is non-zero, you call the molecule as polar. If you have got any molecule whose net dipole moment is zero, you call it as non-polar. You call it as non-polar. Now the third point, whenever you see any molecule of the type Ab2L0, what is meant by Ab2L0? I'll let you know in some time. First you remember it. Ab2L0. If you have a molecule of the type Ab3L0, if you have a molecule of the type Ab4L0, if you have a molecule of the type Ab5L0, similarly, you have got Ab6L0, right? Ab6L0. You have got Ab7L0. You have got Ab3L2, sorry, Ab2L3. You have got Ab4L2. All these molecules, which will be of these types. How do we check the type of the molecule? That's something I'll teach you in some time. Remember it for now. Whenever you see molecules of these types, their net dipole moment directly you will be taking as zero. So these molecules are going to be non-polar in nature. Non-polar in nature. Perfect. One more thing, guys. Whenever you are given with 3 to 4 molecules, whenever you are given with some molecules, and you have to arrange them on the basis of net dipole moment. Whenever you'll be having some molecules and you will have to arrange them on the basis of their dipole moment, the first thing you will do is check the electronegativity difference between the atoms. More the electronegativity difference between the atoms, more is going to be the dipole moment. Number one. Number two, more the distance between the atoms. More the distance between the atoms, more is going to be the dipole moment. Right? One more thing, people. These are two things which I want every one of you to remember. Now see how I'm going to utilize them in the questions. Just this slide you have to remember and you are sorted for life. Let me show you how. We'll start with this particular slide. Start from here. Here the bond is between O and H. Here it's between N and H. In the periodic table, which one is most electronegative element? Fluorine followed by oxygen followed by nitrogen. Right? Now, whenever you have to compare molecules as per the dipole moments, first priority goes to electronegativity difference. Now, my dear students, bond is between OH. Here the bond is between OH. Here the bond is between NH. Where is the electronegativity difference more? Electronegativity difference is more here. More the electronegativity difference, more the dipole moment. More the electronegativity difference, more the dipole moment. More the electronegativity difference, more the dipole moment. NH bond, PH bond. OH bond, SH bond. More the electronegativity difference, more the dipole moment. Simple. Leave this as such. I'll be showing this in 2 to 3 minutes. Before that, talk about this one. HF, HCl, HBr, HI. More the electronegativity difference, more the dipole moment. Okay, look at this one. Do you see the CCl bond? Less electronegative to more electronegative. Less electronegative to more electronegative. Both the moments are going in the same direction. Now say, less to more. Equal and opposite direction. So which one will have more dipole moment? This one. Now NH3, NF3. NH3 structure I told you a few minutes back. NH3 structure I showed you a few minutes back. Due to lone pair, towards the lone pair. Less electronegative to more electronegative. Less to more. Perfect. Now NF3. Less electronegative to more electronegative. Less to more electronegative towards the lone pair. Now do you see all these moments are technically going in the same direction? Here all are not going in the same direction. I will say there will be some cancellation here, due to which net dipole moment of this molecule will be more. So remember, NH3 has got more dipole moment, more net dipole moment than what? Than NF3. Perfect. So all these 3 questions are clear with this. And let's move on now to this one. This first question. Few minutes back I told you, more the electronegativity difference, more the dipole moment. Similarly, more the distance, more the dipole moment. See, dipole moment is equal to Q multiplied by A. So dipole moment is directly proportional to distance. More the distance, more the dipole moment. More the charge, more the dipole moment. More charge will come due to more electronegativity difference. Right? Now understand this particular question. This is important. And remember this. First of all, this is CH3F. So the bond is between C and F here. The bond is between C and Cl here. Let me call this as number 1. Let me call this as number 2. This is number 3, number 4. So let's compare these two first. When I compare these two, electronegativity difference between C and F is more than that of C and Cl. So as per charge factor is concerned, dipole moment of 1 should be more than that of 2. But at the same time, there is one more factor, distance factor. Remember, CCl bond length is more than that of CF bond length. CCl bond length is more than that of CF bond length, due to which, as per distance factor, 2 dominates over 1. As per distance factor, dipole moment of 2 should be greater than that of 1. As per charge factor, dipole moment of 1 should be greater than 2. And in this particular case, distance factor dominates. In this particular case, distance factor dominates. Perfect. So remember, the order here is 2, then 1, then 3, then 4. Okay? Remember this particular case, take a star on it. Right? Perfect, guys? Who is this bloody spammer? Dude, you can get the hell out of my class. What are you doing here? Who has sent you here? Done, people? So this is the case where distance dominates over charge. This is the case where distance dominates over the electronegativity difference. There were some spammers, I blocked them. Okay? So remember this particular case, guys. Okay, one more example. I believe you would have studied GOC somewhere. You know which is electron deficient. Sorry, you know which is electron donating, which is electron withdrawing. You know that, I believe. Right? Now have a look. Understand. CH3. CH3 is electron donating group. CH3 is electron donating group. If CH3 donates electrons, when it donates electrons, can I say this will technically get delta positive and here delta negative? And the moment is from positive to negative. Here also it will be from positive to negative. So they are cancelling each other. Net dipole moment here will be 0. Right? Now, CH3, it is donating. So delta positive, delta negative. So from positive to negative. See, one vector is going in this direction and one vector is going in this direction. So at an angle of what? 120. Perfect. Look here. Positive to negative. One vector is going downwards. One vector is going in this direction. At an angle of what? At an angle of 60. Can I say lesser the angle between two vectors. More is the resultant. Right? So where would be the resultant more? In the third case. So dipole moment, net dipole moment in the third will be greater than 2, will be greater than 1. This is the order. Okay? This is the order, my dear students. Am I clear? Is this clear to everyone? Yeah? Someone is asking why distance dominates. Don't ask me why at this time. You have 12 days left, bro. Whatever I'm telling you, just remember it. Okay? Don't ask for the explanations at this point. If you wanted explanations, you would have come to this channel before 1 year. Okay? Right now, whatever I'm telling you, just remember it. Just remember it. If you want to score, well, don't ask me why, what, how. That time is over right now. Okay? Let's move on to the next one. See guys, this NO2, nitro group is electron withdrawing. Nitro group is electron withdrawing. Okay? This is withdrawing. This is donating. When it donates, it gets delta positive, delta negative. So positive, negative. This is withdrawing. When it withdraws, it gets delta negative, delta positive. So positive, negative. One vector is pointing in this direction. One vector is pointing in this direction. Right? At an angle of 120. Positive to negative. One going downwards, one in this direction at an angle of 60. Right? Positive to negative. Both in the same direction, angle 0. So lesser the angle between two vectors, more is the resultant. So P will have more dipole moment followed by 2, followed by 1. This is the order of the dipole moment. I believe you can easily solve these sort of questions. Tell me about this one. Let's call this as A. Let's call this as B, let's call this as C, and let's call this as D. You have to give me the order of the net dipole moments. My dear students, look carefully. Look carefully. This is CF bond. Less electronegative to more electronegative. Let's say the magnitude of this vector is x. From less electronegative to more electronegative. This again CF. Its magnitude will be x. Less to more. Its magnitude also will be x. Now, if you look carefully, this vector and this vector, one is going in this direction. One is going in this direction. This is x. This is x. At an angle of 120. At an angle of 120, the resultant will be in this direction and resultant will be also x. This is something I believe you would have studied in physics. This is one vector, this is one more vector. At an angle of 120, the resultant will be also x. The resultant will be also x. Already in this direction there was x. Now there is one more x. So x and x adds up. So net dipole moment here magnitude is 2x. Okay? Right? Now guys look here. Less electronegative to more electronegative. Less to more. Less to more. These two vectors, one going in this direction, one going in this direction, right? They are at an angle of 120. So this and this, they are at an angle of 120. Let's say this is x, its magnitude also x. These two are at an angle of 120. So resultant is in this direction, that will be also x, and this x cancels out because they are opposite, so net is 0. Net is 0. Look at the next one. This is less to more, less to more, less to more. If this is x, this is also x, this is also x, because everywhere there is CF bond. So this is cancelled out, net is x, right? Less to more, cancels out, resultant is 0. Now give the order. 2x, x, 0, 0. So A will have maximum dipole moment, net dipole moment, then comes C, and B and D, their dipole moment is 0, that is equal. Right? B and D have got same dipole moment, that is 0. This is the order here. I believe this sort of a question you can easily solve. From now on. Am I clear with this? Everyone? Everyone in the chats, people? Yeah? I hope you will be in a position to solve these sort of questions if it comes in your exam. Now, my dear students, there is one more type of the question, frequently asked question. That is Fajan's rules. I'm not going to go into the depth. I'll tell you few things to remember so that you can solve the questions based on Fajan's rules, right? Understand what I'll be doing. If I talk about the Fajan's rules, my dear students, with the help of Fajan's rules, we can compare covalent character in ionic bonds. For example, there will be 3-4 molecules given to you. And they'll ask you which one has got more covalent character, which one has got less covalent character. You'll get questions like that also. For that, you have to remember two things. That's all. What is that? See, I will say covalent character in an ionic bond is directly proportional to two things. It is directly proportional to the polarizing power of cation. I'm writing positive. Positive means cation. Also, the same covalent character in an ionic bond is directly proportional to polarizability of anion. So how many terms came? 2 terms. One is polarizing power of cation, one is polarizability of anion. Now, one more thing which I want you to remember. What is that? The term polarizing power of cation, it is directly proportional to the charge on cation, inversely proportional to the size of cation. Similarly, polarizability of anion. It is directly proportional to charge of anion, also directly proportional to size of anion. Okay. One more thing, my dear students. Covalent character is inversely proportional to ionic character. These are few pointers which I want you guys to remember directly.
Do you understand? Covalent character directly proportional to polarizing power of cation, directly proportional to polarizability of anion. Now, polarizing power of cation is directly proportional to charge of cation, inversely proportional to size of cation. Right? Similarly, polarizability of anion is directly proportional to charge on anion, also directly proportional to size of anion. Now, we are sorted. We are done. We can easily solve the questions. How? Have a look. Tell me the answer of this question. Arrange the following on the basis of the polarizing power of cation. Arrange the following on the basis of polarizing power of cation. My dear students, polarizing power of cation is directly proportional to charge on cation. More the charge on cation, more the polarizing power. More the charge on cation, more the polarizing power. Done and dusted. Right? Okay. Now the charge on every cation is same. Talk in terms of size. Charge of every cation is same. Talk in terms of size. This is lithium, sodium, potassium, rubidium, cesium. Lithium, sodium, potassium, rubidium, cesium. They belong to the same group. Down the group, size increases. Right? Polarizing power is inversely proportional to size. Lesser the size, more the covalent character. Lesser the size, lesser the size, more the polarizing power of cation. Right? Perfect. Lesser the size, more the polarizing power of cation. Again, they belong to second group. And down the group, size increases. Beryllium, magnesium, calcium, strontium, barium. Down the group, size increases. So beryllium has got lesser size. Lesser size means more polarizing power. Simple. Simple. Simple, people. Now, you can have cations like this as well. Zinc dipositive, cadmium dipositive, mercury dipositive. Zinc is 3D element. This is 4D. This is 5D. Remember one thing directly, my dear students. When you move from 3D to 4D and 4D to 5D, the polarizing power of cations increases. The polarizing power of cations increases. Remember it directly. When you move from 3D to 4D, 4D to 5D, polarizing power of cations, it's going to increase. It's going to increase. It's going to increase. And if you got it, tell me the answer of this question. See, arrange the following on the basis of polarizability. Polarizability. Polarizability is defined for anions. Polarizability is defined for anions. And polarizability is directly proportional to charge on anion, directly proportional to size of anion. More the charge on anion, more the polarizability. More the charge on anion, more the polarizability. Simple. Simple. Right? The charge on every anion is same. So talk in terms of size. More the size of anion, more the polarizability. More the size of anion, more the polarizability. More the size of anion, more the polarizability. Right? Do you understand? Now, arrange the following on the basis of covalent character. Arrange the following on the basis of covalent character. Arrange the following on the basis of covalent character. Understand, people, what I'm going to do. See, this is basically zinc dipositive Cl negative. This is cadmium dipositive Cl negative. Hg dipositive Cl negative. Right? See, Cl negative everywhere is same. So I cannot decide on the basis of Cl negative. I have to decide on the basis of cation. We have to give the order of covalent character. And you know, covalent character is directly proportional to polarizing power of cation. Now, this is 3D, this is 4D, this is 5D. Its polarizing power is maximum. More the polarizing power of cation, more the covalent character. Simple. This is the order of covalent character. Yeah? Look at this one. Zinc dipositive, cadmium dipositive, Hg dipositive. This is the order of covalent character. Now, Li positive, F negative, Na positive, F negative, K positive, F negative, Rb positive, F negative, cesium positive, F negative. So F negative everywhere same. Talk in terms of cation. Even the charge on every cation is same. Charge on every cation is same. Talk in terms of size. Lesser the size of cation, more its polarizing power. So more polarizing power of this cation is more because its size will be least. Lithium, sodium, potassium, they belong to same group. Down the group, size increases. So Li positive will have least size. Lesser the size of cation, more will be its polarizing power. And more the polarizing power of cation, more is going to be the covalent character. Right? Similarly, this is B dipositive. This is BeCl, B dipositive here also, B dipositive here, B dipositive here. So you cannot talk in terms of cation. You have to talk in terms of anion. Talk in terms of anion. F negative, Cl negative, Br negative, I negative. Right? Charge on every anion is same. Talk in terms of size. More the size of anion. I negative has got maximum size. Fluorine, chlorine, bromine, iodine. They belong to same group. Down the group, size increases. Size of this anion is maximum. More the size of anion, more the polarizability of anion. More polarizability of anion means more covalent character. So this is the order of covalent character. Got it? Right, people? Am I clear? Am I clear? Am I clear? Am I clear? Now, this is also one special case. Understand. This is Cu positive, Cl negative. This is Na positive, Cl negative. So leave Cl negative aside. Talk in terms of Cu positive. Talk in terms of cation, Na positive. Talk in terms of Na positive. Now, my dear students, if I ask you, what is the electronic configuration of copper positive? Its electronic configuration will be argon followed by 3d10 configuration. Actually, it was 4s1 also, but it's Cu positive, so one electron out. So it's argon followed by 3d10. Na positive. Sodium's actual configuration is neon 3s1, but it's Na positive, so take one electron out. So it is just Na. Whenever you see this sort of a configuration means noble gas configuration followed by D10 configuration. Whenever you see this configuration, noble gas configuration followed by D10 configuration, this configuration is called as pseudo inert gas configuration. It's called as pseudo inert gas configuration, right? Pseudo inert gas. This is just inert gas configuration. This is just inert gas configuration. Remember, polarizing power of that cation, which shows pseudo inert gas configuration. Polarizing power of that cation, which shows pseudo inert gas configuration, is more. So polarizing power of this cation is more. If polarizing power of this cation is more the polarizing power, more the covalent character. Done? Simple. Now, my dear students, now comes one more term here, which all of you love, that is your hybridization. I'm not going into the details of hybridization. I'll just show you how do we calculate hybridization of different molecules. I'll just show you how do we calculate hybridizations of different molecules. See guys, what do we do? There is basically a method by means of which we calculate hybridization. One method is there. That method is called as the steric number method. That's called as steric number method. There's a method with the help of which we calculate hybridization. The method is called as steric number method. The method is called as steric number method. Now, what is steric number basically? Steric number is nothing but it is the number of sigma bonds. Number of sigma bonds that the central atom forms plus the number of lone pairs which are there on central atom. I'll show you how to calculate them. First of all, steric number. It is the sum of the number of sigma bonds that the central atom forms plus the number of lone pairs which are present on the central atom. How do we calculate these sigma bonds and lone pairs? I'll show that in some time, but before that, try to understand. Remember, when the steric number comes out to be 2, hybridization involved is sp. When the steric number comes out to be 3, hybridization involved is sp2. When the steric number comes out to be 4, hybridization involved is sp3. When the steric number comes out to be 5, hybridization is sp3d. And when the steric number comes out to be 6, hybridization is sp3d2. When the steric number comes out to be 7, hybridization is sp3d3. Okay? Right? Now, one more thing. When the hybridization is sp, the geometry which is predicted through hybridization, that is linear. Okay? sp2, trigonal planar geometry. sp3, geometry predicted through hybridization, that is tetrahedral. sp3d, trigonal bipyramidal. sp3d2, octahedral. sp3d3, pentagonal bipyramidal. And at the same time, remember, one more question can be asked. Which d orbital is involved in sp3d hybridization? Remember, it is dz square that's involved in this hybridization. Which d orbital is involved here? It is dx square minus y square and dz square. Which d orbital is involved here? It is dx square minus y square, comma dz square and dxy. Okay? Now people, let me show you where do we use all this in the questions? Okay. Let's have a look now. Let's try to understand. Let's try to understand, guys. I'll be starting with a simple molecule. For example, CH4. A very simple molecule this is. Which one is the central atom? Carbon. How many valence electrons carbon has? 4. Right? How many surrounding atoms carbon has? 4. Surrounding atoms of 4. Remember people, number of surrounding atoms is equal to number of sigma bonds. Number of surrounding atoms is equal to number of sigma bonds. So basically, valence electrons with carbon were 4, and this carbon is forming 4 sigma bonds. If carbon had 4 valence electrons, and it is utilizing all the 4 valence electrons to form 4 sigma bonds, will there be any lone pair on carbon? No. Can I calculate steric number? Yes. How? Sigma plus lone pair. That's 4. When steric number is 4, hybridization is sp3. Okay. Now, what will be the type of the molecule? Let me show it to you right here only. Type of the molecule. If A is the central atom, how many sigma bonds it's forming? 4. So it is AB4. How many lone pairs are there? 0. The type of the molecule is AB4L0. Understood? Let me take few more molecules. For example, I have got a molecule like this, XeF4. Let's say XeF4. This xenon is the central atom. How many valence electrons it has? 8. How many? 8. How many surrounding atoms? 4. So 4 sigma bonds. Out of 8 valence electrons, 4 valence electrons have been used to form 4 sigma bonds. So 4 will be left as such on xenon in the form of how many lone pairs? 1, 2 lone pairs. So 4 sigma, 2 lone pairs. Steric number. Sigma plus lone pairs. 4 plus 2, 6. Hybridization. sp3d2. Type of the molecule. AB4L2. AB4L2. Okay. Understood? Okay. Now, my dear students, for example, you have got the molecule like this. Let's say you have got something like this. NO2 negative. NO2 negative. Nitrogen. How many valence electrons? 5. But there is a negative charge as well. So add this. So 5 plus 1, 6. How many surrounding atoms? 2. So 2 sigma bonds. Now, when oxygen is the surrounding atom, what do you do at that time? When oxygen is the surrounding atom, see, I have to calculate lone pairs. When oxygen is the surrounding atom, what do we have to do at that time? I'm just telling you one thing by means of which you can remember. See, 6 valence electrons, 2 oxygen atoms, 6 valence electrons which nitrogen had, right? And there are 2 oxygen atoms. Oxygen forms generally which bond? Double bond, right? So imagine as if one oxygen is forming 2 bonds with nitrogen. So 2 oxygens will form 4. Guys, do you understand what I'm trying to say? I'm just telling you the trick by means of which you can remember it. When oxygen is the surrounding atom, see, nitrogen has how many valence electrons? 6. Imagine one oxygen is forming 2 bonds. So 2 oxygen will form 4 bonds. 2 oxygen atoms will form 4 bonds with nitrogen. Right? How many valence electrons nitrogen had? 6. How many bonds it has to form technically? 4. So out of 6 valence electrons, 4 should be used. Right? So that means 2 valence electrons will be left as such in the form of a lone pair. So steric number. 2 plus 1, 3. Hybridization. sp2. Type of the molecule. AB2L1. Do you understand? For example, I've got the molecule like this. Let's say you've got the molecule I3 negative. I3 negative, I can write it as II2 negative. II2 negative. Talk about this iodine. How many valence electrons? 7. There is a negative charge. So 7 plus 1 makes it 8. How many surrounding atoms? 2. So 2 sigma bonds. Out of 8 valence electrons, 2 valence electrons are used to form 2 sigma bonds. So 6 are left as such in the form of 3 lone pairs. So how many lone pairs? 3. Steric number. Sigma plus lone pairs. 3 plus 2, 5. Hybridization. sp3d. Type of the molecule. AB2L3. Understood? Am I clear? Am I clear?
Let me take a few more molecules. For example, you have got ClF3. Valence electrons which chlorine has, 7. Surrounding atoms, 3. Lone pairs, 7 minus 3 is 4, 4 by 2 is 2. The same thing, okay? Steric number, 3 plus 2, 5. Hybridization, sp3d. Type of the molecule, ab3l2. Someone was, in the comments, someone was asking about XeOF4. XeOF4. Perfect, XeOF4. Let me make its rough structure. Xe, oxygen forms double bond. And there are 4 fluorines, correct? 4 fluorine atoms, like this. So xenon, how many valence electrons? 8. How many surrounding atoms? 4 plus 1, 5. So sigma is 5. Perfect. Out of 8 valence electrons, how many have been used? 1, 2, 3, 4, 5, 6. Out of 8, 6 have been used. So 2 are left as such in the form of a lone pair. So 5 plus 1 is 6. So steric number is 6. If steric number is 6, hybridization sp3d2. Geometry, the type of the molecule, AB5L1. I think you can easily calculate hybridization of each molecule from now on. Yeah? Am I clear, guys? Am I clear now? Is every single thing clear till here? Honestly, tell me in the chats. Someone is talking about XeO2F2. Chalo, let me try that too. XeO2F2. Huh? If you have XeO2F2, so there are 2 oxygen atoms. XeO2F2. So if you have got XeO2F2, xenon, how many valence electrons? 8. How many sigma bonds? 2 plus 2, 4. Right? How many lone pairs? Out of 8 valence electrons of xenon, how many are used? 1, 2, 3, 4, 5, 6. Wait, XeO2F2. F2 means there's only 2 fluorine. This is XeO2F2. Okay. Out of 8 valence electrons, how many are used? 1, 2, 3, 4, 5, and 6. So out of 8, 6 are used. So 2 are left as such in the form of a lone pair. So steric number 4 plus 1, 5. Hybridization sp3d. Type of the molecule ab4l1. Am I clear now? Yes? Quick in the chats. Quickly in the chats, people. Quickly in the chats. Everyone. All right. Now, guys, now comes your VSEPR theory, which gives us the information about the shape of the molecule. Which gives us the information about the shape of the molecule. Which gives us the information about the shape of the molecule. Okay. Now, how do you predict shapes of different molecules? How do you predict shapes of different molecules? Try to understand what exactly I'm going to do. Let me first of all talk about those molecules which have steric number 3. Steric number 3 means hybridization is sp2. What is the geometry predicted through hybridization? Geometry predicted through hybridization is trigonal planar. I'm going to first of all talk about these molecules. Guys, try to understand. Be very cautious now, okay? This is important. This is important. My dear students, how many possibilities are there? Someone is asking me how to know the valence electrons. How to know the valence electrons? Just remember them. What are you asking me? How to know the valence electrons? Someone is constantly, sir, percentage purity, percentage. Go to my mole concept chapter. Study percentage purity if you want to study, okay? All right, look here now. I'm first of all talking about those molecules which have got steric number 3. Steric number 3 means what is the geometry which is predicted through hybridization? That is trigonal planar, right? Now the point is, how many ways are there? How many ways are there by means of which? How many ways are there by means of which steric number can be 3? There is the first possibility. Steric number can be 3 if sigma bonds are 3 and lone pairs are 0. This is the first possibility to have steric number 3. Second possibility, sigma bonds can be 2, lone pairs can be 1. This is the second possibility, wherein steric number can be 3. 2 plus 1 is 3. Okay. Now, my dear students, if sigma bonds are 3, lone pairs are 0, what is the type of the molecule? It's AB3L0. It is AB3L0. Remember, when the central atom does not have any lone pair, when the central atom does not have any lone pair, remember, whatever geometry is predicted through hybridization, whatever geometry is predicted through hybridization, that will be the actual shape. So right now, central atom does not have any lone pair. So geometry predicted through hybridization is planar. So shape will be also planar. Shape will be also planar. How it looks like? This is your AB3L0. This is A, this is B, this is B, this is B. So this AB3L0, this shape is what you call as trigonal planar shape. So all these 4 atoms are on board, are on one plane. And the angle here will be how much? Angle here will be 120 degree. Perfect. Now, 2 sigma bonds, 1 lone pair. The type of the molecule will be AB2L1, right? So central atom has a lone pair. Central atom has a lone pair. Now shape will be different as what we had predicted through hybridization. Through hybridization, we had predicted planar. But in reality, shape will be different. How am I going to make the shape? In order to make the shape, make the geometry once again. Geometry was like this. Geometry was like this. But this is AB3L0 type. What do I have to make? AB2L1. So do one thing. Remove one of the bond pair. Instead of that, put a lone pair. Okay. Now hide the lone pair. How it looks like? It looks like bent shaped. So the shape is bent. So the molecule which is of the type, AB2L1, it will be bent shaped. Okay. Perfect. Now, my dear students, let me talk about those molecules which have steric number 4. Steric number 4. Steric number 4 means hybridization sp3. Hybridization sp3. That means geometry predicted through hybridization is tetrahedral. Geometry which is predicted through hybridization, that is tetrahedral. Now understand. Tell me one thing. How many possibilities are there to have steric number 4? The first possibility is 4 sigma bonds, 0 lone pair. This is the first possibility. Second possibility is 3 sigma bonds, central atom forms, 1 lone pair. Third possibility is 2 sigma bonds, which the central atom forms, and 2 lone pairs. If 4 sigma, 0 lone pair. The type of the molecule will be AB4L0. The type of this molecule will be AB4L0. Central atom does not have any lone pair. If central atom does not have any lone pair, whatever is the geometry which is predicted through hybridization, that's going to be the actual shape of the molecule. So shape of the molecule here will be tetrahedral. Shape will be tetrahedral, right? And how it looks like? It looks like this. This is A, this for example B, this is one more B, this is one more B, right? And this one more B. This particular shape is called as tetrahedral, and in case of tetrahedral geometry, the bond angle is kept as 109 degree 28 minutes. Okay? Perfect. Similarly, my dear students, if sigma are 3, lone pairs are 1. So the type of the molecule will be AB3L1. AB3L1. Now the central atom has lone pair. So whatever geometry we predicted through hybridization, that is not going to be the actual shape. We have to make the actual shape. How? In order to make the actual shape, make the geometry again. Make the geometry again. Once I make the geometry, this was AB4. This was AB4. But what do I have to make? I have to make AB3. AB3L1. So what I'll be doing, I'll be removing one bond pair, and instead of that, I'll be keeping a lone pair. This is your AB3L1. Now, if you hide this lone pair, this shape is called as pyramidal shape. This is called as pyramidal shape. Okay. Now, this will be AB2L2. AB2L2. Before AB2L2, what did I make? I made AB3L3. Sorry, I made AB3L1. I made AB3L1. So what do I have to make? I would make now AB2L2. Again, in order to make the actual shape, make the geometry once again. This was AB4. The geometry was like this. The geometry was like this. Now, do one thing. Remove 2 bond pairs and place 2 lone pairs. Place 2 lone pairs. When you hide these lone pairs, it is again bent shaped, or you call it as V-shaped. The shape of this molecule is V-shaped or bend-shaped. Okay? I believe this is also clear. Yes? Now, my dear students, I'm going to talk about those molecules which have steric number 5. I'm going to talk about those molecules which have steric number 5. Steric number 5. That means geometry. That means, first of all, hybridization, sp3d. Geometry predicted through hybridization. What is that? That will be trigonal bipyramidal. Now tell me what all possibilities are there to have steric number 5. What all possibilities do we have to have the steric number 5? Number 1. The first possibility is 5 sigma bonds, 1 lone pair. Second possibility, 4 sigma bonds. Sorry, this was 0 lone pair. 4 sigma bonds, 1 lone pair. Third possibility, 3 sigma bonds, 2 lone pairs. Okay. Fourth possibility, 2 sigma bonds, 3 lone pairs. These are all the 4 possibilities by means of which steric number can be 5. Because steric number is sigma plus lone pair, sigma plus lone pair. Okay. Now people try to understand. In the first case, the type of the molecule is AB5L0, right? Central atom does not have a lone pair. So whatever is the geometry predicted through hybridization, same is going to be the shape. So shape is also trigonal bipyramidal. How it looks like exactly? AB5L0. This is A, this is for example B, this is one more B, this is one more B. So all these atoms are present on the same plane. All these atoms are present on the same plane. Now perpendicular upwards there will be one B, perpendicular downwards there will be one more B. Okay, there will be one more B. Now this particular bond, which is perpendicular, what do you call it? You call it as axial bond. Axial. This is also axial bond. Okay, this is what you call as equatorial bond. Equatorial bond, right? I believe this is also clear. Tell me quickly. Is it clear? Is it clear, my dear students, everyone? Yes? Okay, the next one is of the type AB4L1. AB4L1. Let me directly make the shapes now. AB4L1 will be seesaw shaped. Seesaw shaped. How it looks like? AB4L1. Let me make it here. This is A. This is B. This is B. At the equatorial position, there's a lone pair. This is B. This is B. At axial positions. This shape is called a seesaw shape. Right? Similarly, AB3L2. AB3L2. It has got T shape. It is T-shaped. It is T-shaped. How it looks like? This is A, right? This is a lone pair at equatorial position. Lone pair at equatorial position. This is a bond pair at the equatorial position. At axial, there is one bond pair. Axial, there is one more bond pair. Now, if you hide these two lone pairs, it looks like a T-shaped one. This molecule is of the type AB2L3. AB2L3, how it looks like? AB2L3 will be linear shaped. Linear. So basically, if this is A, at all the 3 equatorial positions, there'll be 3 lone pairs. There'll be lone pairs at equatorial positions, perpendicular upwards, perpendicular downwards. It'll be B. When you hide these lone pairs, you get linear. It's a linear shape basically. It is linear shape. Right? So this was steric number 5. Now what is left? Steric number 6 is left, right? Steric number 6. Steric number 6 means hybridization sp3d2. Right? Hybridization sp3d2. Geometry which is predicted through hybridization, that's octahedral. That is octahedral. Now you tell me what all possibilities are there to have steric number 6. The first possibility is if there are 6 sigma bonds, 0 lone pair. This is the first possibility. Second possibility is 5 sigma bonds, 1 lone pair. Third possibility which we have, 4 sigma bonds, 2 lone pairs. Type of the first molecule will be AB6L0. Type of the second molecule will be AB5L1. This will be AB4L2. AB4L2. Now, in the first case, since central atom does not have any lone pair, so whatever is the geometry predicted through hybridization, that's going to be the shape. So shape is also octahedral. Shape is also octahedral. How it looks like? AB6L0, right? This is A, this is B, this is B, this is one more B, this is one more B, and all these are present on the same plane. Perpendicular upwards, there is one more B. Perpendicular downwards, there is one more B. This shape is called as octahedral shape. Now they can ask you about bond angles here as well. They can ask you about the bond angles as well, okay? All right, AB5L1. AB5L1, its shape will be square pyramid. Its shape will be square pyramidal. And how it finally looks like, let me make the shape directly. This is A, for example. This was B. This one more B, one more B, one more B, right? Let's say you have kept a lone pair here. All right, and perpendicular upwards, there is B. So it is square, and at the top, there is a pyramid formation. So it's square pyramidal. Now AB4L2 will be square planar. It will be square planar. And how it finally looks like, this is A, this is B, this is B, this is one more B, one more B. All are present on the same plane. And perpendicular upwards, there is lone pair, here also lone pair. Hide the lone pairs, it's square planar, right? So my dear students, these are the possible things which we have. Okay? Perfectly done? Can you tell me the answers of these questions now? Just a second. Tell me guys, what is the shape of this molecule? AB4L0. It will be tetrahedral. AB4L2. 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 Square planar. Its shape. AB2L1. AB2L1. It's bent. AB2L3. Linear. Right? Similarly, AB3L2. Linear. Wait, what did I write here? AB2L3. AB2L3 is linear. Okay. AB2L3 is linear. What was here? Here we have got AB3L2. Sorry. AB3L2. Few minutes back. AB3L2 means T-shaped. AB5L1. It will be square pyramidal. Square pyramidal. AB4L1 will be seesaw. Yeah, that's it. Done, done, done. So I hope whenever a question comes from shape, geometry, hybridization, everything, you should be in a position to solve it. Got it? Now, guys, there is one more question that's asked. That is question based on bond order. Question based on bond order. But I'll be giving you the trick also. I'll be giving you the trick to calculate bond order also. But before that, I'll show you the actual way by means of which bond order is calculated. Because it is not only questions will be based on bond order. Some questions will be based on calculate the anti-bonding electrons, calculate the bonding electrons, etc., etc. Okay, I'll show it to you. The actual stuff first, then I'll give you the trick also. First of all, your molecular orbital theory, my dear students. What molecular orbital theory says? Molecular orbital theory says that atomic orbitals of the bonding atoms. Atomic orbitals of the bonding atoms. Atomic orbitals of the bonding atoms. They combine to form what? They combine to form molecular orbitals. Atomic orbitals of bonding atoms, they combine to form what? To form molecular orbitals. Number of atomic orbitals combined is equal to number of molecular orbital forms. Number of atomic orbitals combined is equal to number of molecular orbitals formed. Let's say here two atomic orbitals of bonding atoms are combining. So two molecular orbitals will be formed. One will be called as bonding molecular orbital. One will be called as anti-bonding molecular orbital. Okay. Remember, energy of bonding molecular orbital is less, stability is more. Energy of anti-bonding molecular orbital is more, stability will be less. Okay. Bonding molecular orbital you represent either with sigma or pi. Anti-bonding molecular orbital you represent with sigma star or pi star. Okay. Perfect. Now, my dear students, for example, I've got two atoms. Now they have to form a molecule. Two atoms, they have to form a molecule. Perfect. Two atoms have to form a molecule. Sorry. Two atoms have to form a molecule. So if two atoms have to form a molecule, first of all, these two atoms must come close. When they come close, their atomic orbitals will combine. They will lead to the formation of molecular orbitals. They lead to the formation of what? Molecular orbitals. Now, once molecular orbitals are formed, then we have to arrange those molecular orbitals on the basis of their increasing energies. We have to arrange molecular orbitals on the basis of their increasing energies. And my dear students, this is the increasing energy order of the molecular orbitals, and this order is valid for those species which have got total number of electrons up to 14. So once molecular orbitals are formed, then we have to arrange these molecular orbitals on the basis of their increasing order of their energies. And this is the increasing order of the energies of the molecular orbitals. And this order is basically followed by those molecules which have total number of electrons less or equal to 14. Right? But if there's a molecule which have got total number of electrons more than 14, greater than 14, then this particular order is followed. You can take the screenshots first, or anyways, you are going to get the PDF also, right? And my dear students, once we arrange these molecular orbitals on the basis of increasing energies, then what are we supposed to do? We are supposed to fill electrons in these molecular orbitals. As per Hund's rule, as per Pauli's exclusion principle, as per Abbas principle. We are supposed to fill electrons in these molecular orbitals. And remember, once we are done filling the electrons in the molecular orbitals, then there's a formula by means of which you can calculate bond order. Bond order is nothing but half of number of electrons in bonding molecular orbital minus number of electrons in antibonding molecular orbital. Half of number of electrons in bonding minus number of electrons in antibonding. Remember, if bond order is equal to 1, if bond order comes out to be 1, that means between two atoms there is a single bond. If bond order is 2, between two atoms there is a double bond. Between two atoms there is a triple bond. If bond order comes out to be less than 0, that means molecule. If bond order comes out to be less or equal to 0, that means molecule does not exist. Okay? We say the molecule is non-viable. When the bond order comes out to be less or equal to 0. Now the point is, how do we exactly calculate the bond order? Have a look, guys. Try to understand. For example, you have got H2 molecule. Tell me, in one hydrogen atom, there is 1 electron. 2 hydrogen atoms means 2 electrons. So in total, how many electrons we have? 2. Every molecular orbital can accommodate maximum of 2 electrons. So these 2 electrons will go here. So what is its molecular orbital configuration? It is sigma 1s2. Right? This is bonding molecular orbital. This is antibonding, bonding, antibonding, bonding, right? Bonding, antibonding. Perfect. Now, if you wrote the molecular orbital configuration of hydrogen, can you calculate bond order? Bond order is half of number of electrons in bonding, 2, antibonding, 0. The value comes out to be 1. So bond order is 1. That means between 2 hydrogen atoms, there is a single bond. Now, as I told you, every molecular orbital can accommodate maximum of 2 electrons. It can accommodate maximum of 2 electrons. And both the electrons are present. So is there any unpaired electron? No, there is no unpaired electron. If there is no unpaired electron, the molecule is supposed to be diamagnetic. If there was unpaired electron, it was supposed to be paramagnetic. Right? For example, He2. One helium atom contains 2 electrons. 2 helium atom contains 4 electrons. So 2 here and 2 here. So configuration is sigma 1 is 2 and then sigma star 1 is 2. Perfect? So 2 bonding electrons, 2 antibonding electrons. So calculate the bond order. Half of bonding electrons, 2, antibonding 2. The value comes out to be 0. If bond order is 0, molecule does not exist. He2 does not exist. Right? Similarly, for example, Li2, hydrogen, helium, lithium. One lithium atom contains 3 electrons. So 2 will contain 6. So 2, 4, 5 and 6. So configuration is sigma 1 is 2, sigma star 1 is 2. Similarly, sigma 2 is 2. So how many bonding? 2 to 4. So bond order will be half of bonding minus anti-bonding. That is 2 by 2 is 1. So bond order is 1. If bond order is 1, that means between 2 lithium atoms, there is a single bond. Now tell me, every molecular orbital accommodates maximum of 2 electrons. So everywhere there are 2 electrons. Is there any unpaired electron? No. If there is no unpaired electron, it's again supposed to be diamagnetic. Perfect. Similarly, you can check this, right? You can check this. Let me talk about this carbon, C2 molecule. 6, 6, 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Now, these are degenerate. They have equal energies. So pairing won't be done until each degenerate electron gets 1 electron each. Pairing won't be done until each degenerate orbital gets 1 electron each. That too with the same spin. So how many I've used? 2, 4, 6, 8, 9, 10, 11, 12. So total there were 12 electrons and I have filled these 12 electrons. Now calculate bond order. Half of number of electrons in bonding 2, 4, 6, 8 minus number of electrons in anti-bonding 2, 4. So 8 minus 4 is 4. 4 by 2 is 2. So bond order is 2. If bond order is 2, that means there's a double bond in C2. And remember, this is a special molecule. Normally what happens? In a double bond, normally one bond is sigma, one is pi. In a double bond, normally one bond is sigma, one is pi. But in C2 molecule, both the bonds are pi bonds. Both the bonds are pi bonds. Right? Now tell me, do you see any unpaired electron? No. So this molecule again is supposed to be diamagnetic. Right? Talk about N2. N2 will have 14 electrons. 12 we have already filled till here. 12. So 13, 14. Right? 13, 14. Perfect. You can calculate its bond order. It will come out to be 3. Perfect. It will come out to be 3. N2 positive. It was a 14 electron species. N2 positive will be 13 electron species. N2 will be 14. Positive means subtract 1. So 13 electron species. When you calculate its bond order, it will be 2.5. N2 negative. 15 electron species. Now you must be thinking, since N2 negative is a 15 electron species, so how come this order is valid? This order is valid only up to 14 electrons. But N2 negative, no doubt it has 15 electrons. But its parent molecule is N2, from which this is made. Its parent molecule is N2. That parent molecule is following this configuration. So N2 negative will follow also this configuration. Guys, do you understand? And when you try filling things, N2 negative, its bond order will also be 2.5. Its bond order will be also 2.5. And remember one thing, guys, bond order is directly proportional to bond dissociation energy. Directly proportional to, you can say, stability. Inversely proportional to bond length. So anything can be asked out of these. Anything can be asked out of these. Anything can be asked out of these. Now, for example, there is one important thing which I can ask you here. I can give a question here first. Let's say you've got N2. You've got N2 positive. You've got N2 negative. I'm asking you to give the order of stability. I'm asking you to give the order of stability. This is A, this is B, this is C. Give me the order of stability. First of all, you will calculate bond orders. I'm telling you bond orders here only. This is 3, this is 2.5, this is 2.5. Now, you know, more the bond order, more the stability. More the bond order, more the stability. So A is maximum stable. Now, here the bond order is same, 2.5, 2.5. So which one is more stable? Remember, guys, remember one thing, an important statement. Whenever you have got two species which have got same bond order, whenever you have got two species which have got same bond order, at that point of time, that species which has lesser antibonding electrons, will be more stable. And when you write the molecular orbital configuration of N2 positive and N2 negative, you will find N2 positive has got lesser antibonding electrons. So lesser antibonding electrons means more stability. So B will be more stable than C. Right? Similarly, guys, one more thing. Whenever you see isoelectronic species, isoelectronic species are the ones which have got same number of electrons, right? Isoelectronic species, their bond order is also same. Isoelectronic species, their bond order will be same. Okay? Their bond order will be same. So till now I was talking about filling of electrons in those species which have got electrons less or equal to 14. Now what about greater than 14? Then this particular order is to be followed. For example, O2. How many electrons? One oxygen has got 8 electrons. 2 will be having 16 electrons. So fill these 16 electrons here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? Because these two are also degenerate. Now, calculate the bond order. Half of number of electrons in bonding. How many? 2, 4, 6, 8, 10, minus. How many electrons in anti-bonding? 2, 4, 5, 6. 10 minus 6 is 4. 4 by 2 is 2. So bond order is 2. Bond order 2 means between two oxygen atoms there is double bond. Now, do you see unpaired electrons? Yes, unpaired electrons. 2 unpaired electrons. So the species is paramagnetic. Right? The species here is paramagnetic. And at the same time, if the species is paramagnetic, you can calculate the moment also, spin magnetic moment. You know the formula under root of n into n plus 2. Under root of n into n plus 2. Under root of n into n plus 2. I hope you remember. Under root of n into n plus 2. What is n? Number of unpaired electrons. How many do you see? 2. So root of 2 into 2 plus 2. Right? Clear, guys? Now finally, let me give you one trick by means of which you can remember all this. Whenever you see a 14 electron species, its bond order will be always 3. 14 electron species, like N2. N2 contains 14 electrons, bond order 3. Whenever you see 15 electron species, its bond order will be 2.5. Whenever you see 16 electron species, bond order 2. 17 electron species, bond order 1.5. 18 electron species, bond order 1. So subtract by 0.5, 0.5, 0.5, 0.5. Similarly, 13 electron species, again subtract 0.5, 2.5. 12 electron species, bond order 2. 11 electron species, bond order 1.5. 10 electron species, bond order 1. Perfect? Right, people? Okay. At the same time, there is one exception here, which I would want you to remember. For example, you have got CO positive molecule. CO positive. How many electrons are there? Carbon has got 6, oxygen has got 8, positive charge, so subtract 1, 8, 6, 14 minus 1, 13. So it's a 13 electron species. If it is a 13 electron species, its bond order has to be 2.5. But in reality, its bond order is 3.5. Remember this one, CO positive. Remember this one, CO positive. Its bond order is 3.5. Okay. Now, for example, the question is asked like this. You have got Cn negative, you have got CO. Check their bond orders. Calculate the electrons. 7 plus 6 is 13 plus 1, 14. 14 electron species. 8 plus 6 is 14. So both are 14 electron species. If they are having same electrons, that means they are isoelectronic. If they are isoelectronic, you know isoelectronic species have same bond order, and 14 electron species will have bond order of 3. So their bond order will be 3. And with this, your chemical bonding is done and dusted. Okay? So which chapter next? Thermodynamics or equilibrium? Can you tell me the answer of this one? NO positive, Cn negative. Again, 8 plus 7, 14. 8 plus 7, 15 minus 1, 40. It's a 14 electron species. 7, 6, 13, 1, 14. 14 electron species. So both will have bond order 3. Okay? Which chapter the next? Quick. Before starting the next chapter, again, it's going to be a small break. So that you will also refresh, I'll also refresh. Right? We'll have tea. Let me call my mother and ask her to get tea for me. I've not had lunch. Okay? And I'm, chakkar aa raha hai mujhe. Hello? That's good. Achha, okay. Wait. I cannot have lunch. If I have lunch, then I'll be sleepy. I won't be able to teach. Hello? Black coffee without sugar. No, 2 minutes Muslim. Jaldi, huh? So the time is 4:55. I'm giving you the break of 20 minutes. It'll be 5:15, huh? So equilibrium starts at it is 4:55. Let's start at 5:20. Let's take 25-minute break. It's okay. Okay? So we'll start, but I would want everyone, guys, everyone to be back, okay? Everyone to be back. And after equilibrium, we'll do thermodynamics. Don't worry. But I would want everyone to be back. Is it a promise? Yeah? Okay. See you. See you in some time.
What's up, people? Is everyone back? Yes, is everyone alive? Is everyone alive? Tell me once. Is everyone alive? Say it in the chats. Is everyone alive? Someone is barely breathing. Is that? Alive and kicking. Yeah, great. Great, great, great. Spammers have started coming. Someone is writing PW. Why you are writing PW in my chats? Go to their channel now. So should we start? Yes. Done, 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 done. Telegram link I've already given you. Name of the Telegram channel is Wassim Bhat Chemistry Official. Wassim Bhat Chemistry Official is the name of the Telegram channel. Sir, do you know Pratik sir? They are facing a lot of problems. Yes, yes, Pratik is my very good friend. There were some issues with the channel. I don't know whether it's fixed or not. Chalo, should we start then? Should we start? Should we start? Should we start? Sir, did you block me? No, I did not block. Chalo then, let's get going. Let's get started. And now we are going to start chemical equilibrium first. Chemical equilibrium, right? So my dear students, chemical equilibrium, one of the important chapters. So first of all, let me tell you from which topics questions are asked in chemical equilibrium chapter. I'm talking about chemical equilibrium, not ionic equilibrium, okay? Ionic equilibrium will be done, that's a separate chapter. That will be done after this. So first of all, what all topics are asked? From which topics questions are asked in the chapter chemical equilibrium? So my dear students, the first topic is going to be characteristics of equilibrium constant. Characteristics of equilibrium constant. From this topic, questions are frequently asked, number one. Number two, a relation between Kp and Kc. A relation between Kp and Kc. Number three, Kp and Kc calculation by mole and degree of dissociation method. By mole and degree of dissociation method. And then it is going to be Le Chatelier principle. These are the topics
from which questions are asked in the chapter chemical equilibrium. So we are going to cover them one by one. And after covering this chemical equilibrium, then we'll start the new chapter that's going to be ionic equilibrium. Okay? So without wasting any sort of time, let's get going. Let's get started with the chapter chemical equilibrium, my dear students. My dear students, first of all, how to write expression. First of all, how to write expression of equilibrium constant. How do we write the expression of equilibrium constant? Try to understand what exactly I'm going to say. Okay? For example, you have got a balanced chemical equation like this. N1A plus N2B. And here I'm showing the reversible sign. N1A plus N2B gives N3C plus N4D. Imagine it's a balanced chemical equation wherein N1, N2, N3 and N4. These are the stoichiometric coefficients of reactants and products. These are the stoichiometric coefficients of reactants and products. Just a second, guys. Yuvraj, will you stop this spamming at all, or do you want to get blocked again? If yes, then let me know. I'll do it. Sit properly. If you want to study, then be here. Otherwise, you can leave. Whosoever you are. See, guys. I have taken a balanced chemical equation. And my dear students, how do we write the expression of equilibrium constant for a balanced chemical equation? Try to understand. Whenever you have to write the expression for equilibrium constant, you'll be always starting with the product. I'll write active mass of C. You must be thinking what this active mass is. Give me some time, you'll understand it. Just remember what I'm saying. I'll be starting with the product, and I wrote active mass of C raised power stoichiometric coefficient, that is N3. Active mass of D raised power stoichiometric coefficient, that's N4, divided by, come to the reactant side, active mass of A raised power stoichiometric coefficient, N1. Active mass of B raised power stoichiometric coefficient, N2. So first of all, whenever you will have to write the expression for equilibrium constant, you'll be always starting with the product. You'll be writing their active masses in the numerator divided by active masses of reactants in the denominator. Number one. Number two, whenever you have a reactant or product, in aqueous phase, that means in the brackets, they will mention AQ. Remember that particular reactant or product which will be in aqueous phase, its active mass is basically its concentration. Whenever you have got a reactant or product in gaseous phase, in the bracket they will mention G. Its active mass is either taken as its concentration or pressure. Whenever you have got a pure solid or pure liquid, its active mass is taken as unity. Its active mass is taken as 1. So remember these three things first of all. Whenever you see any reactant or product in aqueous phase, its active mass is its concentration. Gaseous phase, its active mass is concentration pressure. Pure solid or pure liquid, its active mass is taken as 1. Now, my dear students, let me tell you one simple thing over here. What is that? Equilibrium constant, how do we exactly define it? First of all, this was how to write the equilibrium constant expression. How do we define the equilibrium constant? Simple. Understand. Over here, if you look at this particular reaction, these are basically two reactions, forward and backward. Let the rate constant of forward reaction is Kf. Let the rate constant of backward reaction is Kb. Let the rate constant of forward reaction is Kf. Let the rate constant of backward reaction is Kb. Now, equilibrium constant is defined as the ratio of rate constant of forward reaction to that of rate constant of backward reaction. Equilibrium constant is defined as the ratio of rate constant of forward reaction to the rate constant of backward reaction. Now, my dear students, how do we write the expression for equilibrium constant? I told you a few minutes back. It's active mass of C raised per n3, active mass of D raised per n4 divided by active mass of A raised per n1, active mass of B raised per n2. This is how you write its expression. Now, let me tell you, we divide this equilibrium constant into two parts. Basically, it's divided into many parts. But right here in your syllabus, I'm dividing into two parts, right? One is called as Kc, one is called as Kp. Otherwise, there is one more thing that is Kx. There is one more thing that is Kpc. Nothing to do with all of them. First of all, equilibrium constant, I'm classifying it into two parts. One is Kc, one is Kp. Now, what is Kc and what is Kp? My dear students, remember, whenever in the expression of equilibrium constant, active masses are replaced by concentration. Whenever in the expression of equilibrium constant, active masses are replaced by concentration. At that point of time, your equilibrium constant Keq is called as Kc. What is Kc? Kc is equilibrium constant only. It is equilibrium constant only. Whenever in the expression of equilibrium constant, you replace active masses with the term concentration. At that point of time, Keq is replaced by Kc. Now, how do I write this expression? See, instead of active mass of C, I'll write concentration of C at equilibrium raised by stoichiometric coefficient. Concentration of D at equilibrium raised by stoichiometric coefficient divided by concentration of A at equilibrium raised by stoichiometric coefficient. Concentration of B at equilibrium raised by stoichiometric coefficient. Point number one. Point number two. Whenever in the expression of equilibrium constant, active masses are replaced by the term pressure. At that point of time, your Keq is replaced by what? It's replaced by Kp. And how do I write this expression? Instead of active mass of C, I'll write partial pressure of C at equilibrium raised per n3, partial pressure of D at equilibrium raised per n4 divided by partial pressure of A at equilibrium raised per n1, partial pressure of B at equilibrium raised per n2. So this is first of all how you write the expression of Kc and Kp. Number one. Number two, my dear students. Number two. For example, this is the reaction. This is the reaction. Do you see all the reactants and products are in gaseous phase? Absolutely. For gases, active mass is either concentration or pressure. That means I can write the expression for Kc as well. I can write the expression for Kp as well. If I write the expression for Kc, I'll start with the product. I'll write concentration of Hi at equilibrium raised per stoichiometric coefficient, that's 2. Concentration of H2 at equilibrium raised per stoichiometric coefficient. Concentration of I2 at equilibrium raised per stoichiometric coefficient. Correct? If I write the expression for Kp, I'll use the term pressure. I'll use partial pressure of Hi at equilibrium raised per stoichiometric coefficient. That is how much? That is 2 divided by partial pressure of H2 at equilibrium raised per stoichiometric coefficient 1 and partial pressure of I2 at equilibrium raised per stoichiometric coefficient 1. Perfect. This is how you write expression for Kc and Kp. Similarly, if you look at this particular expression, again, all the reactants products are in gaseous phase. For gases, active mass is concentration as well as pressure. So I can write the expression for Kc as well as Kp. Now write the expression for Kc first of all. It is concentration of PCl3 at equilibrium raised per stoichiometric coefficient, concentration of Cl2 at equilibrium raised per 1, concentration of PCl5 raised per 1. Similarly, Kp, it's going to be partial pressure of PCl5 at equilibrium raised per stoichiometric coefficient divided by partial pressure of PCl3 at equilibrium raised per stoichiometric coefficient, partial pressure of Cl2 at equilibrium raised per stoichiometric coefficient. This is how you write the expressions for Kp and Kc. Okay. Now, can you give this a try? See guys, this is in solid form. The one that's in solid form, its active mass is 1, so nothing to do with this. The one that's in solid form, its active mass is 1, nothing to do with this. This is in gaseous form. For gases, active mass is concentration as well as pressure. So I can write expression for Kc as well as the expression for Kp. So I would say Kc expression is nothing but concentration of carbon dioxide at equilibrium raised per stoichiometric coefficient. Kp is partial pressure of carbon dioxide at equilibrium raised per stoichiometric coefficient. Perfect. Right, people? Perfect. Sir, Kp is wrong. Did I write something wrong? Oh, okay. This all right. I wrote reverse. My bad. Chalo ji. This is partial pressure of PCl3 at equilibrium raised power 1. This is partial pressure of Cl2 at equilibrium raised power 1 divided by partial pressure of PCl5 at equilibrium raised power 1. Now correct? Got it. Okay, cool. Chalo, moving on. Look at the next one. Solid phase, nothing to do with this. Gaseous phase, yes. Gaseous phase, yes. For gases, active mass is concentration as well as pressure. So Kc is nothing but it is concentration of SO3 at equilibrium raised power 1 divided by concentration of O2 at equilibrium raised power 3 by 2. Similarly, Kp expression. Kp expression is going to be partial pressure of SO3 at equilibrium raised power 1 divided by partial pressure of O2 at equilibrium raised power 3 divided by 2. So this is how you write the expressions for Kp and Kc. Now there is one more term. My dear students, there is something called as delta Ng. How do we calculate delta Ng for the reaction? Delta Ng for the reaction is nothing but it is number of moles of gaseous products minus number of moles of gaseous reactants. Delta Ng is what you call as number of moles of gaseous products minus number of moles of gaseous reactants. Number of moles of gaseous products minus number of moles of gaseous reactants. Now, how exactly it's used? For example, this is the reaction. I want to calculate delta Ng for this reaction. Delta Ng is equal to number of moles of gaseous products. This is the product and also in gaseous phase. How many moles? 2. Minus number of moles of gaseous reactant. This is the gaseous reactant. This is the gaseous reactant. Their stoichiometric coefficients are 1 and 1. So gaseous moles are 1 plus 1, 2. So 2 minus 2 is 0. So delta Ng for this reaction is 0. Simple. What about delta Ng for this reaction? Delta Ng will be equal to number of moles of gaseous products 1 plus 1, 2 minus number of moles of gaseous reactant. That's 1. So 2 minus 1 comes out to be 1. Perfect. Similarly, this particular reaction. What about delta Ng for it? Number of moles of gaseous product. This is not the gaseous product, nothing to do with this. This is the gaseous product and its moles are 1. Minus number of moles of gaseous reactant. There is no gaseous reactant, right? Similarly, look at the next one. If I talk about delta Ng for this particular reaction, number of moles of gaseous product, that's 1. Minus number of moles of gaseous reactant, that's 3 by 2. So 1 minus 3 by 2 is nothing but minus 1 by 2. I believe this is clear to everyone. This is clear to everyone. Now, my dear students, whenever you have got a reaction like this, for example, N1A gas plus N2B gas, it's in equilibrium with N3C gas plus N4D gas. This is a balanced chemical equation. Now, for this particular reaction, what is the relation between Kp and Kc? Remember, I'm not deriving any relation. I'm just giving you the result. For this gaseous phase reaction, Kp is equal to Kc RT raised power your delta N. And since it's a gaseous phase reaction, so I'm writing delta Ng here. Kp is equal to Kc RT raised power delta Ng. Number one. Number two, my dear students, tell me one thing. If, for example, delta Ng is equal to 0, anything raised power 0 is 1, I would say at that point of time, Kp and Kc would be equal. So when delta Ng is 0, your Kp, Kc will be equal. And if delta Ng is non-zero, your Kp and Kc are not equal. Right? Your Kp and Kc are not equal. One simple conclusion. Okay? If delta Ng is 0, anything raised power 0 is 1, Kp, Kc equal. Delta Ng non-zero means Kp and Kc are not equal. Okay? Now on this particular one, there was a question asked long back. And you can get similar sort of questions. For example, this is the question. In which of the following Kp and Kc are not equal? Tell me. Kp and Kc are not equal when delta Ng is non-zero. Which of the following reaction is there whose delta Ng is non-zero? That is the last reaction. Right? If you calculate delta Ng for the last reaction, delta Ng will be number of moles of gaseous product, that is 2, minus number of moles of gaseous reactant, that's 1. So 2 minus 1 is 1, which is non-zero. And when delta Ng is non-zero, your Kp and Kc won't be equal. Perfect? Simple basic question. Absolutely. It's a simple basic question. Now tell me one thing. Write the expression of Kp in terms of Kc. Tell me for the first reaction, what is delta Ng? For the first reaction, delta Ng is number of moles of gaseous product minus number of moles of gaseous reactant, which is 1 plus 1, 2. So delta Ng is 0. So your Kp is equal to Kc RT raised by delta Ng. When delta Ng is 0, Kp and Kc will be equal. This is the expression of Kp in terms of Kc. Simple. For the second reaction, what is delta Ng? Delta Ng is equal to number of moles of gaseous products, 1 plus 1, 2, minus number of moles of gaseous reactant, that's 1. So I would say Kp would be equal to Kc RT raised by delta Ng, that's 1. So this is the relation, this is your Kp in terms of Kc. Similarly, you can check this and this on your own. Hello, let me show you the fourth one. What is the delta Ng for the fourth reaction? Number of moles of gaseous product, that is 1. Is there any gaseous reactant? No. So I would say again, Kp is equal to Kc RT raised by delta M. That's 1. Sometimes they'll ask you, what is the ratio of Kp and Kc? So simple, Kp divided by Kc is equal to RT raised by 1. Sometimes they'll ask you, what is the ratio of Kp and Kc for any type of reaction? Understood? What about this reaction? Chalo, let me show you the third one also. Delta Ng for the third one will be number of moles of gaseous product, which is 2, minus number of moles of gaseous reactant, that's 4. The value is minus 2. So Kp is equal to Kc RT raised by delta Ng. Sometimes they'll ask you, what is the ratio of Kp and Kc? Kp and Kc ratio will be 1 divided by RT ka square. Simple. Yes, I believe this is clear. Now guys, there are few things which you need to remember. From which questions will be frequently asked. Sir is going very fast. I'm supposed to go fast. I cannot go slow. Right? This is the one shot of your class 11th. So how do you expect I'll go slow? It will take 36 hours then. Okay? Chalo guys. Few more things by means of which questions will be easily you can solve the questions. What kind of questions? Have a look. My dear students, whenever you have got a reaction at equilibrium, for example, this is the reaction which is at equilibrium. Let's say its equilibrium constant is, for example, K1. Let's say its equilibrium constant is K1. Okay? My dear students, when you reverse the reaction, remember equilibrium constant is inversed. Earlier, equilibrium constant of this reaction was K1. Now, after reversing the reaction, equilibrium constant is inversed. It becomes 1 by K1. So when you reverse the reaction, equilibrium constant is inversed. Okay? Number 2. The reaction is same. A gives B, whose equilibrium constant is K1. My dear students, if you multiply this reaction with some number, let that number be n. I'm multiplying this reaction by some number n. When you multiply the reaction by some number, that number goes to the power of equilibrium constant. Earlier, equilibrium constant was K1. Now it's K1 raised power n. Similarly, for example, you have got the reaction like this. A in equilibrium with B, whose equilibrium constant is K1. C in equilibrium with D, whose equilibrium constant is K2. Now, for example, when you add two reactions, the net reaction becomes A plus C gives B plus D. My dear students, when you add two reactions, the equilibrium constants are multiplied. So the equilibrium constant of this reaction would be K1 multiplied by K2. So these are the three things which I would want you guys to remember for now. Number one. When a reaction is reversed, equilibrium constant is inversed. When you multiply a reaction by some number, that number goes to the power of equilibrium constant. Similarly, on adding the reactions, equilibrium constants are multiplied. That's it. Okay, that's it. At the same time, guys, remember equilibrium constant. If I talk about this equilibrium constant of the reaction, or let me just write it in general way, equilibrium constant only depends on temperature. Remember that. Equilibrium constant only depends on temperature. And when it comes to endothermic reactions, in case of endothermic reactions, your equilibrium constant is directly proportional to temperature. And in case of your exothermic reactions, your equilibrium constant is inversely proportional to temperature. Remember this particular statement as well. Equilibrium constant only and only depends on temperature, and for endothermic, equilibrium constant is directly proportional to temperature. For exothermic, equilibrium constant is inversely proportional to temperature. Okay? Got it? Got it, people? And if this is clear, then let's see what kind of question can be framed. It's a very common question. This has been asked in different exams also. Very basic, very simple question. See how do we tackle with such kind of the questions. My dear students, two reactions are given. Two reactions are given. Right? This is the reaction whose equilibrium constant is given to me. This is the reaction whose equilibrium constant is given to me. And this is the reaction whose equilibrium constant needs to be calculated. This is the reaction whose equilibrium constant is given to me. This is the reaction whose equilibrium constant needs to be calculated. Remember, that particular reaction whose equilibrium constant needs to be calculated. That particular reaction whose equilibrium constant needs to be calculated. You are supposed to make that reaction. You are supposed to make that reaction from the reaction whose equilibrium constant is given. That particular reaction whose equilibrium constant is to be calculated, you are supposed to make that reaction from the reaction whose equilibrium constant is given. So technically, I am supposed to make second from first. How? Have a look. What I'll be doing? I'll be first of all reversing this reaction. When you reverse this reaction, it becomes 2 times NH3 gives N2 plus 3 times H2. Since when you reverse the reaction, equilibrium constant is inversed. Now it becomes 1 by 49, right? Now I'll be multiplying this reaction with 1 by 2. When I multiply this reaction with 1 by 2, 2 gets cancelled. It becomes NH3. This becomes half of N2 and this becomes 3 by 2 times H2. Since I multiplied this reaction with 1 by 2, that 1 by 2 goes to the power of equilibrium constant. So it's 1 by 49 raised power 1 by 2. The value comes out to be 1 by 7. My dear students, just look carefully. Was I supposed to make this reaction? Was I supposed to make this reaction? Yes, I made this reaction, right? And its equilibrium constant is coming out to be how much? 1 by 7. Simple. Yes? Perfectly done. One more question I'm going to solve on the same so that it becomes clear to you. This is also a common question and these sort of questions are frequently asked. See guys, understand carefully. 3 reactions are given, their equilibrium constants are given, K1, K2, K3. And as per the question, I am supposed to calculate equilibrium constant for this reaction. I'm supposed to calculate equilibrium constant for this reaction. Now how do I do it? Try to understand carefully what I'll be doing. My dear students, the reaction which I have to make, in this reaction, NH3 is on left side. NH3 is on left side. Among these reactions, do you see NH3 anywhere? And I can see NH3, but it's on right side. So first of all, I'll be reversing this reaction. I'll be reversing this first reaction. When I reverse this reaction, it becomes 2 times NH3 gives N2 plus 3 times H2. Now, after reversing the reaction, equilibrium constant is inversed. Now it's 1 by K1. Okay. Now, at the same time, the reaction which I have to make in this reaction, I can see twice NO. And this twice NO is on right side. In any reaction, do you see twice NO? Yes, in the second reaction, which is already on right side. So I'll write this reaction as such. N2 plus O2 gives 2 times NO, whose equilibrium constant is K2, right? The reaction which I have to make, I can see 3 times water here on the right side. Do you see water anywhere? Yes, here. But it just, I just don't need water. I need 3 times water. So what I'll be doing? I'll be multiplying this reaction by number 3. When I multiply this reaction with number 3, it becomes 3 by 3 times H2. 3 by 2 times O2 gives what? Gives 3 times water. Since I multiplied this reaction by number 3, that 3 goes to the power of equilibrium constant. So it's K3 raised power 3. Now, just add these reactions. Just add these reactions. Just add these reactions. When you add these reactions, N2 N2 cancels out. 3 times H2, 3 times H2 cancels out. It becomes twice NH3. O2 plus 3 by 2. O2 makes it 5 times O2. So 2 times NH3 plus 5 by 2 times O2. It gives me what? It gives 2 times NO plus 3 times water. Just check, was I supposed to make this reaction only? Absolutely, I was supposed to make this reaction only. How did I get this reaction? When I added these reactions, and when I add the reactions, equilibrium constants are multiplied. So, first one was 1 by K1, second one is multiplied by K2, third one is multiplied by K3 raised power 3. Do you see any option like this? K2, K3 raised power 3 divided by K1. Yes, it's option A. Perfect. Yes, easy peasy. Yes, it is easy peasy. Now, if you think everything is easy peasy, then let's move on to the actual stuff, which is not easy peasy. Yeah? Sir, you look tired. Of course, I'm supposed to look tired, right? We have started the session at 10:30.
So what do you expect? Huh? Chalo now. This is something very important. Very, very, very important. Which this part of the chapter is phobic to students, I would say. They hate it. They hate it. But you are going to love it. Why? Because I'm going to start from the basics only. See, guys. The first thing which I'm going to teach you right now, what is that? How do we calculate? How do we calculate moles of reactants and products at equilibrium? How do we calculate moles of reactants and products at equilibrium? First of all, if I ask you what is equilibrium, if I ask you what is equilibrium, you study equilibrium, right? You have been studying from past 2 years equilibrium. What is equilibrium basically? What is equilibrium? My dear students, equilibrium is the state. It is the state which is basically the most stable state of the system. Equilibrium is most stable state of the system. That's the reason why every reversible reaction wants to attain equilibrium. Because when equilibrium is attained in the reaction, the stability of the system is maximized. The stability of the system is maximized. Someone is saying rate of forward is equal to rate of backward. That is not the definition of equilibrium. That is the characteristic feature of equilibrium. So basically, when equilibrium is established, at equilibrium, rate of forward becomes equal to rate of backward. That is the characteristic feature of equilibrium. That's not the definition of equilibrium. Definition of equilibrium is the state at which entropy attains its maximum value, Gibbs free energy attains its minimum value. That's something I'll teach you in thermodynamics. Just wait for it. That is the definition. Okay? In short, you remember one thing. Equilibrium is the most stable state of the system. Equilibrium is the most stable state of the system. That's why every reversible reaction wants to attain equilibrium as quick as possible. Okay? Now, people, understand what I'm going to say. Calculation of moles of reactants and products at equilibrium. How do we calculate moles of reactants and products at equilibrium? How do we calculate moles of reactants and products at equilibrium? Try to understand, people. For example, you have got the reaction like this. A gives B plus C. This is the reaction, let's say. Okay? I'm writing time t is equal to 0. Time t is equal to 0 means reaction has not started. Time t is equal to 0 means reaction has not started. When the reaction has not started, that means there will be only moles of reactant present in the container. And let the moles of reactant initially is equal to A. This would be 0, this would be 0 because the reaction has not started. Now, when the reaction starts, moles of reactant will keep on decreasing. Moles of product will keep on increasing. There will be a stage when equilibrium would be established in the reaction. And when equilibrium is established, let's assume at that point of time, out of A moles of reactants, when equilibrium is established in the reaction, let's assume at that point of time, out of A moles of reactants, X moles got converted into products. So I'll be left with A minus X moles of reactant. So these are the moles of reactant left in the container at equilibrium. I assumed at equilibrium, X moles of reactant had got converted into products. I assumed at equilibrium, out of A moles of reactant, X moles had got converted. So I'm left with A minus X at equilibrium. Now, use the stoichiometry. 1 mole of A gives 1 mole of B. So X moles of A would give X moles of B. 1 mole of A gives 1 mole of C. So X moles of A gives X moles of C. These are the moles of reactants and products which are present in the container at equilibrium. These are the moles of reactants and products which are present in the container at equilibrium. Let me show you one more case. For example, you have got the reaction like this. A gives 2 times B plus 3 times C. Now, I'm writing time t is equal to 0. That means the reaction has not started. So I'll be having, for example, A moles of reactant. This is 0, this is 0. Now, when equilibrium is established in the reaction, let's assume out of A moles of reactant, X moles got dissociated. X moles got converted into product. So I'll be left with A minus X moles. So these are the moles of reactant left in the container at equilibrium. Now use the stoichiometry. 1 mole of A gives 2 moles of B. So X moles of A would have given 2X. 1 gives 3, X gives 3X, right? So these are the moles of reactants and products which are present in the container at equilibrium. As simple as that, right? As simple as that. Yes? Now, my dear students, there can be one more scenario. I'm writing the reaction saying what? A gives
2 times B, or let me write simple reaction. A gives B plus C. This is the reaction. Now at time t is equal to 0, there would be some moles of reactant in the container. But let's assume before the start of the reaction itself, let's assume before the start of the reaction itself, we have kept some B and C in the container already. Let's say we have got B moles of this, we have got C moles of this. Before the start of the reaction already, we have kept some moles of products as well in the container. Before the start of the reaction, right? Now, when reaction would start, moles of reactant will decrease, moles of product will increase. There will be a point when equilibrium will be established. Let's assume at equilibrium, out of A moles of reactant, X moles got converted into product. So I'll be left with A minus X moles of this, right? At equilibrium, the number of moles of reactant will be A minus X. Now, already in the container, there were B moles of this product. Can I say some more moles of B would have got formed? How much? See, 1 mole of A gives 1 mole of B. X moles would have given X. So this B plus X, these are the moles of this product at equilibrium. Similarly, this will be C plus X. These are the moles of this C at equilibrium. Do you understand? If you understand, how do we calculate? Moles of reactants products at equilibrium, then it is high time to do the calculation of Kp and Kc by mole method. See guys, Kp and Kc calculation by which method? By mole method. Kp and Kc calculation with the help of which method? Mole method. Try to understand what exactly I'm going to do. For example, my dear students, I am taking the reaction like this. 2A gas, it gives B gas plus C gas. Just one reaction I'm taking. 2A gas gives B gas plus C gas. Can you first of all tell me what is the delta Ng for this reaction? Quick, in the chats. Absolutely. Delta Ng for the reaction is 0. If delta Ng for the reaction is 0, we already know when delta Ng for the reaction is 0, Kp and Kc value comes out to be equal. So for this particular reaction, Kp and Kc would be equal. Now try to understand. Let's say at time t is equal to 0, we have got A moles of reactant. Let's say this is 0. Now at equilibrium, let's assume out of A moles of reactant, X moles got dissociated into product. X moles got converted into product. So I'll be left with A minus X moles of reactant at equilibrium. Now, 2 moles of A gives 1 mole of B. 2 moles of A gives 1 mole of B. 1 mole of A gives 1 by 2 moles of B. X moles will give X by 2 moles of B. Did you understand this point? Again, I'm repeating. 2 moles of A gives 1 mole of B. So 1 mole of A gives 1 by 2 moles of B. X moles of A would give X by 2 moles of B. Similarly, 2 moles gives 1 mole. So 1 gives 1 by 2. X gives X by 2. So what did I get? I got the moles of reactants products present in the container at equilibrium. Now, my dear students, for example, I have to calculate the expression for Kc. How do I write the expression for Kc? Kc expression will be concentration of B at equilibrium raised by stoichiometric coefficient, concentration of C at equilibrium raised by stoichiometric coefficient, concentration of A at equilibrium raised by stoichiometric coefficient. That's 2. So technically, in order to calculate Kc, what do I need? I need concentrations of reactants and products at equilibrium. How do I calculate concentrations? My dear students, concentration is nothing. It means moles divided by total volume. Let's assume the volume of the container is V liters. Okay, just give me a second. I'm getting one call. Okay, just a second. Hello? Walaikum assalam. आप इसको सदाम को कॉल कीजिए. आपके उसका नंबर है? आप उन्हीं को कॉल कीजिए. मैं अभी लाइव क्लास में हूँ. ओके. Okay, what I was trying to say is, see guys, I was telling you, in order to calculate Kc, what do I need? I need concentrations of reactants products at equilibrium, right? Now concentration is what? When you divide moles with the total volume of the container, total volume of the reaction vessel in liters. When you divide moles with the volume of the reaction vessel in liters, you get concentration. Now tell me, I have to calculate concentration of reactants products at equilibrium. So what do? Concentration is moles by volume. So how many moles of reactant do we have at equilibrium? A minus X. Divide by total volume of the vessel, V liters. This is already X by 2 moles. Divide by total volume of the vessel, V. X by 2. Divide by total volume of the vessel, V. So what are these terms if I ask you? These are now the concentrations. These are now the concentrations of reactants and products at equilibrium. My dear students, if these are concentrations of reactants and products at equilibrium, then you can easily calculate Kc expression. Concentration of B at equilibrium, what is that? That's X divided by 2, V, raised power stoichiometric coefficient 1. Concentration of C at equilibrium, that's X divided by 2V, raised power stoichiometric coefficient 1. Divided by concentration of A at equilibrium, that is A minus X divided by V, raised power stoichiometric coefficient 2. Now, V becomes V square cancels out. So, Kc comes out to be X makes it X square, 2 ka square is 4 multiplied by A minus X square. This is the expression of what? This is the expression for Kc. This is the expression for Kc. This is the expression for what? This is the expression for Kc. Now, I have to calculate the expression for Kp as well. I have to calculate the expression for Kp as well. Okay. Now, how do we get the expression for Kp? First of all, what is Kp as per you? Kp expression will be partial pressure of B at equilibrium raised power stoichiometric coefficient, partial pressure of C at equilibrium raised power stoichiometric coefficient, partial pressure of A at equilibrium raised power stoichiometric coefficient. Now, what is partial pressure? How do we calculate partial pressure? Partial pressure is calculated as total pressure multiplied by mole fraction. Partial pressure is calculated as total pressure multiplied by mole fraction. Now try to understand what exactly I'm going to do. Tell me one thing. At time t is equal to 0, you tell me the answers, okay? At time t is equal to 0, how many gases were in the container? At time t is equal to 0, how many gases were there in the container? At time t is equal to 0, how many gases were there in the container? At time t is equal to 0, there was only one gas in the container. Now at equilibrium, how many gases are there in the container? Tell me. At equilibrium, how many gases are there in the container? There are 3 gases in the container at equilibrium. At equilibrium, there are 3 gases. So can I say at equilibrium, there is a gaseous mixture present in the container? There are some moles of A, there are some moles of B, there are some moles of C. So at equilibrium, there is a mixture of gases. Let's say the total pressure of this mixture at equilibrium is Pt. Total pressure of this mixture at equilibrium is Pt. Now, the total pressure of the mixture will be due to A, B as well as C. Total pressure of the mixture will be due to A, B as well as C. Now, the contribution made by A, the contribution made by gas A towards the total pressure is what I call as partial pressure. Is what I call as partial pressure. Contribution made by gas B towards the total pressure is what I call as partial pressure. Contribution made by gas C towards the total pressure is what you call as partial pressure. And you know, total pressure of the mixture will be the sum of partial pressures. Will be the sum of partial pressures. Correct? Will be the sum of partial pressures. Now the point is, how do I calculate partial pressure of A, B, C at equilibrium? Partial pressure of A will be total pressure of the mixture at equilibrium multiplied by mole fraction of A at equilibrium. Simple. Okay? Now people try to understand. First of all, these were the moles of reactants products at equilibrium. Tell me one thing. How do I get the mole fraction at equilibrium? Before getting the mole fraction, tell me how many total moles are there in the container at equilibrium. Total moles in the container at equilibrium will be A minus X plus X by 2. A minus X plus X by 2 plus X by 2. How much that will be? That will be A. These are the total moles present in the container at equilibrium. Now, if I divide A minus X with total moles, if I divide X by 2 with total moles, if I divide X by 2 with total moles, now what do I call these terms as? I call these terms as the mole fractions. This is the mole fraction of reactant at equilibrium. This is the mole fraction of B at equilibrium. This is the mole fraction of C at equilibrium. Now, mole fraction is to be multiplied with what? Total pressure of the mixture at equilibrium. Let the total pressure of the mixture be Pt. Let the total pressure of the mixture be Pt. And if I multiply them with Pt, what did I get? I got the partial pressures of reactants products at equilibrium. These are partial pressures of reactants products at equilibrium. And since you got the partial pressures of reactants products at equilibrium, now the point is you just have to write the expression for Kp. How do I write the expression for Kp? I've already written the expression. I just have to put the values. Now put the values, guys. Kp. Kp is equal to partial pressure of B at equilibrium. How much is that? X divided by 2A multiplied by Pt. Multiplied by partial pressure of C at equilibrium. Again the same. So it becomes square. Divided by partial pressure of A at equilibrium. That is A minus X multiplied by Pt divided by A ka whole square. Perfect. Now see what all things will get cancelled out. See, a square gets cancelled out. pt square gets cancelled out. So I'll be left with x square divided by 2 ka square is 4 and a minus x ka square. So this is the expression for Kp also which you have calculated. Now tell me one thing, is Kp and Kc coming out to be equal? Is Kp and Kc coming out to be equal? Absolutely, Kp and Kc are coming out to be equal. Why is that? Because we already knew this reaction is the one whose delta and G is 0, and all those reactions with delta and G 0, their Kp and Kc are always equal. I mean, did you understand the procedure of calculating Kp and Kc? So technically, in order to get the Kc value, we need concentrations at equilibrium. In order to calculate Kp value, we need partial pressures at equilibrium. Understood? Say yes or no in the chats, quick. Say yes or no in the chats, quick. Let's do some questions so that you can understand it properly. Okay? Let's do the questions so that you can understand it properly. Have a look, guys, how exactly I'm going to solve the questions. For example, this is the question. This is the question. Look at the question carefully. Look at the question carefully. Question says the reaction is A gas plus B gas. Okay? It gives 2 times C gas. Now the question says initially we are starting with 2 moles of A, 1 mole of B and 1 mole of C. So already in the beginning you have got 2 moles of A, 1 mole of B and already there is 1 mole of C in the container. Before the start of the reaction itself, there is C present in the container. How much? 1 mole. Perfect. Now tell me one thing, at equilibrium, let's assume out of 2 moles, X got converted. So I'm left with 2 minus X, right? Now, 1 mole reacts with 1 mole. So X would have reacted with X. It's simple. See, A is reacting with B, right? So I'm assuming out of 2 moles of reactant, X moles reacted basically. I'm assuming at equilibrium out of 2 moles of reactant, X moles reacted. So I'm left with 2 minus X. So 1 mole of A reacts with 1 mole of B. So X moles of A would have reacted with X moles of B. I had 1. Out of 1, X is reacting. So I'm left with 1 minus X. So these are the moles of B in the container at equilibrium. Now already there was 1 mole of C in the container. Now some more moles would have got formed. 1 mole of A gives 2 moles of C. So X would have given 2X. Tell me, is this point clear? Is this particular step clear? These are the moles of reactants products at equilibrium. These are the moles of reactants products at equilibrium, right? Now guys, the container in which reaction is taking place, volume of that container is 10 liters. Perfect. Now if I divide these moles with the total volume, 2 minus X divided by 10. Similarly, 1 minus X divided by 10. Similarly, 1 plus 2X divided by 10. What do I call these terms as? I call these terms as concentrations. These are the concentrations of reactants products at equilibrium. These are the concentrations of reactants products at equilibrium. As per the question, they have mentioned final concentration of C is 0.2 molar. What is meant by final concentration of C? Final concentration of C means concentration of C at equilibrium. Because when equilibrium is established in the reaction, after that, moles of reactants products does not change. After that, concentrations of reactants products does not change. When equilibrium is established in the reaction, after that, concentrations of reactants products does not change. So, final concentration of C means the concentration of C at equilibrium, right? So, this is given to me as per the question 0.2. As per our calculation, what is the concentration of C at equilibrium? As per our calculation, concentration of C at equilibrium is 1 plus 2x by 10. And this value, I can say it is equal to 0.2. 0.2 means 2 by 10. 10 cancel. X value will be 0.5. If you got the X value, put the value of X in these values, in these expressions. 2 minus X. 2 minus 0.5 is 1.5. 1.5 divided by 10, 0.15 molar. This is the concentration of A at equilibrium. 1 minus X. 1 minus 0.5 is 0.5. 0.5 divided by 10, 0.05 molar. Similarly, 1 plus 2x by 10, 1 plus 2x by 10, it will come as 0.2 molar. So basically, these are the actual concentrations of reactants products at equilibrium. These are the actual concentrations of reactants and products at equilibrium. Now you can easily write the expression for Kc. Kc will be concentration of C at equilibrium. How much is that? 0.2. Raised power stoichiometry coefficient, that's 2. Divided by concentration of A at equilibrium. How much is that? 0.15. Raised power stoichiometry coefficient, that's 1. Concentration of B at equilibrium, that is 0.05. Raised power stoichiometry coefficient 1. Solve it, get the value of Kc. Is it clear?
Is it clear, guys? Is it clear? Yes or no in the chats? I'm going to solve a few more questions so that it becomes like properly clear. Look at this question, guys. The question is, on starting with 1 mole of HI in a 2-liter container, calculate the concentration of each species at equilibrium if Kp for the decomposition of HI. First of all, you are decomposing HI. Remember this reaction. When HI is decomposed, what do you get? You get H2, and with H2 you get I2. Right? You get I2. See how you are going to tackle the questions. See how you are going to tackle the questions. Understand? Understand, guys? Yes, you will have a biology class also at 7 p.m. today, right? But I'll also continue here on this stream. Biology ma'am will also continue. You will have to watch one of the session in the recorded format. Okay? You'll have to watch one of the session in the recorded format. The choice is yours. Okay? Like, ma'am will start at 7 p.m. I'll also continue at 7. So 2 sessions will be live on the channel at 7 p.m. One is my session, one is ma'am's session. One of the session you will have to watch in the recorded format. That's okay, right? That's okay, because we have got lesser time left. We cannot afford to do things. We cannot afford to leave things. When class will be over? Class will be over till my throat is, Okay, let's see. See, guys, on starting with 1 mole of HI, so we are starting with 1 mole of HI. Understand? We are starting with 1 mole of HI in a 2-liter vessel. In a 2-liter vessel. Calculate the concentration of each species at equilibrium if Kp is equal to 16. We are given with Kp, right? We are given with Kp. How much is Kp for this reaction? 16. Can you tell me what is delta Ng for this reaction? What is delta Ng for this reaction? 0. If delta Ng is 0, that means Kp Kc has to be. If delta Ng is equal to 0, that means Kp Kc has to be equal, right? So this is also the value of Kc. Perfect. This is also the value of Kc. Now, guys, this is 1. This is 0. This is 0. Now, at equilibrium, let's assume out of 1 mole of reactant, X moles got converted into product. So I'll be left with 1 minus X. So these are the moles of reactant in the container at equilibrium. Now, 2 moles of HI gives 1 mole of H2. 1 mole gives 1 by 2. X gives X by 2. Similarly, 2 gives 1. 1 gives 1 by 2. X gives X by 2. Now, what I'll be doing? Divide these moles with the total volume of the container. So this is divided by 2. When this is divided by 2, it becomes X by 4. When this is divided by 2, this becomes X by 4. So these are the concentrations of reactants products at equilibrium. Right? These are the concentrations of reactants products at equilibrium. So technically, I'm supposed to calculate concentration of each species at equilibrium. So if I want the concentrations of each species at equilibrium, I need to get the value of X. How do I get the X? For that purpose, what I can do, I can write the expression for Kc. What is the expression for Kc? Kc expression will be concentration of H2, X by 4. Concentration of I2, X by 4. So it's X by 4 ka square. Divided by concentration of Hi ka square, which is 1 minus X divided by 2 ka square. And this value as per the question is 16. This value as per the question is 16. See, this is 2 ka square 4. 1, 4, 1, 4 gets cancelled. So it will be X square divided by 4 multiplied by 1 minus X ka square is equal to 16, right? If you take root on both the sides, it becomes X divided by 2 minus 2X is equal to 4. So which means that X is equal to 8 minus 8X, or I can say 9X is equal to 8, X is equal to 8 by 9. If you got the value of X, put the value of X here. What do I have to calculate? I have to calculate concentration of each species. Okay. 1 minus X by 2. So concentration of each species at equilibrium. 1 minus X by 2. 1 minus 8 by 9 divided by 2. How much it will be? This will be 9 minus 8. That's 1. 1 by 9. It will be 1 by 18. So this is the concentration of reactant at equilibrium. X by 4. How much is X? 8 by 9. So this is 8 divided by 9, 4 is 36 molar. This is the concentration of this one. Even this will be 8 divided by 36 molar. Understood? Is it clear? Is it clear, guys? Is it clear?
Now guys, sometimes what you have to do, sometimes you will have to start with the pressure directly. See, till now I was starting with moles. I start with A, 0, 0, some A minus X, X, etc., etc. Okay. Now the point is, sometimes you will be starting with the pressure. Sometimes you'll have to start with the pressure directly. Sometimes you'll have to start with the pressure directly. Like you have this question. The reaction is AB3. AB3 gas. It gives what? It gives AB2 gas. And with AB2 gas, what do I have? I have half of B2 gas. Okay. Now, as per the question, initially at time t is equal to 0, the pressure of AB3 is 900. This is 900 torr. This will be 0. This will be 0. Now, my dear students, what you have to do? You have to treat the pressure in the similar way. You have to treat the pressure in the similar way as we treat the moles. So, this will be 900 minus X torr. 900 minus X torr. Now, 1 gives 1, X gives X. 1 gives 1 by 2, X gives X by 2. So, what did you get? So, technically, I would say you got the partial pressures directly. You got directly the partial pressures of reactants products at equilibrium. You got directly the partial pressures of reactants products at equilibrium. Now, as per the question, total pressure of the mixture at equilibrium. That's given to me. How much? Total pressure of the reaction, total pressure of the mixture at equilibrium is 1000 torr. Total pressure of the mixture at equilibrium is 1000 torr. Now, total pressure at equilibrium will be this plus this plus this. So, it will be 900 minus X plus X by 2. This is equal to 1000. Right? So, X cancels out. 900 goes that side. So, it will be 100. So, X will be 200. X will be 200 torr. Now, 900 minus 200 is 700. This will be 200. X by 2, 200 by 2. This will be 100. So, you got the exact partial pressures. You got the exact partial pressures of reactants products at equilibrium. Since you got exact partial pressures of reactants products at equilibrium, then you can calculate Kp expression easily. Partial pressure of AB2 at equilibrium, that is 200 torr, raised power stoichiometric coefficient 1. Partial pressure of B2 at equilibrium, 100, raised power stoichiometric coefficient 1 by 2. Partial pressure of AB3 at equilibrium, 700, raised power stoichiometric coefficient 1. When you solve it, value comes out to be 20 by 7. Got it, guys? Tell me once. Is it clear? Is it clear? Quickly in the chats. All right. Now, similarly, there's a term called as degree of dissociation. Similarly, there's a term called as degree of dissociation. There's a term called as degree of dissociation. My dear students, degree of dissociation is represented by alpha. Degree of dissociation is represented by alpha. How do we define it? Degree of dissociation is basically the fraction of reactant. The fraction of reactant which gets converted into product. Degree of dissociation is the fraction of reactant which gets converted into product. What it means exactly, where do we use it? Have a look. For example, you have got the reaction like this. Again, A gas, it gives B gas plus C gas. This is the reaction. Let's say at time t is equal to 0, we have got A moles of reactant. This will be 0, this will be 0. Now let's assume that degree of dissociation is alpha. What is degree of dissociation? Alpha. Alpha is defined as number of moles of reactant dissociated. Number of moles of reactant dissociated. Matlab number of moles of reactant which get converted into products. Number of moles of reactant which get converted into products divided by initial moles of reactant. This is alpha. Number of moles of reactant dissociated. Number of moles of reactant converted into product divided by initial moles of reactant. Now tell me, this is alpha is equal to ND divided by how many initial moles of reactant? I have A. So ND will be equal to what? ND will be A into alpha. ND will be A into alpha. What does that mean? That means these are the moles of reactant which have got converted into product. These are the moles of reactant which have got converted into product, which have got dissociated. Correct? So if you see carefully, I started with A moles of reactant. I started with A moles of reactant. And out of A moles, A alpha moles got converted into product. Out of A moles, A alpha moles got converted into product. So can I say I'll be left with A minus A alpha? Now, 1 gives 1, A alpha gives A alpha. 1 gives 1, A alpha gives A alpha. Right? So these are the moles of reactants products which are present in the container at equilibrium. These are the moles of reactant product which are present in the container at equilibrium.
So technically, till now I used to do a minus x, a minus x, a minus x, x and x. So technically I would say this a alpha is nothing but x. Technically I'll say this a alpha is nothing but x. Okay. One more thing, guys, which I would want to share with you here. What is that? Remember, sometimes in the question, they will give percentage dissociation. They won't give alpha. Remember, percentage dissociation is nothing but alpha multiplied by 100. Percentage dissociation is nothing but alpha multiplied by 100. Remember this particular point as well. Now the point is, how do we do Kp and Kc calculation? How do we do Kp and Kc calculation? By degree of dissociation method. How do we do Kp and Kc calculation by degree of dissociation method? Now I'll make you understand. How do we do the Kp Kc calculation by degree of dissociation method? I'll just take one simple example so that it becomes clear to you. Let's say the reaction is 2 times A gas. Okay, it gives B gas plus C gas. Tell me, what is delta Ng for this reaction? Delta Ng for this reaction is 0. Now you tell me, if delta Ng is 0, can I say Kp and Kc would be equal? Of course, your Kp and Kc value would be equal. Kp and Kc would be equal. Right? Kp and Kc would be equal because delta Ng is 0. Now guys, let's say degree of dissociation is also alpha. At time t is equal to 0, we are starting with A moles of this. This is 0, this is 0. Now at equilibrium, I'll be left with A minus A alpha. At equilibrium, I'll be left with A minus A alpha. Now tell me, 2 moles give 1. 1 gives 1 by 2. A alpha gives A alpha by 2. Similarly, 2 gives 1. 1 gives 1 by 2. A alpha gives A alpha by 2. So these are the moles of reactants products at equilibrium. Now, in order to calculate Kc, what do I need? I need concentrations. How do I convert these moles into concentrations? Divide these moles with the total volume. Divide these moles with the total volume. Divide these moles with the total volume. What are these terms now? These are the concentrations of reactants products at equilibrium. Now you can easily make the expression for Kc. But before making the expression for Kc, let's calculate partial pressures also at equilibrium. Let's calculate partial pressures of reactants products at equilibrium. Think, how many total moles are there in the container at equilibrium? Total moles in the container at equilibrium will be A minus A alpha plus A alpha by 2 plus A alpha by 2, which will come out to be A. Now divide A minus A alpha with total moles. Divide this A alpha by 2 with total moles. Divide this A alpha by 2 with total moles. What do I call them as? These are called as partial pressures. Now, these partial pressures are multiplied with total pressure of the mixture at equilibrium. These partial pressures are multiplied with total pressure of the mixture at equilibrium. What do I call them as? I mean, these mole fractions are multiplied with total pressure of the mixture at equilibrium. Mole fraction into total pressure of the mixture at equilibrium. Mole fraction into total pressure. What do I call them as? Partial pressures. So I got the partial pressures of reactants products. I got the partial pressures of reactants products. Now, do you see any term getting cancelled out here? A gets cancelled. So it becomes 1 minus alpha into Pt. A gets cancelled. This becomes alpha by 2 multiplied by Pt. This also becomes alpha by 2 multiplied by Pt. What are these terms? These are the partial pressures of reactants products at equilibrium. I got concentrations at equilibrium. I got partial pressures at equilibrium. Now it is the high time to write Kc expression and Kp expression. Now tell me, how do I write Kc expression? Kc is going to be concentration of B at equilibrium. How much is that? A alpha by 2B. Multiplied by concentration of C at equilibrium. That's again the same, those square. Divided by concentration of A at equilibrium. A minus A alpha divided by V raised by stoichiometric coefficient. Now do a bit of calculation. See, this will be A square cancel, V square cancel. So I will be left with alpha square divided by 2 ka square is 4 multiplied by 1 minus alpha ka square. This is the final expression which I get after all the cancellation. Right? Now, I want to write the Kp expression. Kp expression will be partial pressure of B at equilibrium. How much is that? Alpha by 2 multiplied by Pt. Similarly, partial pressure of C at equilibrium, that's again the same. So square divided by partial pressure of A at equilibrium. How much is that? 1 minus alpha multiplied by Pt whole raised by stoichiometric coefficient. Stoichiometric coefficient here is 2, right? So see what all things will get cancelled out. Pt square cancels out. So it's going to be alpha square divided by 2 ka square 4 multiplied by 1 minus alpha ka square. Do you see, guys? Kp again comes out to be same. Kp is again coming out to be same. Right? Why is that? Because the reaction which we have its delta Ng was 0. Yeah? Is everything clear? I'm asking you. Okay? Perfectly done. One more thing, guys. One more important thing that I want to give you here. What is that? Remember it directly. Alpha. Just a second. Oh, should I teach it here or? Just a second, guys. Just give me a second, okay? Okay. So you mark the heading here as effect of alpha, or write it as simple variation of alpha with volume and pressure. Variation of alpha with volume and pressure. Remember, alpha is directly proportional to V raised power delta Ng divided by sum of stoichiometry coefficients of gaseous products. Similarly, alpha is directly proportional to 1 by P, where P is the total pressure, raised power delta Ng divided by sum of stoichiometry coefficients of gaseous products. These are two important results. Why they are important? Let me tell you their significance. Understand their significance, guys. See what I'm going to do. For example, you have got the reaction like this. PCl5 gas, it gives PCl3 gas plus Cl2 gas. What about delta Ng for this reaction, first of all? Delta Ng is number of moles of gaseous product, 2 minus 1 is 1, right? What is the sum of stoichiometric coefficients of gaseous products? Sum of stoichiometric coefficients of gaseous products. Sum of stoichiometric coefficients of gaseous products is 1 plus 1, 2, right? That means alpha will be directly proportional to V raised power. Delta Ng is 1 divided by sum of stoichiometric coefficients of gaseous product is 1 by 2 basically. So you can say alpha and volume, this is how they are related. Alpha is directly proportional to square root of V for this particular reaction. Similarly, you can say alpha and pressure. Alpha is inversely proportional to pressure whole raised power, same, delta Ng divided by sum of stoichiometric coefficients. Delta Ng is 1, sum of stoichiometric coefficients is this. So alpha is inversely proportional to basically square root of pressure. Sometimes they'll ask you a question like this. They'll ask you how alpha is related to volume, how alpha is related to pressure. Okay? Sometimes they'll ask you something like this as well. How alpha is related to volume and how alpha is related to pressure. Okay? Got it? So first of all, you have to calculate delta Ng for the reaction. Then you have to calculate sum of stoichiometric coefficients of gaseous products. Now guys, there is one more topic left here. That is your Chatelier principle. That is your Chatelier principle. See, I'm not going to explain Chatelier principle. I'll just tell you those points which are required to solve the questions. Okay? I'll tell you those points which are required to solve the questions. Okay, see guys now. See first of all. The first thing, for example, you have got a reaction like this. A gives B. A gives B. Let's say. Remember one thing, whenever you'll be having a reaction at equilibrium, whenever you will have a reaction at equilibrium, whatever you do to the reaction, if you have got the reaction at equilibrium, whatever you do to the reaction, equilibrium is going to do opposite of that. Equilibrium is going to do opposite of that. Just remember it like this. Your questions will be solved easily. I'm not talking about the conceptual part of it, right? You have got nothing to do with that right now. I'm just telling you those things which are required to solve the questions basically. So at equilibrium, whatever we do to the reaction, equilibrium does opposite of that. So what I'll be doing, for example, if you increase the concentration of reactant, equilibrium has to decrease it. How equilibrium will decrease the concentration of reactant? It will shift the equilibrium in the forward direction. So equilibrium will shift forward. Simple. Okay. Similarly, if you decrease the concentration of reactant, equilibrium will try to increase it. How? They'll be backward. Okay. If you increase the concentration of product, equilibrium will try to decrease it. How? Again backward. Backward shift. Okay. If you decrease the concentration of product, equilibrium will try to increase it. How? Forward shift. Perfect. Got it? Is this clear? This is how you can remember it. But you have taken note of one thing here. In a reaction, if you will be having some solid or a liquid. Okay, solid. See, I'm writing a statement, then I'll make you understand. On adding or removing a solid. On adding or removing a solid at equilibrium. Remember, there'll be no shift. What does that mean? For example, you have got the reaction like this. CaCO3 solid in equilibrium with CaO solid plus carbon dioxide gas. Okay. Now, my dear students, if you increase the amount of this or decrease the amount of this, nothing happens. There will be no shift. When you add or remove any solid at equilibrium, nothing happens. There will be no shift at all. Remember this particular point. This is important. From this, question will be asked. So this was point number one. Point number two, in case of endothermic reactions, on increasing the temperature, reaction shifts in the forward direction. On decreasing the temperature, it shifts backward. This is for endothermic reaction. Similarly, for exothermic reaction, on increasing the temperature, there will be backward shift. And on decreasing the temperature, there will be forward shift. Okay? This is one more thing which you are going to remember. It has got explanation as well. Van 't Hoff equation, etc. Nothing to do with that. Now, guys, the third point. Remember, on increasing the pressure,
on increasing the pressure, equilibrium shifts in the direction, in which gaseous moles decreases. What does that mean? That means, for example, you have got the reaction like this. PCl5 gas, it gives PCl3 gas plus Cl2 gas. Let's say this is the reaction. In the forward direction, are the gaseous moles increasing? Yes. 1 on this side, 2. In the backward direction, gaseous moles are decreasing. Now, since the reaction is at equilibrium, if you increase the pressure, equilibrium shifts in the direction in which gaseous moles decreases. So if I increase the pressure, equilibrium will shift in the direction in which gaseous moles decreases. That means at that point of time, which shift will happen? Backward shift will happen. Okay, in this particular case. But take a note of one more thing. If you will have any reaction whose delta Ng is 0, if you increase or decrease the pressure, there'll be no shift. Any reaction whose delta Ng is equal to 0, on increasing or decreasing the pressure, there'll be no shift. Similarly, guys, these are 3 parameters, right? The fourth parameter, what is that? When you add an inert gas, let's say you have got the reaction which is at equilibrium. Now you are adding some inert gas at constant volume. Remember, when you add inert gas at constant volume, again, there will be no shift. Similarly, when you add inert gas at constant pressure, equilibrium shifts in the direction in which gaseous moles increases. Remember this particular point as well. On adding inert gas at constant pressure, equilibrium is going to shift in the direction in which gaseous moles increases. Let me take the example as well. Let's say you got the reaction like this. N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. Tell me one thing. In forward direction, are the gaseous moles increasing or decreasing? 1 plus 3 is 4. This is 2. So gaseous moles are decreasing in the forward direction. In the backward direction, gaseous moles are increasing. Now, if I add the inert gas in the system at constant pressure, equilibrium will shift in the direction in which gaseous moles will increase. That means equilibrium will shift forward. Okay? Equilibrium will shift forward at that point of time. Perfect. But here, one more thing you have to remember. Here, my dear students, one more thing you have to remember. If you have got the reaction whose delta Ng is equal to 0, and if you add inert gas at constant pressure, or the reaction whose delta Ng is 0, when you add inert gas at constant pressure, remember there will be no shift. All of these things will have got logics as well. I'm not talking about the logics explanations. I'm just telling you the things which you have to remember, right? Now the last thing, when you add the catalyst at equilibrium, nothing happens to equilibrium constant. When you add catalyst in the reaction at equilibrium, nothing happens to equilibrium constant. Now, if I quickly recap it, or let's recap it through the question. Tell me the answer of all these questions. What do you think? What do you think is going to be the answer? Tell me, people. Quickly in the chats. Done? See guys, first of all, more H2 is added. If you increase the amount of H2, equilibrium will try to decrease it. How? Forward shift. NH3 is added. If you add NH3, equilibrium will try to decrease it. Backward shift. Is the reaction endothermic or exothermic? Since heat is absorbed, endothermic. And on increasing the temperature, in endothermic reaction, forward shift is favored. Inert gas is added at constant volume, no shift. Inert gas is added at constant pressure. Reaction shifts in the direction in which gaseous moles will increase. Gaseous moles are increasing in backward shift. So, it will be backward shift. Done? Done, people? If this is done, tell me the answer of this one. Quick. Tell me the answer of this one. Quickly. First of all, you are adding an inert gas in a closed container. Closed container means volume is constant. Closed container means volume is constant. So you are adding inert gas at constant volume. Will there be any shift? Inert gas addition at constant volume? No shift, right? So no change will happen in the concentration of reactants and products. Perfect. Tell me this one. The equilibrium amount of carbon dioxide can be increased by. We have to increase the equilibrium amount of carbon dioxide. How equilibrium amount of carbon dioxide can be increased? When reaction will shift forward. Now, how reaction will shift forward? If you increase the amount of reactants. If you increase the amount of reactants, equilibrium will try to decrease it. How? It will shift the reaction forward, due to which carbon dioxide amount will increase. So, increasing the amount of reactant, increasing the amount of carbon monoxide. Perfect. My dear students, this was your chemical equilibrium. It is done and dusted. Now is the time for ionic equilibrium, but ionic equilibrium will be started after the break. Okay, let's take a small break. Let's refresh ourselves because my throat is also not in better condition. It is 6:43. We'll start at 7:10. Huh? Okay. But is everyone going to join back or you will leave? I know there is a biology class scheduled at 7 p.m. but it's completely your choice. Okay. See, both the streams will go parallelly, live. One of the session you will have to watch recorded. Someone is saying no break. I know you don't need break, but I need break. You can understand the way I talk now. Yeah. Okay. So ionic equilibrium starts at 7:10. So I would want every one of you to be back on time. Okay. All right, guys. Chalo. You also take some rest, but be back on time. I would want everyone to be back. See you in a while.
Is everyone back? Yes. Is everyone back? Let me know once in the chats. Quick, everyone. All right. So, my dear students, let me know once if chemical equilibrium chapter is like perfectly clear to everyone. Can you quickly let me know in the chats if this chapter is like very, very much clear? All right. Perfect. I think it's been almost like 9 hours we have been together, yeah? KPKC is scary, is that? It's not. You just revise it once after the session ends. It'll be perfectly fine. Okay, is everyone alive? Alive and kicking? Is everyone alive and kicking? Yeah? Perfect. Yes, I know you have zoology class, biology class scheduled to 7:30. I told you already, like there'll be 2 sessions going on parallelly after 7:30, right? So one of the sessions you'll have to watch in the recorded format. Yeah? Chalo, let's move on to the chapter Ionic Equilibrium. My dear students, the first thing, what are the topics from which questions are asked in the chapter Ionic Equilibrium? Let's talk about that. Most of the times, you'll find the question from the topic pH. This is the main topic here from which the questions are frequently asked, pH calculation. Well, after pH calculation, there is one more topic from which questions can be asked. That is your salt hydrolysis. And there is one more topic. What is that? That's what you call as buffer solution. And apart from buffer, there is one more topic that's called as solubility product. Well, these are the topics from which the questions are frequently asked when it comes to the chapter Ionic Equilibrium. Okay? So we'll be covering all these topics one by one in detail, in depth. All right, people? I'll be starting right from basics only because this, I believe, like majority of the students find this chapter tough. So I'll be starting this particular chapter from the basics. I won't directly go to pH. Before going to pH, I'll try to cover some basic things so that it becomes clear to you. Okay? So let's move on. And my dear students, I'm marking the heading here as ionization constant. I'm marking the heading here as ionization constant, or you call it as the dissociation constant. Ionization constant or dissociation constant of a weak electrolyte. This is something which I represent with Ki. Now, first of all, what is a weak electrolyte? That's something every one of you would be already knowing. What is a weak electrolyte? Weak electrolyte is any substance which on dissolving in water, does not dissociate completely, right? Any substance which on dissolving in water dissociates partially into its ions. That's what you call as weak electrolyte. Now, my dear students, regarding weak electrolytes, you have to remember just one thing. What is that? Whenever you introduce a weak electrolyte in water,
that weak electrolyte that gets partially ionized, that gets partially dissociated, and that weak electrolyte remains in equilibrium with its ions. This is the first thing which you should remember from now onwards. Again, I'm repeating the same thing. When I talk about weak electrolyte, when you introduce weak electrolyte in water, it is going to get partially ionized. It will get partially dissociated into its ions. And that weak electrolyte in water is going to remain in equilibrium with its ions. What does that mean? Let's have a look. For example, I've got a weak electrolyte AB. AB, for example, is a weak electrolyte. Now, my dear students, you are introducing this weak electrolyte in water. Now, when you introduce this weak electrolyte in water, it will get partially ionized and its ions will be, for example, A positive aqueous and B negative aqueous. These are going to be its ions. Okay. Now, my dear students, let's assume initially at time t is equal to 0. Let's say initially the concentration of the electrolyte was C. In chemical equilibrium, we used to start with moles. We used to start with A0, 0, A minus A alpha, A alpha, A alpha, right? Here in ionic equilibrium, we are not going to start with the moles. We'll be directly starting with the concentration. We'll be directly starting with the concentration. So I'm assuming the concentration of the weak electrolyte initially is C. Okay? Right? And my dear students, if this is C, then this is going to be 0. This is going to be 0. Now, let's assume the degree of ionization is alpha. So I would say at equilibrium, I'll be left with C minus C alpha. C minus C alpha. Now we use the stoichiometry. 1 mole gives 1 mole. From C alpha, you'll get C alpha. This is also going to be C alpha. Now, if I ask you, what is this C minus C alpha? What is this C alpha? And what is this particular C alpha? Let me tell you, these are not the moles. These are the concentrations. These are the concentrations of reactants and products present in the container at equilibrium. Right? So basically, you introduced a weak electrolyte in water. It got partially ionized. And when it got partially ionized, after that, this weak electrolyte remained in equilibrium with its ions. Right? So in the final solution, the concentration of AB, in the final aqueous solution, the concentration of AB will be C minus C alpha. Concentration of A positive in the final solution will be C alpha. Concentration of B negative in the final solution will be also C alpha. Right? Now, my dear students, I'm going to write the expression for Ki. What is Ki? Ki is what we call as ionization constant. Ki is what we call as ionization constant. Its expression is written the same way as we used to write the expression for Kc. Its expression will be written the similar way as we used to write the expression for Kc. So it's going to be concentration of A positive at equilibrium raised power stoichiometric coefficient, concentration of B negative at equilibrium raised power stoichiometric coefficient, concentration of AB at equilibrium raised power stoichiometric coefficient. Now, my dear students, tell me one thing. What is the concentration of A positive at equilibrium in the container? It is C alpha. Similarly, B negative concentration, again C alpha, divided by AB concentration at equilibrium, that is C minus C alpha. Now, what you can do here is, if you take C common here, one of the C gets cancelled out. So I'll be left with C alpha square divided by 1 minus alpha. This is first of all the expression which I would want every one of you to remember from now onwards. Ki, ionization constant of the weak electrolyte, is nothing but C alpha square divided by 1 minus alpha. If the electrolyte dissociates under the stoichiometry 1 is to 1 is to 1. I believe this is clear. Now, my dear students, try to understand a few more things. After getting the Ka value, I'll be doing certain assumptions. I'll assume certain things. And what are the things which I'm going to assume? My dear students, I'll assume let alpha is less than 0.05. I'm assuming alpha is very small. What does that mean? Alpha is very small means this electrolyte's ionization is very, very, very small. Only a small % of this electrolyte has ionized in water, and after that has attained equilibrium with its ions. So I'm assuming alpha values very small, less than 0.05. If alpha is less than 0.05, then instead of 1 minus alpha, if alpha is very small, instead of 1 minus alpha, I can write 1. Right? Now, I'm going to write the expression again. Expression is going to be Ki is equal to C alpha square divided by, instead of 1 minus alpha, you can write 1. So, my dear students, from here, you can calculate alpha value. Alpha will be equal to under root of Ki divided by C. alpha will be equal to under root of ki divided by c. This is how you calculate alpha value. This is how you calculate alpha value. Now, my dear students, in the question, they'll give you the ki value, they'll give you the c value. Now, you'll be calculating alpha from here. You'll be calculating alpha from here. Correct? Okay. And once you get alpha, that means you can easily calculate the concentration of A positive and B negative at equilibrium. And concentration of A positive in the solution, concentration of B negative in the solution at equilibrium. Both are equal to C into alpha. Alpha you'll be calculating from here. Multiply that with C. You'll be getting the concentration of each ion at equilibrium. Do you understand? Do you understand? Right? Do you understand, people? Am I clear with this? Perfect. Now, my dear students, if I particularly talk about weak electrolyte, the common examples of the weak electrolytes are weak acids and weak bases. Weak acids and weak bases. They are the common examples of weak electrolytes. Weak acids and weak bases. Common example of weak electrolytes. Now, my dear students, if the weak electrolyte is your weak acid, at that point of time, your Ki is replaced by the term Ka. And Ka expression will be the same, C alpha square divided by 1 minus alpha, right? And when you do the assumptions and all, again you will be getting the alpha value. Again you will be getting the alpha value as under root of Ka by C. Alpha value you will be getting under root of Ka divided by C. But when your weak electrolyte is a weak base, then remember your Ki is replaced by Kb. And Kb expression is going to be similar. C alpha square divided by 1 minus alpha. And when you do certain assumptions, your alpha value will be under root of Kb divided by C. Remember these 2 points as well. Okay? So when your weak electrolyte is a weak acid, then Ka. When your weak electrolyte is a weak base, then Kb. Both the expressions are same. C alpha square divided by 1 minus alpha. Okay? Perfect. Now, my dear students, what we are going to do over here, try to understand very clearly what we are going to do over here. Have you heard about Ostwald's dilution law? What Ostwald's dilution law says exactly, what it states. Ostwald's dilution law states that on dilution, degree of ionization of a weak electrolyte that increases. On dilution, degree of ionization of a weak electrolyte increases. Ostwald's dilution law says that with dilution, degree of ionization of the weak electrolyte that increases. Okay? How come it increases? Try to understand. My dear students, for example, this is the container which was completely filled with water. Now, in this container, you have introduced this weak electrolyte, which remained in equilibrium with its ions. Now, for example, in the same container, you are introducing more water. That means you are doing dilution. If you are doing dilution, guys, that means on dilution, what happens to volume of the solution? With dilution, volume of the solution will increase. Your concentration is nothing but moles per unit volume. With dilution, volume of the solution is increasing. If volume is increasing, that means concentration is decreasing. And if concentration decreases, if C decreases, that means alpha value increases. If C decreases, that means alpha automatically increases. So basically, one thing which you have to remember, with dilution, degree of ionization of a weak electrolyte, that increases. With dilution, degree of ionization of the weak electrolyte, that increases. That means with dilution, your weak electrolyte gets more and more converted into its ions. With dilution, your weak electrolyte gets more and more converted into its ions. That's the only thing which you have to remember over here. Perfect. Now, guys, I'm going to talk about the pH calculation. Try to understand what this pH calculation exactly is all about. Or before doing the pH calculation, let's try to solve one question so that it becomes like properly clear to you. See, guys. Look here carefully. The question says, calculate the concentration of each ion. Calculate the concentration of each ion at equilibrium. Calculate the concentration of each ion at equilibrium for 0.1 molar solution of a weak electrolyte AB. So basically, as per the question, you have introduced this weak electrolyte AB into water, and now it's in equilibrium with its ions. Ions are A positive and B negative. Right? Now again, at time t is equal to 0, let its concentration is C. And this C value is given to me in the question, that is 0.1 molar. So this would be 0, this would be 0. Degree of ionization is alpha. At equilibrium, again, this is going to be C minus C alpha. This would be C alpha, and this would be C alpha. Now, if you write the expression for Ki is going to be C alpha square divided by 1 minus alpha, right? Now, you'll be doing certain assumptions. You'll assume let alpha is less than 0.05. At that point of time, 1 minus alpha is taken as 1. Therefore, I'll be getting the alpha value under root of Ki by C. Correct? Now, what is the value of Ki? What is the value of Ki? 10 raised power minus 5. What is the value of C? C is 10 raised power minus 1. I think there is some electricity cut. I'll have to turn one light off for some time till generator is on. Okay, so let's calculate it. It will be under root of 10 raised power minus 4, which will be 0.01. 0.01 means 10 raised power minus 2. So this is your alpha, correct? What am I supposed to calculate? Calculate the concentration of each ion at equilibrium. Do you look at the ions? What are their concentrations at equilibrium? That is C alpha. I would say concentration of A positive as well as concentration of B negative at equilibrium is nothing but C into alpha. C value is given to me in the question. That's 10 raised power minus 1. 0.1. Alpha value I just got 10 raised power minus 2. The overall value is 10 raised power minus 3 molar. So the concentration of each ion at equilibrium. The concentration of each ion at equilibrium is how much? The concentration of each ion at equilibrium is how much? 10 raised power minus 3 molar. Let me know once in the chats if this particular question is clear. Let me know once in the chats, people, if this particular question is clear. Every one of you. Everyone, people. Is it clear? Did you understand how do we deal with such kind of the questions? Perfect. Perfect, perfect, perfect. Now, guys, one more thing. For example, you have taken a weak acid HA and you are introducing this in water. It is going to remain in equilibrium with its ions. Ions will be H positive aqueous plus A negative aqueous, correct? Now, you know all the things. Let its concentration be C. This is 0. This is 0. Now, at equilibrium, this is going to be C minus C alpha. This would be C alpha. This would be C alpha. Now, if you write the expression for Ka, that becomes C alpha square divided by 1 minus alpha. Now, if I assume certain things, let alpha be less than 0.05. Therefore, instead of 1 minus alpha, I can just write 1. So, my alpha becomes under root of Ka divided by C. Now, try to understand what exactly I'm going to do. So, basically, what we did exactly, we introduced the weak acid. We introduced the weak acid in a container which was full of water. Now, this weak acid got partially ionized. It came in equilibrium with its ions. Okay? Now, people, try to understand one thing. Ka and alpha, are they directly proportional or inversely? Ka and alpha, they are directly proportional. So, can I say more the value of Ka, more is going to be the value of alpha? So, that acid whose ionization constant Ka is more, that acid whose ionization constant Ka is more, its alpha will be more. That means degree of ionization of the acid will be more. More the degree of ionization of the acid. That means more acid will get converted into, more acid would have got converted into its ions. If more acid has got converted into its ions, I would say more would be the concentration of H positive in the solution. And more the concentration of H positive in the solution, more is going to be the acidic strength. More is going to be the acidic strength of the solution. More the acidic strength of the solution, lesser is going to be the pH. Right? Lesser is going to be the pH. Simple. Correct? Correct, people? Now, same goes for the bases. Let's say you have taken a weak base BOH and you have introduced this BOH in water. It has got ionized as B positive aqueous and OH negative aqueous. Right? Now, finally, what would be the alpha value? Alpha would be under root of Kb by C. Now, Kb and alpha directly proportional. So, more the dissociation constant of a weak base, more the dissociation constant of the weak base, more is going to be the alpha value for the base. More is going to be its alpha. More alpha means more degree of dissociation. More alpha means more degree of dissociation. More degree of dissociation means more base has got converted into its ions. That means in the solution, more will be the concentration of OH negative. More the concentration of OH negative. I would say more is going to be the basic strength of the solution. More the basic strength of the solution, more is going to be the pH of the solution. Understood? Understood, people? Am I clear with this? Everyone in the chats once? Am I clear with this? Am I clear with this? Just let me know once in the chats quick. Yeah? Just let me know in the chats quick if every single thing is clear till here. Perfect? All right. All right. Now, guys, if this is clear, you should be in a position to solve this question. You should be in a position to solve this question. So you have taken a weak acid CH3COOH, and this weak acid you have introduced in water. So it will get partially ionized, CH3CO negative aqueous, and with that you'll be having H positive aqueous, correct? Perfect. Now, initially at time t is equal to 0, its concentration is C, which is given to me as 0.05 molar. Now this is 0, this will be 0. Now the same process at equilibrium, this will be C minus C alpha, this will be C alpha, this will be C alpha. Now what I can do, I can calculate alpha value. Alpha will be equal to under root of Ka by C. We know that for a weak acid. Under root of Ka. Ka value is 1.25 into 10 raised power minus 6. C value is given to me as 0.05. This will be 1 times, this will be 25 times. Root of 25 is 5. 10 raised power minus 6 ka root is 5. 10 raised power minus 3. So this is alpha. What was I supposed to calculate? I was supposed to calculate the concentration of H positive. What is the concentration of H positive in the final solution? That is C alpha. What is the value of C? C was 0.05, which means 5 into 10 raised power minus 2. And what was alpha? Alpha is 5 into 10 raised power minus 3. So I would say it's going to be 25 into 10 raised power minus 5 molar. This is the concentration of H positive in the final solution. Perfect, guys. Am I clear with this? Am I clear with this? I believe yes. Now, guys, I'm going to move on to one more thing. Post-Walsh dilution, I've discussed with you. Now, I'm going to move on to something called as ionic product of water. Ionic product of water. What is this ionic product of water? Let me tell you, if you talk about your pure water, H2O liquid, pure water is considered to be a weak electrolyte. And it also remains in equilibrium with its ions. Ions will be H positive aqueous and OH negative aqueous. Pure water is also considered as a weak electrolyte. It's going to remain in equilibrium with its ions. Ions will be H positive aqueous, OH negative aqueous. Now, my dear students, if it is a weak electrolyte, then I can write this ionization constant Ki expression. That's going to be concentration of H positive raised power 1, concentration of OH negative raised power 1, divided by concentration of H2O. Now, H2O is a liquid here. Its concentration will be constant. This is constant, this is constant. Multiplication of these two constants will be one more constant that I will call as Kw. So, Kw is nothing but concentration of H positive multiplied by concentration of OH negative. Now, my dear students, remember one thing. At 25 degrees centigrade, concentration of H positive and concentration of OH negative. At 25 degrees centigrade, concentration of H positive and concentration of OH negative in water, both are 10 raised power minus 7 molar. If both are 10 raised power minus 7 molar, I would say Kw value at 25 degrees centigrade will be 10 power minus 7, 10 power minus 7, which will be 10 raised power minus 14. This is the value of Kw at 25 degrees centigrade. Now, you must have studied pH, I believe so. What is pH basically? A lot of you will say power of hydrogen, potent of hydrogen, something. There is nothing like that. What is pH? P is just a mathematical operator. P is just a mathematical operator which stands for minus log. P is just a mathematical operator which stands for minus log. Right? P is just a mathematical operator which stands for minus log. So if I'm writing pH, it means I'm talking about minus log of H positive concentration. If I write POH, P stands for minus log. It means I'm talking about minus log of OH negative concentration. If I write pKw, it means I'm talking about minus log of Kw. If I write pKa, it means minus log of Ka. Correct? So my dear students, in this particular equation, if I multiply throughout with minus log, I I'll get one expression. Expression will be something like this. pH plus POH is equal to 14, right? After doing the derivation and stuff. And this particular equation is only valid at 25 degree centigrade. Okay? Perfect. Now, there are a few things which I want you guys to remember directly. There are a few things which I want you guys to remember directly. What are those things? Remember, my dear students, ionic product of water is directly proportional to temperature. Ionic product of water is directly proportional to temperature. Okay? And remember, on increasing the temperature, remember pH of water decreases. On increasing the temperature, pH of water decreases. pH of water decreases, but neutrality of water remains the same. Neutrality of water remains the same. Neutrality of water remains the same. You know, you might be thinking it's a contradictory statement. On one side, sir is saying when you increase the temperature of water, its pH will decrease. Then how come water is going to remain neutral only? There's a logic behind that. I'm not going there in the logic. Perfect. Just remember this statement. That is super sufficient for you right now. When you increase the temperature of water, its pH decreases, but water remains neutral. So when you are drinking water at 25 degrees centigrade, so you are drinking neutral water. If you are drinking water at 50 degrees centigrade, it's still neutral only. But the pH of water at 50 will be less than that of pH of water at 25. I know this is contradictory, but that's the reality. Okay, it has got logic as well. I'm not talking about the logic here, just the conclusion which can be asked in your examination. They can ask you, on increasing the temperature of water, what happens to pH? You will say pH will decrease. On increase the temperature of water, what happens to neutrality? Water is still going to remain neutral only. Yeah? Okay? Perfectly done. Now, my dear students, one more thing. I believe this is something which you all would be knowing. When concentration of H positive and OH negative in the solution are equal, right? We say the solution is neutral. When the concentration of H positive in the solution is greater than that of OH negative, that means the solution is acidic. The solution is acidic. And when the concentration of OH negative is greater than that of H positive, we say the solution is basic. Okay? Neutral means at 25 degrees centigrade, pH will be 7. Acidic means at 25 degrees centigrade, pH will be less than 7. Basic means at 25 degrees centigrade, pH will be greater than 7. Okay? Now, people, I'm going to jump, okay, into something. What is that? Have a look. A small question. Calculate the pH of water. Calculate the pH of water at 25 degrees centigrade. Kw is given to me as 10 raised per minus 14. Raised per minus 14. Now, you know, Kw of water is nothing but that is concentration of H positive, concentration of OH negative. And this value, as per the question, is given to me as 10 raised per minus 14. Now, water always is neutral at any temperature. That means in water, concentration of H positive and OH negative will be always equal. So it means I can write concentration of H positive square is 10 raised per minus 14, which means that concentration of H positive in the solution is 10 raised per minus 7 molar. If the concentration of H positive is 10 raised per minus 7 molar, I can just calculate pH. P stands for minus log of H positive concentration, right? This value comes out to be 7. So pH of water at 25 degrees centigrade is 7. Okay? Perfect. Am I clear with this? Similarly, guys, for example, there is a question asked like this. Calculate the pH of water. Calculate the pH of water at some temperature, 85 degrees centigrade. Okay? And let's say your Kw is given as 10 raised per minus 13. Kw is given as 10 raised per minus 13. So how will I be tackling this question? Your Kw is nothing but, you know it, concentration of H positive, concentration of OH negative, and this value right now is given as 10 raised per minus 13. Water at all the temperatures is neutral. That means concentration of H positive, OH negative in water is always neutral, whatever is the temperature. So I can write concentration of H positive square is equal to 10 raised per minus 13, or I can say concentration of H positive will be 10 raised per minus 6.5 molar, right? So I can say pH will be equal to minus log of H positive concentration, minus log of 6.5. The value comes out to be 6.5. Log of m raised per n is n log m. Correct? I believe this is clear to everyone. I believe this is clear to everyone.
Is it clear? Now, my dear students, let's see exactly how do we calculate pH of strong acids and strong bases. How do we calculate pH? pH calculation of strong acids and strong bases. How do we calculate pH of strong acids and strong bases? Understand properly what I'll be saying. For example, I'm writing a statement. I'm writing 10 raised power minus 3 molar HCl aqueous. 10 raised power minus 3 molar HCl aqueous solution. I want to calculate its pH. I want to calculate its pH. How do I do it? First of all, HCl. HCl is a strong acid. HCl is a strong acid, and all the strong acids are strong electrolytes. HCl is a strong acid, and all the strong acids are strong electrolytes. So basically, you have introduced HCl in water. And when you have introduced HCl in water, it would have got 100% ionized into H positive and Cl negative. Correct? Now, people, at time t is equal to 0, its concentration is 10 raised power minus 3 molar. This would be 0, this would be 0. Now, it's a strong electrolyte, it's a strong acid. It would have got 100% ionized. So, nothing left. 1 gives 1, 10 power minus 3 gives 10 power minus 3. Even this will be 10 power minus 3. So, in the final solution, what is the concentration of H positive? That's 10 raised power minus 3. So, I can calculate pH of the solution. pH will be minus log of H positive concentration. So, the value comes out to be 3. So, pH of this solution is 3. Simple. Got it? Perfectly done, guys. Perfectly done. Yeah? Is it done? Okay. There might be some variations as well. For example, I'm writing something like this. 10 raised power minus 7 molar HCl aqueous. I want to calculate pH of this solution. I want to calculate pH of this solution. Now try to understand what exactly I'm going to do. I want to calculate pH of this particular solution. Now again, HCl is a strong electrolyte, strong acid. Strong acid means strong electrolyte, completely dissociated, right? How will it undergo dissociation? HCl, when is introduced in water, it will get dissociated as H positive aqueous and Cl negative aqueous. Now, its concentration is kept as 10 raised power minus 7 molar. This is 0, this is 0. Now, after some time, this will be 0, this will be 10 power minus 7 molar, this will be 10 power minus 7 molar. Because it's a strong electrolyte, 100% ionized. So, technically, what is the concentration of H positive here? Concentration of H positive is 10 raised power minus 7 molar. So, pH should be equal to, P is minus log of H positive concentration. So, this value should come out to be 7. This value should come out to be 7. But, pH is equal to 7. That means it's a neutral solution. That means it's neutral. But I have taken acid. pH of acid should be less than 7. pH of acid should be less than 7. Right? It's coming 7. So there is some problem. Let's try to rectify that problem. See, guys. Basically, what happened here in this particular case, you have introduced HCl in water. In water, due to the self-ionization of water, in water, there was already H positive present. H positive concentration due to water is already 10 power minus 7 molar. Now, H positive concentration due to HCl is equal to 10 power minus 7 also. So, what is the net H positive concentration in the solution? Net is 10 power minus 7, 10 power minus 7, which is 2 into 10 power minus 7. Right? So, if I calculate pH now, pH will be equal to minus log of net H positive concentration, which is 2 into 10 power minus 7. A bit of calculation, it is minus log of m into n. Log of m into n means log of m plus log of n, right? So, log 2 is 0.3. Log of m raised power n is n log m. So, minus 7 comes to the front. So, the value comes out to be 6.7. So, this is the pH of the final solution. Understood? Understood, guys? Is it clear? Yes or no in the chats once? Is it clear? Is it clear to everyone? Quickly. Perfect. Amazing. Now, similarly, guys, what if I'll have a strong base? Let's say I'm taking a strong base as I'm writing, for example, 10 raised power minus 3 molar NaOH aqueous solution. It's a strong base, NaOH. I want to calculate its pH.
Now this NaOH, since it's a strong base means strong electrolyte. When you would have introduced this in water, it would have got ionized completely into Na positive and OH negative. Correct? Now, its concentration in the beginning is 10 power minus 7 molar. This is 0, this is 0. Now it's a strong base, completely ionized, so I'm left with nothing. 1 gives 1, 10 power minus 7 gives 10 power minus 7. Similarly, this also gives 10 power minus 7. So tell me what is the concentration of OH negative in the final solution? Concentration of OH negative in the final solution is, sorry, this was 10 raised power minus 3. My bad. This 10 raised power minus 3, huh? Minus 3. Okay. OH negative in the final solution is 10 raised power minus 3 molar. So if you got OH negative, we can calculate POH. P stands for minus log of OH negative concentration, which is 10 raised power minus 3. Log of M raised power N is N log M. So minus 3 comes to the front, log 10 is already 1. So POH we got as 1. Sorry, POH we got as 3. Now you know, pH plus POH at 25 degrees centigrade is equal to 14. Therefore, I can calculate pH. 14 minus POH, 14 minus 3, that comes to 11, right? So pH of this particular solution will be 11. Right? Again, I believe this is clear to everyone. Right, people? Now, similarly, there can be a scenario like this. Let's say I'm writing 10 raised power minus 7 molar NaOH aqueous solution. Now, 10 power minus 7 molar NaOH aqueous solution. If I follow the normal process, what I have been doing, so what will be the OH negative concentration coming from NaOH? That will be 10 power minus 7. So POH will be 7. Therefore, pH should be 7. But pH 7 means neutral. But I have taken base. So what do? At that time, take water into consideration. So you have introduced NaOH into water. In water, there were already OH negatives present. And what was the concentration of OH negative in water? Already 10 power minus 7. What is the concentration of OH negative which is getting generated from NaOH? That is also 10 power minus 7. So if I ask you, what is the net OH negative ion concentration? That is this plus this. It comes out to be 2 into 10 raised power minus 7 molar. So if I talk about POH, P stands for minus log of OH negative, which is 2 into 10 power minus 7. This value will come out to be 6.7. If POH is 6.7, we know pH plus POH is equal to 14. So I can calculate pH from here. 14 minus 6.7. The value comes out to be 7.3. So pH of the solution will be 7.3. Understood? Am I clear with this? Am I clear with this? Let me know once in the chats, people. Am I clear with this? Yes or no? Perfect. Now, guys, there is one more case. Mixing of strong acids. If we mix two strong acids, what will be the pH of the final solution? If we mix two strong acids, what will be the pH of the final solution? What does that mean? For example, this is a container. We have got one more container here. Let's say in this container, I'm keeping HCl aqueous solution. In this container also, I'm keeping HCl aqueous solution, right? So both the solutions are strong acids. They are strong acidic solutions. Let's say its normality is N1, volume is V1. Let's say its normality is N2, volume is V2, right? Now, my dear students, if I mix these, this is strong acidic solution, this is strong acidic solution. If I mix them in this final container, when I introduce both of them into this container, I'll be getting a final solution. I'll be getting a resulting solution. Now, in the question, they'll ask me, calculate the pH of this resulting solution. How do I calculate pH of this resulting solution? My dear students, first of all, understand, in this resulting solution, I will be calculating the H positive concentration. That will be equal to N1V1 plus N2V2 divided by V1 plus V2. And once I get H positive concentration, then I can calculate this is the net H positive concentration in this final solution. Then I can calculate pH, which will be minus log of H positive net. Minus log of H positive net. Do you understand? If you are mixing two strong acids, pH of the final solution is calculated like this. Similarly, if you are mixing two strong bases, so I'm marking the heading as mixing of strong bases. Mixing of strong bases. For example, For example, again, I'm taking two containers, right? Here you have got, for example, NaOH aqueous solution, a strong base. NaOH aqueous, a strong basic solution, right? Let its normality be N1, volume be V1. Let its normality be N2, volume be V2. Now I'm mixing them up. When I mix them up, I'll be getting a final solution here. I'll be getting a final solution, a resulting solution here, right? I'm asked to calculate pH of this resulting solution. First of all, since this is a basic solution, strong basic, this is also strong basic, you are introducing them in this. So I'll be getting the net OH negative concentration here. Net OH negative concentration again is going to be N1 V1 plus N2 V2 divided by V1 plus V2. If you got the net OH negative concentration, you can calculate POH. P stands for minus log of what? Minus log of net OH negative concentration, right? Perfect. I believe this is clear. Similarly, my dear students, imagine now the third case. Imagine the third case. Again, I'm taking two containers. So I'm writing a heading here as mixing of strong acid and strong base. If I mix strong acid and strong base, let's say you have got an aqueous solution of strong acid here. Let's say you have got an aqueous solution of strong base here. Let's say its normality is N1, volume is V1. Let's say its normality is N2, volume is V2. Now you are going to mix them in this particular container. You'll be getting a final solution here, which I call as a resulting solution. I'm supposed to calculate pH of this resulting solution. How do we do it? Understand, guys. Remember one thing. First thing, remember if N1 into V1 comes out to be greater than N2 V2, if the equivalence of acid comes out to be greater than that of equivalence of base, that means the resulting solution will be acidic. If N1 into V1 will be greater than N2 into V2, so the resulting solution is to be acidic. And in that acidic solution, net H positive concentration will be N1 V1 minus N2 V2 divided by V1 plus V2. If you calculate H positive net, you can easily calculate pH, which is minus log of net H positive concentration. Perfect. Now there is one more case. If for example, N2 V2 is greater than N1 V1, if N2 V2 is greater than N1 V1, it means that equivalence of base are more. So resulting solution is going to be basic. And how do I calculate net OH negative concentration in the resulting solution? It is going to be N2 V2 minus N1 V1 divided by V1 plus V2. And once you get OH negative net, you can calculate POH, which stands for minus log of OH negative concentration. And my dear students, the third case, if for example N1 V1 is equal to N2 V2, that means equivalence of acid and equivalence of base are equal, so resulting solution is going to be neutral. Its pH at 25 degrees centigrade is going to be 7. Am I clear? Am I clear, people? Am I clear? Let me know once in the chats. Am I clear? Once in the chats, quick. Can you give this question a try? See, acid, both are strong acids. Right? Both are strong acids. So this is V1, this is M1. This is V2, this is M2. What is the N factor of H2SO4? That's 2. N factor of H2SO4 is 2. Remember, normality is equal to molarity multiplied by N factor. Normality is equal to molarity multiplied by N factor. Molarity is 0.5. N factor is 2. So normality will be 0.5 into 2, that's 1. HCl, its N factor is 1. So normality is equal to molarity into N factor. 0.5 into 1 is 0.5. Now both are strong acids. I'll calculate H positive net in the final solution. When you'll be mixing them up, it's going to be N1 V1 plus N2 V2 divided by V1 plus V2. Now what is N1 into V1? 1 into 400, that's 400, plus N2 into V2. 0.5 into 400 is how much? 0.5 into 400 is 200. Divided by V1 plus V2. 400 is 800. So it comes out to be 6 by 8. 6 by 8 means 3 by 4. Right? This is the net H positive ion concentration. So you can calculate pH. P stands for minus log of net H positive concentration, that is 3 by 4. So it's minus log of M by N will be log M minus log N. Now you know log 3 is 0.6, log 3 is 0.47, Log 4 is 0.6. So the pH of the final solution will be 0.13. Is this particular question clear? Everyone in the chats once? Everyone in the chats, people? Perfect. I believe it's done, right? I believe it's done. Now, my dear students, there is one more case. How do we calculate pH of weak acids? How do I calculate pH of weak acids? How do we calculate pH of weak acids? I'll say weak monoprotic acids, which gives 1 H positive. pH of weak monoprotic acids. pH of weak monoprotic acids. I'll directly give you a formula, remember that. I'll directly give you a formula, remember that. My dear students, pH of a weak monoprotic acid will be equal to half of P of Ka minus log of C, right? And this formula is valid only, if alpha for the weak acid is less than 0.05. Remember it directly. What is C? C is the concentration of weak acid. C is the concentration of weak acid. Ka is the ionization constant of the weak acid. That will be given to us in the question. Yeah? Am I clear? Am I clear? Similarly, guys, if they ask you to calculate pH of a weak base, that particular base that gives only one OH negative, its formula will be POH is equal to 1 by 2 P of Kb minus log of C, where C is the concentration of the base. Okay, and this formula is also valid if alpha value for the base is less than 0.05. I believe this is also clear to everyone. And if you remember these two formulas, you can easily solve the question. For example, okay, before solving the question, one more thing. My dear students, remember this particular value from now onwards. Minus a log of 1.8 into 10 raised power minus 5. This value will be 4.74. Remember this to reduce the calculations. You don't have to solve this value again and again in the questions. In most of the questions, you'll be given with the K value as 1.8 into 10 raised power minus 5. And when you multiply it with minus log, its value will be always 4.74. Its value will be always 4.74. Yeah? Right, people? Perfect. Got it? Let me show you what kind of question can be framed here. See guys, for example, they'll ask me to calculate the pH of 10 raised power minus 1 molar CH3COOH aqueous. And its Ka is given to me as 1.8 into 10 raised power minus 5. Okay, I need to calculate pH of this solution. First of all, CH3COH. CH3COH, weak acid or strong acid? I mean, weak acid or strong? Is that weak acid, right? How do we calculate pH of weak monoprotic acids? There's a formula. Or what is the formula? pH is equal to half of P of K. P stands for minus log. Minus log of this value. That will be 4.74. Minus log of C. C is the concentration of acid. That's 10 raised power minus 1. So it becomes 1 by 2. This becomes 5.74 because this one comes here, right? So it will be 2.87. This is the pH of the final solution, right? Perfect. Its alpha is already less than 0.05. If you calculate alpha, alpha is equal to under root of Ka by C. When you check it also, it will be 0.05, less than 0.05 only. That's why I use the formula directly. All right, guys. Perfect. Now, my dear students, what if we do one thing? What if we are going to mix two weak acids? What if we are going to mix two weak acids? What if we are going to mix two weak acids? How do we calculate pH of the final solution? See, for example, this is the container. Let's say this is the container. In this container, the container is completely filled with water. Now I'm introducing a weak acid HA1. This weak acid is going to remain in equilibrium with its ions. Ions will be H positive aqueous plus A1 negative aqueous. Let its concentration in the beginning is C1. This is 0. This is 0. Let its degree of ionization is alpha 1. So at equilibrium, this is C1 minus C1 alpha 1. This will be C1 alpha 1. This will be C1 alpha 1. And let its ionization constant is Ka1. Now, in the same container, I've got another weak acid Ha2. In the same container, I'm introducing one more weak acid Ha2, right? It will also ionize as H positive aqueous plus A2 negative aqueous. Perfect. Let its concentration is C2 in the beginning. So this is 0, this is 0. Let the degree of ionization is alpha 2. So this will be C2 minus C2 alpha 2. This will be C2 alpha 2. This will be C2 alpha 2. And let its ionization constant is Ka2. Let its ionization constant is Ka2. So basically in the same container, I've introduced two weak acids. So first of all, if I ask you, what is the net H positive ion concentration in the final solution? Net H positive ion concentration will be, what is the concentration of H positive coming from this acid? C1 alpha 1. Concentration of H positive coming from this acid, C2 alpha 2. So net H positive concentration, C1 alpha 1 plus C2 alpha 2, right? This is one way to calculate net H positive ion concentration. Or there is one more way of calculating net H positive ion concentration. That's going to be root of Ka1 C1 plus Ka2 C2. This is one more way of calculating the net H positive ion concentration. And if you get net H positive ion concentration, you can easily calculate pH. P stands for minus log of net H positive ion concentration. Perfect. You can calculate pH of the final solution. Got it? Am I clear, people? Everyone? Everyone in the chats once, quickly. Yeah? Perfect. Is it clear? Now you will be given the values in the question. C1 value will be given, alpha 1 will be given, C2 given, alpha 2 given, or K1 C1 will be given, K2 C2 will be given. You can easily solve the question. I give you the idea of how to solve it. All clear? All right, now we are going to move into what? Someone is saying the worst part of the chapter, salt hydrolysis. Don't worry, it's easy only. See guys, first of all, what is, like how many different types of salts do we have? How many different types of salts do we have? See, first of all, when acid reacts with base, it leads to the formation of salt and water, right? For example, the first type of the salt that we have is the salt of strong acid and strong base. This is the first category of the salt which we have. For example, I'm taking HCl, strong acid. I'm taking NaOH, strong base, right? When acid reacts with base, it leads to the formation of salt. Salt is NaCl. And with NaCl, you have got water. So this is the salt of strong acid and strong base, right? Second category of the salt will be the salt of weak acid and strong base. Weak acid and strong base. Take some weak acid, for example, CH3COH. Take some strong base, NaOH. What is the salt which we get here? Salt is going to be CH3COONA. And with this, you'll be getting water. So this is the salt of weak acid and strong base. This is the salt of weak acid and strong base, right? Third, for example, I'm taking strong acid. Salt of strong acid and weak base. Salt of strong acid and weak base. Take some strong acid, HCl. Take some weak base, NH4OH. This is a weak base, right? So you're going to get the salt here, that's NH4Cl plus water. So this particular salt I'll be calling as salt of strong acid and weak base. Perfect. Now the last step of the salt is going to be the salt of weak acid and weak base. Salt of weak acid and weak base, right? Weak acid and weak base. Let's take the weak base as CH3CO. Let's take the weak acid as CH3COH. Weak base as NH4OH. What do we get here? The salt which we get, that's going to be CH3COONH4. And with this, you'll be getting water. So this particular salt is basically the salt of weak acid and weak base. So we have got four types of salts here. We have got four types of salts here, right? We have got four types of salts here, guys. Perfect. Now the point is, what is meant by salt hydrolysis? What is meant by salt hydrolysis? My dear students, salt hydrolysis is nothing but it is the interaction. It is the interaction of ions of salt. It is the interaction of ions of salt with water. With water to produce either acidic or alkaline solution. So when you introduce salt in water, the ions of salt are going to interact with water. The ions of the salt are going to interact with water. Which ion of salt will interact with water? I'll tell you. The ions of salt are going to interact with water, and that will finally lead to the formation of either acidic solution or alkaline solution. And this process, the process of interaction of ions of salt with water, the process of interaction of ions of salt with water to produce either acidic or alkaline solution, we call the process the salt hydrolysis. For example, let's say you've got the salt as AB. Let's say this is your salt. You are introducing this in water. In water, you know, there are two types of ions present, H positive and OH negative. This salt also has two ions, A positive and B negative. The salt also has two ions, A positive and B negative. Now, what are the possible things which can happen here? Number one, either the cation of salt is going to interact with water or anion of the salt is going to interact with water. If cation of salt interacts with water, this A positive will interact with what? OH negative. When A positive interacts with OH negative, you get AOH. With this, you'll be getting H positive. And when cation of salt interacts with water, we call this hydrolysis as cationic hydrolysis. This is called as cationic hydrolysis. Similarly, when the anion of salt interacts with water, so this B negative will interact with H positive. When it interacts with H positive, you get HB. And what do we get after this? OH negative. And remember, when the anion of the salt interacts with water, we call this hydrolysis as the anionic hydrolysis. Anionic hydrolysis. Now, remember one more thing. That ion of the salt interacts with water. That ion of the salt interacts with water, which would have come either from weak acid or weak base. That ion of salt will be interacting with water, which would have come either from weak acid or weak base. What does that mean? Understand? For example, I'm taking a salt as NH4Cl. If you talk about NH4Cl, there is basically NH4 positive, Cl negative. NH4 positive has come from NH4OH and Cl negative has come from HCl. This is strong acid. This is the weak base. I told you one statement. That ion of salt is going to interact with water, which comes either from weak acid or weak base. So this ion comes from weak base. So this ion of salt is going to interact with water. So if they give you a question, in NH4Cl, when the salt is introduced in water, which ion of salt is going to interact with water? You will say NH4 positive will interact with water because it comes from weak base. Yes. For example, you have got the salt like this. CH3COH. Sorry, CH3CONA. So basically you have got CH3CO negative, Na positive. This is a salt. This CH3CO negative comes from where? CH3COH. Na positive comes from NaOH. Now it's a strong base. This is weak acid. So can I say this ion has come from the weak acid? So this particular ion is going to interact with water. That ion interacts with water, which would have come either from weak acid or weak base. Perfect. Now guys, there is one table that I'm giving you here. Remember that table directly. I'm not deriving any formula. Perfect. I'm not deriving any formula. Actually, one more thing. Before giving the table, remember one more thing as well. Take a note of this particular statement. You can remember it directly. Remember the salt of strong acid and strong base. The salt of strong acid and strong base. It does not undergo hydrolysis. It does not undergo hydrolysis. So when you have the salt of strong acid and strong base, it does not undergo hydrolysis. For example, you've got NaCl. NaCl. It's a salt of strong acid and strong base. When you put it in water, then
There is no interaction of ions of salt with water. Remember directly, the salt of strong acid and strong base, it does not interact with water. It does not undergo hydrolysis. So salt of strong acid, strong base does not hydrolyze. Remember it directly, okay? Remember it directly. Got it? Sir, please save the slides at least once. App may crash. Is that? It's not going to crash. Let's take the risk. Yeah? Let's take the risk. Table you'll memorize, yes. Someone has come. If you have watched 45-minute session, don't watch these. It's a wastage of time. Yeah, right. You're right. You're absolutely right. Let's take the risk also. Yeah? Let's not save the slide set. We'll save it at the end. I'll send you these as PDF, don't worry. All right, let's move on, guys. One table I'm going to give you, and I'm going to put some formulas here in the table. And remember these formulas directly, because the questions are mostly going to be formula based in salt hydrolysis. Questions are mostly going to be formula based in the salt hydrolysis. Okay. Well, people, here I'm going to write the type of salt. The type of salt. Here I'm writing, I forgot the formulas. Hydrolysis constant. And hydrolysis constant is represented by KH. Here I'm writing degree of hydrolysis. Degree of hydrolysis. It is represented by H. And here I'm writing pH of the final solution. These are the three questions which can be asked in your examination. Calculate the hydrolysis constant, calculate the degree of hydrolysis, and calculate the pH. Few formulas you have to remember. For example, you have got the salt of weak acid and strong base. Let's say you have got the salt of weak acid and strong base. Its KH value will be equal to KW divided by KA. Its KH value is equal to KW divided by KA. And KW at 25 degrees centigrade is already 10 raised by minus 14. Ka will be given to be in the question. Okay. Its H value will be equal to under root of KH divided by C. KH will be calculating from here divided by C, where C is the concentration of salt. The salt which you have taken. C represents its concentration. And its pH. Its pH will be, see, this is weak acid, strong base. Which one is dominating? Strong. Strong is base. If the base is strong, so pH will be 7 plus. 7 plus half of, it is going to be P of Ka, P of Ka plus log of C, where C is the concentration of salt. So when the salt of weak acid, strong base undergoes hydrolysis, this is how you calculate hydrolysis constant, degree of hydrolysis, and pH. For example, you have got the salt as strong acid and weak base. Strong acid and weak base. How do I calculate its hydrolysis constant, KH? It is Kw divided by Kb. Basically, the one that is weak, you have to take its K. Here the acid was weak, so in the denominator it's Ka. Here the base is weak, it's Kb. Now H is already under root of KH by C, where C is the concentration of salt. Now what would be the pH here? Which one is strong? Acid. So acid will be deciding here. So pH of the resulting solution will be 7 plus or 7 minus. 7 minus, half of. P of what? Which one is weak? Weak is base. So Kb plus log of C, where C is the concentration of salt. Similarly, if you have got the salt of weak acid and weak base, when the salt of weak acid, weak base undergoes hydrolysis, its degree, its KH is nothing but Kw divided by Ka multiplied by Kb. Kw divided by Ka into Kb. And at the same time, its degree of hydrolysis H is nothing but under root of Kw only,
right? And its pH will be equal. Its pH will be equal to 7 plus half of, it will be P of Ka minus P of Kb. Minus P of Kb. Got it? My dear students, there is one thing which you can analyze. Degree of hydrolysis depends on concentration of salt. Degree of hydrolysis depends on concentration of salt. Degree of hydrolysis does not depend on concentration of salt. So they might ask you a question, in which of the following salt, degree of hydrolysis is independent of the concentration of salt? That's going to be the salt of weak acid and weak base. That's going to be the salt of weak acid and weak base, right? When the salt of weak acid and weak base undergoes hydrolysis, its degree of hydrolysis is independent of the concentration of salt. Okay? Perfect. Okay, tell me one thing. For example, you have got a question like this. 0.1 molar NH4Cl. 0.01 molar NH4Cl. Similarly, 0.001 molar NH4Cl. Arrange the following on the basis of degree of hydrolysis. Arrange the following on the basis of degree of hydrolysis. Now, this is NH4 positive, Cl negative. It's the salt of strong acid weak base. Salt of strong acid weak base. Salt of strong acid weak base is under root of KH divided by C. H is equal to under root of KH by C. So H, degree of hydrolysis, is inversely proportional to concentration. Lesser the concentration, more the degree of hydrolysis. So concentration is least here, so its degree of hydrolysis will be more here. Right? Got it? Okay. Perfect. So for example, I'm giving you a question like this. Let's say you have got 0.1 molar NaCl. You have got 0.1 molar NH4Cl. And for example, you have got 0.1 molar NaCN. You have to arrange them on the basis of their pH. You have to arrange them on the basis of pH. First of all, these are all salts. These are all salts, right? These are all salts. These are all salts. You have to calculate their pH. This is basically Na positive, Cl negative. So this is the salt of strong acid and strong base. It does not undergo hydrolysis, right? Salt of strong acid, strong base, its pH will be 7 only. Now look at this. NH4 positive, Cl negative. NH4 positive comes from NH4OH. Cl negative comes from HCl. So it's the salt of strong acid weak base. Strong acid weak base. Its pH will be less than 7. This is Na positive, Cl negative. Na positive comes from NaOH, strong base. Cn negative comes from HCN, weak acid. HCN is a weak acid. Weak acid, strong base. Weak acid, strong base. So pH will be greater than 7. So you can arrange them on the basis of their pH. Even these sort of questions, they are asked in the examination. Yeah? Perfect? Done? Done, people? Done. Is it clear? Okay. Now there is one more topic. That is your buffer. That's your buffer. First of all, can you solve this question before showing you the buffer, etc.? Look at the question quickly. पूरा दिन आपके साथ लाइव रहा सर, इस बात का घमंड है मुझे. Wow, that's great. Good line this is. Yeah? I'll make one call. Hello? Walaikum salam. Hello? तुझे ठीक असल पर? Can you hear me, guys?
Can you hear me? Can you hear me? Yeah? Tell me, will you be able to solve this question? Guys, it's a simple question. Okay. Calculate the degree of hydrolysis. So H you have to calculate. Degree of hydrolysis. And pH. Okay, pH also you have to calculate. Obtained by dissolving 0.1 moles of this. This is the salt of weak acid and strong base. Weak acid, strong base. Its moles are 0.1. Volume is how much? 100 liters. So can I calculate concentration of this salt? Concentration of the salt will be moles divided by volume. So it's 10 raised per minus 3 molar. So you got the concentration of salt. Okay, Ka is also given. I have to calculate H. Salt is weak acid, strong base. So it will be under root of Kh divided by C. And Kh already is Kw divided by Ka into C. Now Kw at 25 degrees centigrade already is 10 raised per minus 14. Ka is given in the question 2 into 10 raised per minus 6. C is the concentration, that's 10 raised per minus 3. So you can solve it. Similarly, you can use the pH result, guys. I mean, don't make me solve all this. I'm already tired. Do it on your own now. You just have to identify the salt. You just have to use the formula after that. Nothing more, nothing less. Okay. Similarly, there is one more topic like this. What is that? That is your buffer solution. What is buffer basically? Buffer is the solution. Buffer is the solution whose pH does not significantly change. Buffer is the solution whose pH does not significantly change upon the addition of small amount of base into it. So there is a special type of solution in which if you add small amount of acid or small amount of base, its pH is not going to significantly change. Its pH won't change as expected. So these buffer solutions, they show resistance towards the change in pH. They show resistance towards the change in pH, these buffer solutions. Okay? These buffer solutions, they show resistance towards the change in pH. What does that mean? If you have got a buffer solution, if you introduce small amount of acid into it, small amount of base into it, okay, its pH does not change as expected. Right? Perfect. They show resistance towards the change in pH. They show resistance towards the change in pH. And these solutions are called as buffer solutions. Now, these buffer solutions, my dear students, they're of two types. Simple buffer and mixed buffer. Simple buffer and mixed buffer. Simple buffer, basically, it consists of single substance. Single substance. Your salt of weak acid, weak base. Your salt of weak acid, weak base. For example, if you take the salt of CH3CONH4, this is the salt of your weak acid, weak base. This is the salt of your weak acid, weak base. It is going to behave like a buffer. And in the container, there is only one substance present. So it's a simple buffer. Now, your mixed buffer, it is made up of two substances. It is made of two substances, right? Any buffer which consists of two substances, basically, that's called as mixed buffer. And this mixed buffer is again of two types, acidic buffer and basic buffer. Acidic and basic buffer. Now, the point is how acidic buffer is made. My dear students, acidic buffer consists of, if in the container you will have a weak acid, and the salt of same weak acid with a strong base. For example, this is a weak acid. And this is the salt of same weak acid which it has formed with a strong base NaOH. Is it going into your mind? Yes or no, honestly? Whenever in the container, you will have a weak acid and salt of same weak acid which it has made with a strong base like NaOH. Can you tell me once in the chats if you are getting all this or not? Have proper eyes on the screen. The efficiency is decreased, but still doable. See guys, again I'll repeat. Buffer is a solution in which if you introduce small amount of acid or small amount of base, its pH is not going to change that much. Its pH is not going to change that much. Its pH will slightly change, not what we had expected. So these solutions, they show resistance towards the change in pH. You just remember two types of buffers, acidic buffer and basic buffer. How do we make acidic buffer? Acidic buffer consists of weak acid. Let's say the CH3COH, it's a weak acid. And this is the salt of same weak acid, which it has formed with a strong base. Imagine CH3COH, when it reacts with NaOH, it forms CH3CONa. So that is the salt of weak acid with strong base. That's the salt of weak acid with strong base. So my dear students, whenever in the container, you will find weak acid and the salt of same weak acid with a strong base, this entire mixture is called as a buffer. Which buffer? Acidic buffer. It is the acidic buffer. It is the acidic buffer, right? It is the acidic buffer. And my dear students, how do we calculate pH of the acidic buffer? pH of the acidic buffer is calculated by the formula pKa plus log of concentration of conjugate base, or you can write concentration of salt divided by concentration of acid. This is the pH. This is the formula by means of which we can calculate pH of acidic buffer. Now the point is, how do we make the basic buffer? How do we make the basic buffer? Whenever in the container, you will have a weak base, and the salt of same weak base, which that has made with a strong acid, like HCl. For example, in the container, you've got a weak base like NH4OH. NH4OH is a weak base. NH4OH is a weak base, right? And this is the salt of same weak base which it has formed with strong acid like HCl. So this particular mixture, weak base and the salt of same weak base with a strong acid, it's called as a basic buffer. And how do we calculate its pOH? Its pOH is calculated as pKb plus log of concentration of salt divided by concentration of base. I remember these two results directly. Okay? I remember these two results directly. Got it? Okay? Can you solve on this simple question? Understand? Calculate the pH of 1 liter solution of 0.01 mole of CH3COH. So basically in the container you have CH3COH and you have got CH3COONA. So first of all, check carefully. In the container, what have you taken? You have taken a weak acid and the salt of same weak acid with a strong base. What do I call this mixture as? This is called as acidic buffer. How do you calculate pH of acidic buffer? It is P of Ka plus log of concentration of salt divided by concentration of acid. Now what is P of Ka? What is P of Ka? P stands for minus log. Minus log of this value already I've told you, it's 4.74. Plus log of, what is the concentration of salt? Salt concentration is 0.02. Divided by acid concentration is how much? 0.01. So this log 2 is 0.3. So 4.74 plus 0.3 is equal to 5.04. We can solve it like this. Guys, give me a second. Guys, sorry, I had an important call. Okay, can you hear me now? We are almost done, guys. We are almost done. We are almost done. One last topic of this particular chapter. That is solubility product. Solubility product. How do we write solubility product expressions? How do we write solubility product expressions? Okay, how do we write solubility product expressions? Guys, I think this will be the last chapter of the today's session. Okay, because I'm very tired. My throat has given up. Okay, so 2 chapters will be left. One is your thermodynamics and periodic classification. I'll post the recording of that. I'll post a recording of that. Okay. I want to do thermodynamics, but my throat is seriously not allowing. Because you know, my throat was already in bad condition. Now it has gone worse. Okay. Chalo, let's have a look on this particular one first. Organic chemistry marathon will happen on Wednesday. I told you, class 11th organic. Hydrocarbon, if you do not remember, let me tell you, GOC hydrocarbon. I mean your class 11th organic. It is going to happen on Wednesday. Wednesday 3 p.m. it will happen. Okay. Day after tomorrow on Monday. Monday I'll be taking a session wherein I'll be discussing top 100 questions of your complete chemistry. All right. After this session, there will be one more marathon coming for class 12th chemistry. Class 12th chemistry, there will be one more marathon. After Wednesday. Don't worry, before 25, your entire chemistry will be done. Okay, just trust me. Don't worry. Chalo, how do we write the expression for KSP? My dear students, for example, you have got a sparingly soluble salt as AB. Now, first of all, how this AB undergoes dissociation? This salt, it's A positive and B negative. This is how it undergoes dissociation. Let's say the solubility of this salt is S moles per liter. Let's say the solubility of this salt is S moles per liter. Now, 1 mole gives 1 mole. So from S, you'll be getting S moles per liter. Similarly, this also would be S moles per liter. Perfect. So basically, you have got a saturated solution of this salt. You have taken the saturated solution of this salt. Now, when the salt is introduced in water, when the solution is saturated, in the saturated solution, you will find A positive ions and B negative ions. The concentration of A positive ions in the saturated solution will be S moles per liter. The concentration of B negative ions in the saturated solution will be also S moles per liter. Now the point is, how do we write KSP expression? There is a special way of writing KSP expression. It is going to be concentration of A positive raised by stoichiometric coefficient, concentration of B negative raised by stoichiometric coefficient, right? Nothing to do with the reactant. Now what is the concentration of A positive? That's S, concentration of B negative. S into S makes it S square. So this is how you write KSP expression for this kind of the salt AB. Perfect. For example, you have got the salt of the type AB2. You have got the salt of the type AB2. How will it undergo dissociation? It will dissociate as A di-positive aqueous plus 2 times B negative aqueous. Plus 2 times B negative aqueous. Let its solubility is S. This will be also S. This will be 2 times S. Why is that? Because 1 gives 1, S gives S. 1 gives 2, S gives 2S. Now, if I have to write KSP expression, how do I write KSP expression? It's going to be concentration of A di-positive raised by stoichiometric coefficient 1. Similarly, concentration of B negative raised by stoichiometric coefficient, that is 2. So, this is S. This is 2 times S, cos square. So, the value comes out to be 4S cube. This is its KSP expression. This is its KSP expression. Similarly, for example, you have got the salt of the type AXBY. A general salt, AXBY. Now, how will it undergo dissociation? Let me tell you, it undergoes dissociation as X times AY positive plus Y times BX negative. This is how it undergoes dissociation. Now, if the solubility of this is S moles per liter, 1 gives X, so S gives X times S. This will be Y times S.
If you want to write KSP expression, you can do that. That's going to be concentration of A plus Y raised power stoichiometric coefficient multiplied by concentration of B minus X raised power stoichiometric coefficient. The concentration of A plus Y is X times S raised power X. Concentration of B minus X is Y times S raised power Y. So it's going to be X raised power X, Y raised power Y, and it's going to be S raised power X plus Y, right? This is the expression for your KSP. A general expression for your KSP. Okay? This is the general expression for your KSP. All right? Now, how do we use this in the questions? For example, you've got a simple question like this. KSP of MgOH whole twice is 3.2 into 10 raised power. This is 10 raised power minus 14 here, okay? What do you have to calculate? We have to calculate solubility in water. First of all, tell me one thing. MgOH whole twice. How will it undergo dissociation? It undergoes dissociation as Mg dye positive aqueous plus 2 times OH negative aqueous, right? Let its solubility is S. Now 1 gives 1, S gives S. This will be 2 times S. So if I want to write the expression for KSP, it is concentration of Mg dye positive, that's S raised power 1. Concentration of OH negative, that is 2 times S raised power stoichiometric coefficient 2. So this will be simply 4S cube. So I'll say S will be equal to KSP divided by 4 whole raised power 1 by 3. What is KSP? KSP is 3.2 into 10 raised power minus 14 divided by 4 whole raised power 1 by 3. It can be written as 0.8 into 10 raised power minus 14 whole raised power 1 by 3. Okay, so it can be further written as 8 into 10 raised power minus 15 whole raised power 1 by 3. So it can be 2 into 10 raised power minus 5 moles per liter. This is the solubility. Yes, this is the solubility of MgOH whole twice. Perfect. All right, one more. See guys, one more question. Mercurous chloride. Remember how it undergoes dissociation. This mercurous chloride is a special case. How it undergoes dissociation? It undergoes dissociation as Hg2 dye positive plus 2 times Cl negative. Let its solubility is S. This will be S. This will be 2 times S because the stoichiometric coefficients are 1 and 2. Now, if you write KSP expression again, it's going to be 4S cube. So S is simply going to be again KSP divided by 4 whole raised power 1 by 3. Now, what is KSP? KSP is 10.8 into 10 raised power. This is minus 23. Okay, this is not plus 23. It's minus 23 divided by 4 whole raised power what? Whole raised power 1 by 3. So this value will come out to be 2.7 into 10 raised power minus 23 whole raised power 1 by 3. So it can be further written as 27 into 10 raised power minus 24 whole raised power 1 by 3, which can be written as 3 into 10 raised power 3138 minus 8 moles per liter. Like this, you get simple questions when it comes to solubility product, right? And my dear students, with this, so basically our today's chapters to be completed were mole concept, redox, atomic structure, chemical bonding, chemical equilibrium, ionic equilibrium, thermodynamics, and periodic classification. Okay, these were the chapters which I was supposed to do today. And on Wednesday, you will have an organic chemistry marathon of class 11 that will include GOC and your hydrocarbon. This will happen on Wednesday. So out of these chapters, we could complete this one, we could complete this one, we could complete this, and this. These two, I'll be posting a recording of these two, small recording, wherein you can do these chapters as well. Okay? So how many of you are with me from the morning? Who all are with me from the morning? कौन सुबह से मेरे साथ बैठा है? After this session, guys, trust me, you are going to get that eternal satisfaction. At least when you sleep tonight, you'll realize that
today's day was productive. Because how many chapters we completed? Not a small thing, guys. These are big, big chapters. 6 chapters we completed. 6 chapters we completed. But this today's marathon will be incomplete if you do not follow the session which I'm going to take on Monday, day after tomorrow. That is complete chemistry through 100 questions. So that is going to be the question practice session basically. Okay? And do pray for my throat. I hope it gets better. Okay, it's right now in very, very, very bad condition. I'm taking steroids for throat. You can understand the level of it. You can understand its level, okay? You can understand its level. Just give me a second. I'll post your notes right now in the Telegram. So if you are not the part of the Telegram channel, do be the part of the Telegram channel. The name of the Telegram channel is Wassim Bhat Chemistry Official. Okay? Wassim Bhat Chemistry Official is the name of the Telegram channel. All right? WASSIM BHAT Chemistry Official. Let me write it here. Wassim Bhat Chemistry Official is the name of the Telegram channel on which I shall be sharing the handwritten notes of the today's session. And right after, once this session ends now, do let me know in the comment section whether you found this particular session beneficial. Was it actually beneficial? Did you like it? Did you learn new things? Right? All right. Do let me all that in the comment section of the video. So do you know we started with almost 1500 live watching in the morning, and right now there are only 268 students. So this is your actual competition, guys. This is your actual competition. That was not actual competition. That was just fake. This is your actual competition. Yeah? Now have some good sleep today. Okay? Have some good food. Is it downloaded? Not yet. Questions I'll be discussing day after tomorrow. Right? But one thing, do not forget to comment on this particular video, okay? I'll be checking your comments. Basically, by seeing the comments, you get to know whether the session was beneficial for the students or not. If you do not comment, then we don't get to know how the session was. At least we also need to know how the session was, right? Chalo. Take care. Do comment in the comment section, guys, yeah?